There's something very strange happening at the center of our galaxy. This is a 20-year time-lapse of some stars moving around. As you can see, there appears to be some sort of gravitational influence that's whipping these stars around. In particular, if you look at that big star in the middle, you see how it's getting swished around? Swoosh. So how can that be? What's doing that? Well, if you work out the gravitational math, there has to be something there with a mass of about 4.3 million solar masses, approximately right there, in order to explain why this star is getting whipped around like so. But what kind of an object is that? As you can see, you can't see it. It's apparently invisible, and yet in order to have this kind of gravitational influence, this mysterious dark object has to be incredibly massive. And of course, the reason we don't see this object is because it's a black hole. So black holes are predicted theoretically, and a time-lapse like this gives us a real visual sense that this is actually a real thing that exists. But you know what would be great is if we could actually see this black hole. Because you know from the movies that a black hole is not just a black circle against a black backdrop of space that you wouldn't ever be able to see. But no, around the black hole, you're probably going to have an accretion disk of matter and gas getting all swirled around and real hot and glowing. And then you'll have this gravitational lensing around the black hole, where all of that glowing light from the accretion disk is going to get all warped and bent into like this cool image. And so, in theory, if we had a powerful enough telescope, we could, in principle, see what's going on around this black hole. And it turns out that trying to take a picture of the black hole at the center of our galaxy is something like trying to take a picture of an orange on the moon. That's about how small it would appear, and so it's really not a practical thing to take a picture of the black hole. However, it's not totally beyond what's doable. As it turns out, if you hook up a bunch of radio telescopes at different points across the whole Earth, you can create a planet-sized eyeball that can see radio waves, and that would let you see just barely an image of this black hole. It would be a blurry image because the thing is so small relative to how far away it is, but even still, a blurry image of a black hole is better than no image of a black hole. So people went ahead and did that. They connected a bunch of radio telescopes all over the world into what's known as the Event Horizon Telescope, and with that, they were able to capture this image of the black hole at the center of our galaxy. And wow, what an incredible sight! There it is. There's a black hole. You can actually see it. It's like, yeah, okay, it's a hole. There's some stuff around it, just as expected. So that's pretty cool, and, how lucky we are to be able to see this kind of image. So anyway, all that's to say is that black holes are real, they actually exist, which is very bizarre. These things are quite interesting objects. And so today, as we explore the physics of how black holes work, keep in mind, this isn't just theoretical physics, this is really real, it actually exists. One more thing before we get into the video, just to get us hyped up about black holes, check this out. This is M87. M87 is a supergiant elliptical galaxy in the Virgo cluster, and you'll notice that it has this massive jet of particles coming out of it. And this is really an incredible thing because this jet that's coming out of the center of the galaxy is over 5,000 light-years long. Let me do a tangent real quick. Do you know how long 5,000 light-years is? It's crazy long. So light can go around the Earth 7 times in a second. If you shine a laser beam out into space, in a second and a half, it's already past the moon. So imagine that laser beam keeps going on for 5,000 years, and then you think about where that light is going to be in the year 7,000 and something. 7,000 and something, that's not a year. No one's thinking that far ahead. No one's like, oh, gee, I hope the economy's good in the 7,000s. No, it's like beyond human timescale. But that is how long it would take for light going at the speed of light to go 5,000 light-years. So it's really just an unfathomable distance, and yet there it is. In this image, you can see a thing that's 5,000 light-years long, maybe even closer to 6,000. So it is truly the case that the wonders of the cosmos are quite a sight to behold, and we should all have unending gratitude for the ability to see such marvelous wonders. But more to the point for today's video, guess what is creating this massive jet? You guessed it, it's a supermassive black hole. Now, to be clear, this jet of high-energy particles, this is not coming out of the black hole. Nothing comes out of a black hole. That's kind of the whole thing about a black hole. No, these are particles that are getting close enough to the black hole, they get whipped up and whipped around, and you get these colloidal magnetic fields that go blasting the particles off into space. But none of these particles have actually crossed the event horizon and have come back out. That's not a thing. Anyway, the reason I bring it up is the Event Horizon Telescope also took a picture of the black hole at the center of M87. And here it is. Now, this black hole is truly supermassive. It has a mass of about 6 billion times the mass of the Sun, so over 1,000 times the mass of the black hole at the center of our galaxy. This black hole is so huge that its event horizon goes well beyond the orbit of Pluto. So you have this solar system-sized bubble of no return where if anything goes in there, it's never coming back out into our universe ever again. I mean, just think about that. If you were in a spaceship and you go into this black hole, you could cross the event horizon and still have a whole lot of time to fall into the center of the black hole where you're beyond the point of no return, but you haven't yet been torn apart and spaghettified by tidal forces. So it's just wild to think about. Black holes are super cool. They say that in space, no one can hear you scream. But inside a black hole, no one outside can even see you scream. So it's a whole nother level of cosmic horror. But it's also super fascinating. So that brings us to the topic of today's video, which is the legendary 1973 paper, The 4 Laws of Black Hole Mechanics, by Bardeen, Carter, and Hawking. Oh, and by the way, there's a link to the paper in the description below, and I highly recommend printing it out. When you print out a paper, it makes it real, it makes it tangible, and you're like, okay, I'm going to read this. This is a thing. So I highly recommend if you have a printer, print out the paper. If not, at least open it up on another tab, because this video is all about this paper. In fact, the reason this video exists is because this paper contains profound insights about the nature of space and time and black holes, and that's so cool. But it's also quite a difficult paper. And so I made this video as a walkthrough of the paper so that if you want to learn these concepts, you don't have to learn them alone. So I'm here for you, I'm by your side, and we'll get through this together. Oh, and by the way, I made this video for you. You can use it however you want. The different parts are timestamped, so you can think of it like a book. You can hop to whatever part of it you want to. You can watch it all sequentially, or think of it like a choose-your-own-adventure. Or just go ahead and read the paper, and if there's any part you're a little confused about, just skip ahead to that part of the video and we'll go through it. I know this video is super long, and perhaps that might seem intimidating, but think of it as a comprehensive resource that goes into all of the technical details and that will actually help you learn this material more quickly. Because if you really want to get into this paper, and you really want to understand it completely, it is a bit of a time commitment. But that's just how it is. And by the way, the effort is worth it, not only because this paper contains profound insights, but also because it's a great exercise in general relativity. GR is such a big and intimidating subject, and it's like, how do you even begin to learn this subject matter? Well, one good exercise is to focus on a specific paper, and go into it in gory detail, and think of it like you're a cat scratching the scratching post, sharpening your claws, You're like, all right, I'm going to commit to understanding this paper. And if you do that, and if you see it through, and you put in the time and the effort, then you'll come out of it the other side, having developed an increased competency in general relativity. And if that's something that you want to do, this is a great way to do it. Well, all right then. Hey, before we move on, let me say a few words about the legendary authors of this paper. Now, of course, everyone knows Stephen Hawking, but these other 2 authors are also legendary physicists. Bardeen made foundational contributions to black hole thermodynamics, and he also discovered something known as the Bardeen vacuum. And by the way, just a fun fact, James Bardeen was actually the son of John Bardeen, the only person to ever get 2 Nobel Prizes in physics, one for developing the BCS theory of superconductivity, and then another for co-inventing the transistor. So the Bardeens have quite a legacy in theoretical physics. And then next up we have Brandon Carter. Carter has done a lot of pioneering work in general relativity, especially when it comes to black holes. He made really important contributions, especially to the study of rotating black holes, also known as Kerr black holes, as opposed to Schwarzschild black holes, which are non-rotating. And he also discovered the Carter constant. What is the Carter constant, you might ask? Well, that's a topic for another day. But just to pique your interest, I'll put it this way. If you're orbiting a rotating black hole, you'll have 4 conserved quantities: your rest mass, your energy, your angular momentum, and your Carter constant, which is a kind of hidden symmetry. But anyway, that's a topic for another day. And then, of course, Stephen Hawking, you know him, you love him. He was a central architect of modern black hole physics. He discovered Hawking radiation, actually the year after this paper was published, so we'll talk about that some other day as well. And then, of course, if you haven't yet seen the movie, you should watch The Theory of Everything, which is a fantastic movie about Stephen Hawking's life, which was a life marked by terrible tragedy, but also a truly inspiring resilience. And so everyone go and watch that movie if you haven't yet. All right, now with these three authors on a paper, you know it's going to be a good paper. You also know it's going to be a super difficult paper. I mean, I just have to say. The intended audience of this paper are experts in general relativity and black holes. It's kind of expected that the reader has a PhD in that subject matter, and so there's going to be a lot of math in today's video. But if you are really interested in this subject matter and you're willing to put in some time and effort and commitment to learn the math and the theory, then I think you'll find that these ideas are truly profound and beautiful, and that even though it takes effort to learn these difficult ideas, it's ultimately worthwhile because this is how to think about black holes. And that's just such a cool thing to try to think about. All right, so now I'd like to say a few words about the outline of this video so that we know what we're getting ourselves into. Well, first, we're going to read through the abstract of the paper, and that'll give us a summary of what the paper's all about and how we're going to be coming up with these 4 laws of black hole mechanics. After that, I want to take a moment to briefly review each of the 4 laws of black hole mechanics and show how they compare to the 4 laws of thermodynamics, just so that we have a really good understanding of what it is that we're trying to demonstrate in this paper. Then, before getting back into the paper, I want to do a math and physics warm-up where we talk about some of the concepts that are going to be used in the paper. I figure that if we talk about some of the main concepts before getting into the paper, that'll make the paper a little bit more digestible. Then, after the warm-up, we'll get into part 1 of the paper, which honestly is pretty similar to the abstract with a couple of extra things, so we'll breeze through that pretty quickly. And then it's on to parts 2 and 3, which are definitely the hardest parts of the paper. In fact, the math involved in parts 2 and 3 is graduate-level gravitational physics, and while I hope that this video can stand on its own as an explanation of what exactly all of these equations mean, I know everyone has a different background and different experience, and so some of you might be thinking, oh, maybe I should brush up on this, or oh, I'm curious about that, I'd like to learn more about that. And so to go along with parts 2 and 3 of the paper, I highly recommend the book A Relativist's Toolkit, The Mathematics of Black Hole Mechanics, by Eric Poisson. This book has the mathematical tools and context that you need to fully understand this paper, and so I'll be citing equations from the book quite often throughout the video. And that way, if there's anything in parts 2 and 3 that you want to learn more about, you'll know where to go to find that information. Alright then, so after having our mathematical adventure in parts 2 and 3, we're going to come to the final part, part 4, which is actually going to be a little bit easier. We're just going to zoom out and think big picture about the 4 laws. And so we'll say a few words about that, and that'll bring us to the end of the paper. All right, so without any further ado, let's go ahead and get into the abstract of the paper. Expressions are derived for the mass of a stationary axisymmetric solution of the Einstein equations containing a black hole surrounded by matter, and for the difference in mass between 2 neighboring such solutions. So let me go ahead and pause here and say a few comments on what this sentence means. Well, the thing we're going to imagine is that we have a black hole, and it's rotating, but it's rotating in a way which is axisymmetric. That is to say, if you draw a line between the North and the South Pole, then there's going to be rotational symmetry about that axis. And in addition to a black hole, we're also going to imagine some matter around the outside of the black hole, which, for the sake of simplicity, let's go ahead and imagine that as just a thin ring of matter rotating around the black hole. While the arguments in this paper are going to be slightly more generic than just this thin circular ring situation, this visual is totally fine for the purpose of imagination. Now then, the goal of the paper, as stated here, is to derive equations for the mass of this situation. So the mass of the black hole and also the mass of the stuff around the black hole. So the equation that we're going to derive for the mass is shown here. as we go through the paper, we're going to get into exactly what this equation means. For now, don't worry about the details. I just bring it up here as a bit of foreshadowing. But anyway, there's going to be a term involving an integral over the space-like hypersurface outside the black hole, and that pertains to the mass of the matter around the black hole. And then you're going to have a couple of terms involving the event horizon of the black hole, and its angular velocity and angular momentum and surface gravity and area. But anyway, we'll get into all of that later on. And in particular, in part 2 of the paper, that's the part where we derive the mass formula shown here. Then in part 3 of the paper, we're going to go ahead and jiggle that equation a little bit and think about what if we had 2 nearby solutions in this equation. So 2 very similar situations, but maybe one black hole is a little bit different than the other. And so we can take this mass formula and we can apply variational calculus and jiggle all of the things that the mass depends on, and then calculate what is the response jiggling in the mass. That is, what is the little variation in the mass as a function of the variations in all the things that the mass depends on. And so when we calculate that in part 3, we're going to end up with the differential mass formula shown here. And by the way, the process of calculating the differential mass formula is going to be quite tedious. Mathematically, there's a whole lot that goes into it, so just prepare yourself. That's going to be a tough one. But that's okay. As long as you have enough coffee, you can do anything. All right, so then the abstract goes on to say, 2 of the quantities which appear in these expressions, namely the area A of the event horizon and the surface gravity kappa of the black hole, have a close analogy with entropy and temperature, respectively. This analogy suggests the formulation of 4 laws of black hole mechanics, which correspond to, and in some ways transcend, the 4 laws of thermodynamics. And so that's the gist of the paper. What we're going to do is we're going to use general relativity to calculate the mass of a rotating black hole with some matter around it, and then we're going to jiggle that equation to turn it from an integral equation into a differential equation. And then by examining these equations, we're going to draw an analogy between the behavior of black holes and thermodynamics. Oh, one other comment I have to say while we're here. This paper was published in 1973. Then later on, in 1974 and 1975, you had the discovery of Hawking radiation. Hawking radiation we'll talk about it some other day. Well, never mind it for today. But the gist of it is that when you factor in quantum mechanics, which we won't do today, some of the apparent violations of thermodynamics that the 4 laws of black hole mechanics would seem to suggest are actually resolved by taking a more generalized view of the second law of thermodynamics, in which you get a more nuanced picture when you factor in the entropy outside the black hole as well as the horizon entropy. But anyway, this 1973 paper neglects quantum mechanics, and that's fine. The conclusions that we draw in this paper are still going to be true, with a little asterisk, which is that after you study this, you should also go ahead and study Hawking radiation just to add a little extra nuance to this picture. All right, so before we go further, I think it's worthwhile to take some time to review the 4 laws of thermodynamics and the corresponding laws of black hole mechanics. So first we'll talk about thermo, and then we'll talk about black holes. Well, first of all, we have the 0th law of thermodynamics, which is that if 2 systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. One way to imagine the 0th law is that if you have a bath of water and there are 2 objects in the bath, then if one of the objects is in thermal equilibrium with the bath, and so is the other object, then you know that the 2 objects are also in thermal equilibrium with each other. That is to say, everything's at the same temperature. Now, when you hear that, you might think, okay, what's the big whoop? What's the big deal about that? That's pretty straightforward, right? And it's like, yeah, this law is pretty basic. It essentially is just a way of describing that over time, if you leave a system in equilibrium, the temperature will have a tendency to spread out and become uniform across the whole system. And the simplicity of this law is actually why it's called the 0th law. The reason being, the 1st, 2nd, and 3rd laws of thermodynamics were discovered sometime between the mid-1800s and the early 1900s. And all that time, the 0th law was never explicitly stated, but it was something that a lot of people took as kind of an implicit assumption. And no one really thought to give it a name, Until in the 1930s, someone was like, you know what, this actually should be one of the 4 laws of thermodynamics, but by that time you can't call it the 4th law because it's too basic to be the 4th law. So anyway, they went ahead and called it the 0th law. So that's why the numbering starts at 0. It's kind of a historical thing. So then moving on to the 1st law, we have the fact that changes in a system's internal energy are the heat added plus other energy added. And you see this fact written in different ways, but generally the way it's written is delta U equals T delta S plus omega delta J plus whatever other terms are involved with the energy that you're adding or subtracting from the system. And in this equation, U is the internal energy of a system. So, if you have something, it's going to have some energy in it. But then if you're doing things to this object, you're changing its entropy S, its angular momentum J, then the internal energy is going to change, but it's going to change in a way that you can account for, where, for example, T delta S, that's going to be the heat added to the system. Omega delta J is angular velocity times the variation in angular momentum. So if you're spinning the thing up or spinning it down, that's going to have an effect on the energy. Depending on the context, you might have other terms in this equation, like P delta V, or mu delta N, where mu is the chemical potential and N is the number of particles in the system. So anyway, all the 1st law tells us is that the changes in a system's internal energy can all be accounted for in terms of stuff coming into and going out of the system. And so yet again, the 1st law is pretty basic. Like, of course, the change in the energy of a system is just whatever goes out and what comes in. And yet, despite sounding so simple, the 1st law implies, for example, that you can't have a perpetual motion device. Because a perpetual motion device is something that somehow is able to keep manifesting energy out of nowhere. Well, but by the 1st law of thermodynamics, that's illegal. You can't have that. That's not a thing that can exist. So anyway, that's the 1st law. Now moving on to the 2nd law, we find that the total entropy of an isolated system can never decrease. That is to say that over time, there is a tendency for things to become disordered. So, if you're cooking an omelet and you accidentally drop an egg and it falls on the floor and breaks apart, well, that just became a whole lot more disordered. And that kind of thing happens all the time in every kind of different situation. Things are always falling apart. We're all dust in the wind. I'm sorry to say. But yeah, so that's the 2nd law of thermodynamics. And by the way, notice that in the 2nd law, the word isolated is doing a lot of work. So you can have systems where locally the entropy decreases, but those systems are going to put out heat or entropy in some other way, such that globally there ends up being more entropy in the universe. So, we're actually a good example of this because you think about, in order to stay alive, you don't want to have too much entropy. And so, one of the things that it is to be alive is to seek out pockets of low entropy. We call this food and nutrition and things. And, of course, we get energy from the food as well, but food is also low entropy. And then we convert that into stuff of higher entropy. And at the end of the day, the net result of us being alive is that we create a whole lot of a mess here on Earth. But for a beautiful moment of time, we're able to maintain a state of relatively low entropy. All right, and last but not least, we have the 3rd law, which is that absolute zero temperature cannot be reached in a finite number of steps. Now, the way to think about this is that if you want to make something cold, the colder you try to make it, the harder it is to make it that cold. Absolute zero, where there's no thermal jiggling at all, and everything comes to a complete standstill, is a kind of asymptotic limit of how cold something can be. But in reality, things are always jiggling around to some extent. Well, all right then, so those are the 4 laws of thermodynamics. But this video is not about thermodynamics. This video is about black hole mechanics. So now let's talk about the 4 laws of black hole mechanics. Well, the 0th law is that the surface gravity kappa of a stationary black hole is uniform over the event horizon. The way to think about this is imagine that the surface gravity kappa is analogous to temperature. Well, if the surface gravity of a black hole, that is, the gravity at the event horizon, if that's kind of like a temperature, then when the black hole settles down and everything's all in equilibrium, you would expect, if surface gravity is analogous to temperature, that the surface gravity is going to be uniform everywhere across the event horizon. So that's all there is to the 0th law of black hole mechanics. And we're going to prove that in part 2. All right, then moving on to the first law, we have that the changes in a black hole's mass, angular momentum, and surface area are related by delta m equals kappa over 8 pi delta A plus omega delta J, where m is the mass of the black hole, kappa is the surface gravity, A is the area of the event horizon, omega is the angular velocity of the event horizon for a rotating black hole, and J is the angular momentum of the black hole. In this equation, I've also put a plus ... which pertains to the matter outside the black hole. So in the equation shown here, m is actually the mass of the black hole plus the mass of the matter outside the black hole, as we'll talk about in parts 2 and 3. But anyway, if you look at the equation we've written here, and you think that mass is sort of analogous to the internal energy of the black hole, I mean, after all, E equals mc squared, right? Then you do a comparison between this equation and the first law of thermodynamics, and you realize, whoa, there's a structural similarity here, where, yet again, the surface gravity kappa plays a role that appears to be analogous to temperature. And now we see that the area of the event horizon is somehow analogous to entropy. That's very strange, but that's how it appears to be. And you know what? Here's a fun fact. In this paper, all we're doing is deriving a structural analogy, a comparison between the behavior of black holes and the laws of thermodynamics. But it's nothing more than that for today. It's only like a curious little structural similarity. But later on, when we talk about Hawking radiation some other day, you'll see that it's really more than just an analogy. And so this whole paper is kind of doing a very profound foreshadowing about the nature of black holes. For now, it's time to get into the second law of black hole mechanics, which tells us that the surface area of a black hole can never decrease. Now, I should point out that this neglects quantum effects, because we're not going to be getting into Hawking radiation today. In reality, if you account for Hawking radiation, then the surface area of a black hole can decrease very, very extremely slowly as it evaporates over an incredibly long period of time. But for now, ignoring Hawking radiation and just focusing on the idea that the surface area of a black hole's event horizon can never decrease, and thinking about the first law in the equation that we just wrote, where kappa and A appear together as sort of a temperature-entropy pair, and then thinking about the zeroth law, where we see that, okay, so surface gravity kappa is kind of like temperature. Now the event horizon area A is sort of like entropy. Well, entropy can never decrease. And if the surface area A can never decrease, that's sort of another way in which the area of a black hole's event horizon is kind of an entropy-like thing. So that's very intriguing. That kind of makes you go, what's that all about? Why is it that the area of a black hole's event horizon has to do with entropy? Well, okay, now last but not least, let's think about the third law. Let me ask you this. You tell me, what is the third law of black hole mechanics? Just think about how the surface gravity kappa seems to be strangely analogous to a temperature. And if the third law of thermodynamics is that absolute zero temperature cannot be reached in a finite number of steps, then likewise, the third law of black hole mechanics is that the surface gravity kappa can't be reduced to zero with a finite sequence of operations. So in other words, imagine you have a black hole, there's a singularity, there's an event horizon around it with some surface gravity, and you might think, maybe we can throw some matter into this black hole, throw in a bunch of planets and stars and stuff, and try to spin it up. And maybe if we spin it up fast enough, then you can get to a point where there is such a centrifugal effect that the surface gravity becomes zero at the event horizon, and then maybe you can end up with what's known as a naked singularity, where now there is no event horizon, and the black hole is spinning so fast that it's no longer what we would recognize necessarily as a black hole, where you can't escape, but instead it's just like a weirdly infinite point of spacetime or something. Well, the third law of black hole mechanics tells us that we can't do that. We can't spin up a black hole or do anything to a black hole where the surface gravity would be reduced to zero. And we'll talk more about that later towards the end of the video. But for now, I just wanted to list out all the 4 laws of thermodynamics, as well as black hole mechanics, so you can see the analogy that we'll be exploring in this video. All right, my friends, let's go ahead and begin our mathematical warm-up. We're going to be thinking about space and time and space-time and vectors and covectors and derivatives and curvature and some of the mathematical machinery that we're going to use as we explore this paper. So first things first, we have this notion of a 4-dimensional spacetime. And when you first imagine spacetime, naturally you're going to imagine the 3 dimensions of space and the 1 dimension of time merged together into this 4-dimensional manifold. And intuitively, there's a temptation to imagine Newtonian spacetime, which is where space and time together comprise a kind of background, like a stage in which the various things that live in reality operate. So what I'm showing here, this four-dimensional lattice, you can think about the four different dimensions in this lattice as these four different directions, each of which has its own color. So you see the red, the green, and the blue, those correspond to space, to x, y, and z, and then the orange lines correspond to time. Now you might be thinking, hey, wait a minute, orange lines? I don't see any orange lines, I just see some orange dots. But you got to imagine those dots being extruded along the time dimension, so they really are lines, but they're lines that point in time. And that's why the lattice seems to pulsate, because as we follow along that timeline, we're encountering these uniform grid spacings in our four-dimensional lattice. Now, I don't mean to suggest by this diagram that space-time is somehow discrete and made out of four-dimensional pixels. But no, I'm just using the lattice picture because the pulsing in time lets you feel how time is like a dimension. And so if you see that these orange dots are actually lines in time, then you're thinking four-dimensionally. And then you realize, oh yeah, okay, space and time, it is four-dimensional, of course. And just like x, y, and z are perpendicular, time is perpendicular to all of the spatial dimensions. Now that's the Newtonian picture of space-time. But now, as we're about to see, when you factor in relativity, things get a little bit more complicated. So Newtonian spacetime, just think of that as like a starting point for your imagination. But then naturally the question becomes, how does Einstein's picture of spacetime differ from the Newtonian picture? Well, to see that, the first thing we want to do is to define something known as the Minkowski spacetime interval. And to do that, for now, let's focus on the xt plane, that is, the x direction in space, and the time direction. Never mind for now the y and z directions. Those dimensions still exist, of course. But suppose we have something where all of the motion is in a certain direction. And so to understand the evolution of this thing over time, we can plot things in an xt plane, and therefore make the time dimension visible. So the way to read this diagram is that the horizontal direction x is a direction in space, and then the vertical dimension t goes from the past at the bottom, up through the present, right on the x-axis, and into the future as you go up. Now you see we've put this blue dot right at the intersection of x and t, and that we're going to call an event. By event, we just mean a place in spacetime, so it's a point that's somewhere at some time. And for the sake of simplicity, we may as well put our coordinate system directly on that event. So then there's a very important concept, which is the light cone, and we can draw it like so. If you want to imagine what the light cone is, the easiest way to do it is to imagine at the event, you're going to shine two laser beams, one of them going along the positive x direction, and the other one going along the negative x direction. And over time, those beams of light are going to be moving at a constant speed, and so as time increases, the x-coordinate is going to increase at a linear rate. And because we're using natural units where the speed of light is 1 by definition, and all other speeds are relative to the speed of light, then you'll see that the light rays go out at a 45-degree angle in our spacetime diagram. And then reversing that thought process, you can imagine the bottom half of the light cone as being the rays of light that were coming in from far away and that converged at x equals 0 at the moment of our event. So what's so cool about the light cone? Why do we care about light cone? What's this all about? Well, you know how the speed of light is a speed limit, and so nothing can go faster than the speed of light, and that means that all of the possible chains of cause and effect going from our event to any other event in the universe has to be within the light cone. So inside the light cone on the top half of the plane gives us all the events that our event could potentially influence in the future. And likewise, the points in the light cone on the bottom half of the plane are all of the events in the past that might possibly influence our event. Now, when you think about this, you realize that it would be helpful to define something called the space-time interval, call it S, as s squared equals negative t squared plus x squared plus y squared plus z squared. Now, of course, because we're focusing on the xt plane, For now, we can go ahead and ignore y and z. Now, when you look at the equation shown here, this is the equation for the Minkowski spacetime interval. And you can see that it's very similar to the Pythagorean theorem, or like the distance formula, in four-dimensional spacetime. But with a very important difference that there's a minus sign on the term involving time. And that sign difference between time and space is known as the Lorentzian signature. Now, by the way, we could switch it around. We could have defined our interval so that time is positive and the spatial terms have minus signs. And that's called the mostly minus metric. And in fact, in previous videos, I've used the mostly minus metric. So today we're using the mostly plus metric. And I think mostly minus is convenient for doing particle physics. But when you're doing general relativity, mostly plus kind of feels a little bit better. At the end of the day, it doesn't matter at all whether we define our interval with mostly minus or mostly plus. All that matters is that there's different signs on the time term and the space terms. The reason that sign difference matters is because then we find that there's a quantitative difference between intervals that are within the light cone and outside of the light cone. So you can see with the definition of our spacetime interval here, if you have a point inside the light cone, then relative to our event, it's going to be more time-like separated. So the negative time squared term is going to dominate over the positive x squared term. And so every point inside the light cone is going to have a spacetime interval squared that is negative. And then conversely, relative to our event at the origin, any point that is outside the light cone is going to have a more dominant positive x squared term. And so then you see that the interval between our event and all of the space-like separated events is going to have a positive s squared. Then if you think about all the points that are right on the light cone, where the space and time are perfectly balanced, well, because the minus and the plus cancel out, you see there that all the points on the light cone are separated from our event by a space-time interval of 0. And so such intervals are light-like, also known as null. And the word null refers to the fact that the space-time interval is 0. So when you think about the space-time interval, you can kind of imagine it as sort of like a distance, but it's not really purely distance. It's actually something more generic, and it's something that is not strictly positive, but rather its sign actually encodes whether the vector is time-like or space-like. Now, if we go ahead and imagine another spatial dimension, so now we're thinking about events in the xy plane, with the time dimension perpendicular to the xy plane, you can see that the light cone looks like a cone, and that's why they call it the light cone. So the way to imagine this version of the light cone is that you're living in the xy plane, and at some moment you're going to shine laser beams in a circle all around you, and then you imagine that circle of light growing and growing and growing, and then think about extruding that a long time and think about how it would look, and you realize you end up with a cone like what's shown here. So then from there, if we go ahead and pull in the third dimension, so now we have x, y, and z, and you imagine the same kind of thing, where now you shine a sphere of laser beams in all directions, you can imagine a bubble of light, like a sphere that's expanding and expanding, and even though I don't have a plot of it shown here, because that's kind of a hard thing to plot, you can imagine that in reality, in the full 3+1 dimensional picture, the light cone is a bubble of light expanding and expanding and expanding, like a perfect sphere increasing linearly in time. And it's also the opposite of that from the past. So from the past, it's like a sphere that's shrinking and shrinking and shrinking until it has a volume of 0 right at our event. Alright then, the light cone concept is not that strange, kinda makes sense, but here's where relativity gets kinda weird. Imagine that you and your friend are floating through space along the x-axis, and both of you are at a constant speed. And imagine you're coming at each other and you're going to do a high five. But then it's a near miss and you don't quite get the high five, and so then you both go floating on in opposite directions. So how can we imagine this scenario in a space-time diagram? Well, suppose we let the x-axis increase along the direction that your friend is floating away from you. So your friend is moving along the positive x direction, from your point of view. And let's say from your point of view, you're not moving along x. Even if you are moving, you can say, look, relative to my inertial frame of reference, I'm not accelerating, and so you may as well consider yourself at rest. So then if you think about your trajectory in spacetime, well, you're not moving. You're staying at x equals 0 as time goes on. So from your point of view, your trajectory in spacetime is going to be a boring vertical line, whereas your friend is going to be moving along this exciting tilted line, where the angle of the tilted line represents their speed. And here I've also gone ahead and included the light cone lines, and as you can see from the diagram, the moment of your attempted high five, we're going to call that x equals 0 and t equals 0, and so I've gone ahead and color-coded the spacetime in terms of time-like, light-like, and space-like. So those yellow lines represent the speed of light, the light cone. Now as you can see by the angle of your friend's tilted line, your friend is going pretty fast. They're going a good fraction of the speed of light, because for the purpose of this thought experiment, we want to see the relativistic nature of spacetime, and so it's important that your friend be moving at a relativistic speed. Now in reality, of course, you never want to attempt a relativistic high five. The fastest high five I ever did was 40 miles an hour, and that hurt, so I wouldn't recommend. We didn't factor in relativity, though. Even at 40 miles an hour, you don't have to factor that in. We were just thinking about, dude, this is going to be sick. But anyway, today we do want to think about relativity. So imagine how the high five attempt looks from your friend's point of view. Well, in their reference frame, they're not moving. Their path through spacetime is a boring vertical line. And they see you moving along this tilted line that's going along the negative x direction as time goes forward. Now, at first glance, this concept does not seem too mysterious or weird. It actually just kind of makes sense if you think about it. Of course, you see your friend moving forward along x, and so from their point of view, they see you moving backwards along x. It makes perfect sense. This is the concept of Galilean relativity, which has been known about for centuries and centuries. But then when Einstein came along and taught us about special relativity, that's a whole different thing, and the reason is that special relativity tells us that the speed of light is going to be the same in all inertial reference frames, which is to say that both you and your friend see the same speed of light in both of your reference frames. And at first glance, that seems absurd. You're like, what? How can that be? This is like saying if at the moment you attempted the high five, you both shined some laser beams forward and backwards along x, and somehow, for both of you, as you go on past the high five, you're both going to see those beams of light moving at the same speed. But that defies common sense notions of how speed works. Because, for example, you would think if you shine a light and you're moving in the direction of that beam of light, it should appear slower than the speed of light, right? But no matter how fast you're moving, the speed of light's always the speed of light. It's really a trippy thing to think about. But then the question becomes, how can we reconcile this notion of the speed of light being constant for everyone with this idea of a space-time diagram? How can it be that we can hop from your point of view into your friend's point of view and vice versa, and have this all make sense and not be incoherent? Because the light cone is not allowed to tilt. Well, here's the thing. When you think about the fact that to hop from your point of view into your friend's point of view, or vice versa, you and your friend's world lines are going to have to tilt as you're boosting from one reference frame to another, but special relativity requires the light cone not to tilt. And so if those two things are both going to be true at the same time, then necessarily you and your friend are going to have to disagree on what exactly is going on in space and time. So when you hop from your point of view to your friend's, space and time are going to sort of re-coordinate each other such that the speed of light remains constant, whether you're looking at it from your point of view or your friend's point of view. Now this is a very trippy concept, and so in order to see it, let's go ahead and sprinkle in some events into the xt plane. Now the point of this sprinkling of events is to give us some dots in the plane so that we can see that when you hop from one reference frame into another, space and time distort in a way that tilts you into your friend's point of view without tilting the light cone. But it's worth thinking about what exactly do these event sprinkles correspond to? Like, what are we actually looking at here? Well, these are just going to be little blips in spacetime. So imagine you have an x-axis, and then as time evolves, there's little blips here and there at different places along x and at different times. Oh, you know what? Here's a good way to think about it. So remember those little rubber dome things where you press it and then you put it on the table and then at some unknown time it pops up and it's kind of startling? Well, imagine we line up a bunch of those along our x-axis, and then each one pops off at a different time, and then the time and place of the pop is what we're recording here with our points on the space-time plane. So these dots are just a way of sprinkling the plane with some specific events, so we can get a sense of how space-time transforms as we boost from your reference frame into your friend's reference frame, and vice versa. And by the way, when you hop from one inertial frame to another, that's called a Lorentz boost. And here's the mathematical details of how that works. But never mind those for now. I don't want to get into the algebra. I want to stay focused on the picture. So for now, let's keep things flowing and let's let this evolve and go back and forth between these two different reference frames. And in the animation shown here, you have to keep in mind, the movement in this animation is a movement of our perspective. It doesn't correspond to motion in reality. So you ever seen how a praying mantis looks back and forth to get a sense of depth perception? Imagine we're doing the same thing here. We're moving our head back and forth with this like God's eye view of the xt plane, and thinking about how this sprinkling of space-time events changes depending on which inertial reference frame we take as our point of view. This mental exercise can give us a good feel for some of the weirder aspects of special relativity. For example, let's hang out in your point of view for a moment. Now, from your point of view, you're not moving along x, and so you just flow forward in time along a vertical line. Likewise, then, at the moment of the attempted high five, if you think about all of the events that you would consider to be simultaneous with that high five, that is, if you think about your now slice, so to speak, then that would simply be a horizontal line in the xt plane, by definition, right? But then if you boost into your friend's point of view, notice that your now slice necessarily tilts. And so at the moment of the high five, when you and your friend are right there at the same time, same place, the set of all space-time events that you consider to be in the present moment is actually different than the set of space-time events that your friend considers to be in the present moment. That is to say, simultaneity is relative. Now, you and your friend are both going to be present at x equals 0, at t equals 0, and so you'll agree that right there, right then is the same now. But if you ask your friend, hey, what's going on over there right now, some distance away, they're going to disagree with you about what is happening in the present moment. So one of the bizarre consequences of the speed of light being the same for everyone is that simultaneity is relative, and there's no such thing as an objective now slice. And that's why special relativity sometimes prompts a hippie to say something like, oh man, space and time, it's all relative, dude. Like, whoa, man, what a trip. But here's the thing. Even though space and time are individually relative to some extent, amazingly, the space-time interval is not relative. That's something that all inertial observers can agree on. And so relativity is relative, but it's not like totally relative. It's just an expansion of the way we usually think about space and time. Notice, by the way, that this relativistic picture aligns with common sense, because in everyday life, we deal with things that are going very, very slow relative to the speed of light. And so, in practice, when you hop from your point of view into the point of view of someone going by real fast, like on an airplane or something, well, even then, you're talking about going from a vertical line to basically a vertical line that's tilted a tiny little bit, but this transformation, this Lorentz boost, really doesn't change space and time that much. And so, in everyday life, relativistic effects are negligible. Oh, you know what? While we're here, let me show you something. So imagine that as we're hopping back and forth between reference frames, we consider the sprinkling of events in space-time, and we let each one leave a little trail. Now remember, the motion we're looking at here isn't actually motion in reality. But no, this is just the way that our sprinkling of space-time events is going to transform as we transform our reference frame. And then you'll notice, if you look at this, that all of the events are going to trace out these hyperbolic curves as we take on different points of view. And when you think about the fact that we need to be able to hop into different inertial frames, and at the same time we can't allow the light cone to tilt, then you realize that these hyperbolic curves are exactly the way that we need our events in spacetime to transform in order for relativity to work and for the speed of light to be constant for everyone. Now then consider our definition of the Minkowski spacetime interval. S squared equals negative t squared plus x squared. And remember, just a moment ago, I claimed that even though different observers will disagree on space and time individually, everyone agrees on the space-time interval between two events. And you can see that that is true, because if we impose on all of our events that the space-time interval between our high five and every other event has to be constant, then the equation becomes negative t squared plus x squared is constant. And that is the equation of a hyperbola. So the statement that every inertial observer agrees on the space-time interval between two events can be seen in the way that our sprinkling of events moves along these hyperbolic curves as we shift our perspective between reference frames. And that's something worth meditating on because that is the essence of special relativity. All right, now I want to make one last comment before we move on from this picture, and that is to say, when we're dealing with special relativity and Minkowski spacetime, we call this flat spacetime. Now the word flat spacetime, it means the whole four-dimensional picture, so x, y, z, and t. And flat spacetime also includes this relativistic picture with the Lorentz Boosts and time dilation and length contraction and all of that. So when you hear flat spacetime, don't think about like a two-dimensional thing. No, that is the arena in which special relativity lives. The reason I bring up flat spacetime is because in general relativity, spacetime gets curvy, and then we're dealing with curved spacetime. But like, what even is curved spacetime? What a strange concept. Well, the question of what is curved spacetime doesn't exactly have an easy answer, though it does have a simple answer. Curved spacetime is a spacetime for which the metric deviates from the Minkowski metric. But what does that mean? And how should we visualize it, and what kind of mathematical tools can we use to do calculations in a curved spacetime? Well, as you can imagine, there's a lot of math when it comes to curved spacetime. And actually, first of all, let's be fancy and we'll call it Lorentzian spacetime. Lorentzian spacetime is a generalization of Minkowski spacetime, where the metric tensor is able to vary from one place to another, and so the notion of a spacetime interval is going to deviate from the Minkowski spacetime interval. So first of all, the most basic ingredient of Lorentzian spacetime is the concept of a four-vector. We'll call it V. And in this video, we're going to use abstract index notation, which is where, to denote that something is a vector, we put an upstairs A or a B or a C next to the letter that is the name of the vector. And the way to think about that is V upstairs A is notational shorthand for a vector which contains four scalar components, v0, v1, v2, and v3. Now when we use this so-called abstract index notation, we are not committing ourselves yet to a particular coordinate system. However, it's often simple to think of the vector in terms of having a time component, an x component, a y component, and a z component. But you could imagine using a different coordinate system instead, like for example spherical coordinates. In any case, when you see v upstairs A, think of that as a vector that exists independently of the coordinate system that we use to describe it. Oh, and then just a notational thing. If we are thinking about this four-vector as having a time component and three spatial components, we'll often write the time component as v upstairs t, and the spatial component as v with an arrow. Or, equivalently, v with an upstairs I, where the I stands for only the spatial indices, so only x, y, and z. Alright then, so our next ingredient is the metric tensor, which we'll write g downstairs ab. You can think of the metric tensor as encoding the way that the space-time interval depends on the various dimensions of space and time. So when we're dealing with flat spacetime, that is Minkowski spacetime, and suppose we're working in Cartesian coordinates, t, x, y, and z, then you can think of the Minkowski metric as just the simple matrix shown here, which is essentially the 4x4 identity matrix, but with a minus sign on the time component. And the Minkowski metric we typically write as eta downstairs AB. Now, in general relativity, when we're dealing with Lorentzian spacetime, which is able to get curvy, then in general, the metric g is going to differ from the Minkowski metric eta in accordance with the Einstein field equations, which we'll talk about in just a moment. Those are the equations which tell us how matter and energy curve spacetime. But, something that's nice is that when you're dealing with curved spacetime, very often you have asymptotic flatness. Now, asymptotic flatness, it doesn't mean you haven't been doing your squats. It means that far away at spatial infinity, you go way out there in space, then your metric is going to approach the Minkowski metric. So, for example, we'll see that throughout this paper. When we're thinking about a black hole and some matter around a black hole, in the vicinity of the black hole and the matter, you're going to have some curvature, and our metric is not going to be the Minkowski metric. However, if you hop in a spaceship and go super far away from the black hole, then way out there, the black hole's influence in curving the spacetime is going to drop off, and the metric is going to approach the flat Minkowski metric. Also, the metric tensor has an evil twin, known as the inverse metric. The inverse metric we write as a G with two upstairs indices. Now, sometimes I call the inverse metric the upstairs metric, and I do that a few times in this video, and I apologize because that is kind of a sloppy way of saying it. I really should be more proper and call it the inverse metric. But when you're doing tensor calculus, you're dealing with these objects that can have upstairs indices or downstairs indices. And so anyway, oftentimes I call the inverse metric the upstairs metric. Now, the defining property of the inverse metric is that it's the inverse of the metric, in the sense that if you contract the metric with the inverse metric, such that you have G downstairs AB, G upstairs BC, that gives you a Kronecker delta with the indices A and C. Kronecker delta, all that means is it's the number 1 if the A and C indices are the same, or it's a 0 otherwise. So you can think of the Kronecker delta as the identity matrix. Alright then, so we've been talking about upstairs and downstairs indices, and I think right now it's a good time to say what exactly is the difference between an upstairs index and a downstairs index, because this is actually a really concise and important notational convention. So just now we've seen that we can write a vector as v upstairs A, but on the other hand, if you see a v downstairs A, that's a covector. The definition of a covector is that it's a vector contracted with the metric tensor. That is to say, the covector VA is defined as the metric tensor G downstairs AB contracted with V upstairs B. Now in this equation, we're using the Einstein summation convention in which repeated indices are summed over. So think of this equation as GA0 V0 plus GA1 V1 plus GA2 V2 plus GA3 V3. Or, actually probably a better way to think about it, is that the covector V downstairs A is the matrix product of our metric tensor with our upstairs vector VA. So to turn a vector into its corresponding covector, you simply slap on the metric. And also, when you see an equation like this, G downstairs AB, V upstairs B, if you look at that repeated B index, you have a downstairs B and an upstairs B. And when you're summing over B, you can think about how a downstairs and an upstairs combine together, and that index then goes away in the sum. And then you see on both sides of the equation, you have a downstairs A on the V, and also a downstairs A on the G. So everything balances out as far as the index locations. Oh, and also, when we turn a vector into a covector, this is often called lowering the index, because the vector has an upstairs index and the covector has a downstairs index, so we use the metric to lower the index. Conversely, we can use the inverse metric, that is the upstairs metric, so to speak, in order to raise an index and turn a covector into a vector. Now all this talk about vectors and covectors, in Minkowski spacetime it's very simple. To turn a vector into a covector, you just put a minus sign on the time component. And that's because the Minkowski metric is so simple, it's -1, 1, 1, 1. But in a more generic, curved Lorentzian spacetime, the metric is not going to be so simple, and so in general, the relationship between a vector and its corresponding covector is going to be a little more complicated. But no matter how curvy spacetime gets, you can always make a covector simply by slapping the metric onto a vector. So okay, but what's the deal with covectors? Why do we care about covectors? What are these used for? Why do these matter? Well, once we have a notion of vectors and covectors, we can define the inner product in curved spacetime. Now, the inner product is essentially the dot product. It's a thing where you smush a covector and a vector together, and you end up getting a scalar that behaves in many ways like a dot product. Although it's a little more complicated because we're dealing with Lorentzian spacetime, and so the Lorentzian inner product is going to be affected by the metric. You see, because fundamentally we can define the inner product of two vectors v and w as the covector version of v contracted with the vector upstairs version of w. So we have v downstairs a, w a. This expression is shorthand for v0, w0 plus v1, w1 plus ... And so to take the inner product of two vectors, you just convert one into a covector and then slap it onto the other. But if you want to think about everything purely in terms of vectors, then instead of writing v downstairs a, that is the covector, you can always just write its definition as the metric g downstairs ab contracted with the vector v upstairs b. And here you can see how the inner product is sort of like a dot product, but it's affected by the details of the metric. Throughout this paper, the inner product is used quite often, and so we'll become very familiar with it. But there's one particularly important way in which we use the Lorentzian inner product, which is to calculate the Lorentzian norm squared of a four-vector. So in Lorentzian spacetime, we have this notion of a Lorentzian norm, which is in a way sort of like the magnitude squared of a four-vector. But it's not strictly positive. If the norm squared is positive, then we say that v is a space-like vector. Because remember before, when we were looking at the light cone, we saw that a positive spacetime interval squared corresponds to events that are space-like separated, that is, outside of each other's light cone. Likewise then, if the Lorentzian norm squared is 0, then v is a light-like vector, that is a null vector. It's a vector that points along the light cone. And then finally, if the Lorentzian norm squared is negative, then v is a time-like vector. That is, if you imagine it pointing from one event in spacetime to another, those two events are within each other's light cone. So they're time-like separated. Alright, so having talked about some of the basic ingredients of Lorentzian spacetime, now we're ready to start thinking about derivatives and curvature. So first of all, we have this notion of a partial derivative. And if you've ever done multivariate calculus, then you're familiar with the partial derivative. The partial derivative is just the good old rate of change of a quantity with respect to one coordinate, holding all the other coordinates fixed. So if you have some function, you can say, how does this function change as you move along the x direction? That's going to be the partial derivative along x. Or you could take a partial derivative along y, or z, or time. So suppose you have a four-vector field in 4 dimensions, and then because you're in 4 dimensions, you have 4 different dimensions along which to take the partial derivative. And so if we use our abstract index notation, we can imagine the partial derivative of all possible components of the 4-vector field v along all the 4 dimensions of spacetime as partial VA, partial XB, where both A and B are spacetime indices. Now, if you've ever worked with partial derivatives, you know it can take a lot of work to write partial V, partial X with the horizontal line. I mean, your hand gets tired. So another way we can write this is with comma notation. You see, in comma notation, we simply write our 4-vector, V upstairs A, and then we put a downstairs comma B. And by definition, that means the partial derivative of VA with respect to the B direction in spacetime. And also, earlier we were talking about vectors and covectors, and so you can also imagine the partial derivative of a covector, written in a very compact form, V downstairs A, right, for the covector V, comma, B, where the comma indicates partial differentiation along the B spacetime direction. The partial derivative is like one of the most fundamental concepts in calculus. However, when you're dealing with a curved spacetime, the partial derivative has a fatal flaw, which is that it's not a tensor. That is to say, the partial derivative is not a geometrically meaningful operation in curved spacetime. And the reason is, if you're in flat spacetime, it makes sense to talk about the partial derivative along the x direction. But if you're in curved spacetime, where things get curvy and weird, then what do you even mean by the x direction? Because you go along x and space is all warped and curved, And now what even, are you still going along x? Has x curved? Like what? Huh? So how do you take a partial derivative when space-time itself is curvy? Well, as you can imagine, the solution to this is going to be to define some kind of quantity or something that tracks how our space-time coordinates transform from one place to another. Because if we knew that, if we knew how the coordinates transform as we move along in curved space-time, then we could factor in those changes to the concept of a derivative, and we could upgrade the partial derivative into a so-called covariant derivative, which is a true tensor. So that's the idea. So to that end, we can define something known as the Christoffel symbols, whose definition is shown here. The Christoffel symbols encode how our coordinate basis vectors change from point to point in curved spacetime. So if you find yourself in curved spacetime, and you're moving along, and our coordinate basis vectors are changing and distorting as we go along, the Christoffel symbols give us a quantitative handle on how those coordinate basis vectors are changing. Now, in the interest of time, I'm not going to derive where this equation comes from, but you can see Poisson equation 1.11 and chapter 1 in general for a really good introduction to the Christoffel symbols and all of these derivatives and curvature concepts. But for now, I just want to think about the Christoffel symbols at the level of what they are, not necessarily the details of how exactly they work. And besides, we'll come back to these details later on in the video anyway. But one comment real quick is that if you look in the definition of the Christoffel symbols, you see that we have all of these terms that depend on the partial derivative of the metric. So without even going into the details, you can just think about the fact that, oh, okay, the Christoffel symbols have something to do with the way the metric tensor changes as we move around in spacetime. So the Christoffel symbols are not a fundamentally new thing. If we already have the notion of a metric tensor, as well as a partial derivative, then the Christoffel symbols are made out of those ingredients. And they're just a shorthand way for encoding this particular expression, which turns out to be very useful for a wide variety of calculations. Most famously, the Christoffel symbols appear in the definition of the covariant derivative. So the covariant derivative is like a partial derivative, but it accounts for the spacetime curvature via the Christoffel symbols, and therefore the covariant derivative is genuinely a true tensor even in curved spacetime. So this is a real geometric object with real physical meaning. So for the covariant derivative, we're going to use a semicolon notation. The semicolon notation is exactly the same as the comma notation we saw before for the partial derivative, but the semicolon indicates that we're dealing with a covariant derivative. And so when you see v upstairs a downstairs semicolon b, by definition, that means the partial derivative of VA along the b direction in spacetime, plus this expression involving the Christoffel symbols and the vector. You can see Poisson equation 1.5 for more information about where this definition comes from and why it's how it is. And then likewise, you can see Poisson equation 1.8 for the definition of how to take the covariant derivative of the covector v downstairs a. You know, one thing that's kind of neat about this semicolon notation, it's so concise and easy to write, and your hand doesn't get tired. But also, notice that a semicolon is like an upgraded comma, because a semicolon, it's a comma plus a dot. And if you look at the definition of the covariant derivative, we have a partial derivative plus another thing. So it's sort of like the dot in the semicolon represents that term with the Christoffel symbols. You know what I mean? So I really like the semicolon notation. I think it's neat. All right then, so now we have a notion of a covariant derivative, which is a derivative that's a true tensor, even in curved spacetime. And now we can use this concept of a covariant derivative to define something known as the Riemann curvature tensor. So the equation shown here is the defining equation of the Riemann curvature tensor. On the left side, we have second derivatives made out of the covariant derivative, because when we have a semicolon followed by two indices, that is a concise notation for a second derivative. So you can think of semicolon CD as the partial derivative along the D index of the partial derivative along the C index of the vector VA. So then in our defining equation of the Riemann curvature tensor, Poisson equation 1.31, we have the second derivative of the vector field V minus the second derivative of the same vector field v, but with the two spacetime indices swapped around. Now in flat spacetime, such an expression would always be zero, because as you learn in calculus, when you take a second derivative, the order doesn't matter, whether you take the derivative along x and then the derivative along y, or the derivative along y and then the derivative along x, those are the same, right? Well, in flat spacetime, yes, they're the same. But in curved spacetime, they're not the same. And so in flat spacetime, this equation is zero, and therefore our Riemann curvature tensor R is zero. But in curved spacetime, when the expression on the left is non-zero, then neither is the expression on the right. And so therefore our Riemann curvature tensor, which we write as R upstairs A, downstairs BCD, is non-zero. Now the Riemann curvature tensor has 4 indices. It is a rank 4 tensor. And it has to be, because by definition, the Riemann curvature tensor encodes how much second derivatives do not commute. And so first of all, you think about how many different options there are for taking second derivatives. Well, that's given by the C and the D indices. And then you realize there's 2 other indices when you think about which component of the 4 vector you're taking the derivative of, and how much the failure to commute projects onto which other component of the 4 vector. So all that's to say, our Riemann curvature tensor is a rank 4 tensor. Naively, a rank 4 tensor in 4-dimensional spacetime would have 4 to the 4th power components, that is, a whopping 256 components. But when you think about the symmetries and the antisymmetries in this definition, you realize that fortunately there's actually only 20 independent components of the Riemann curvature tensor, because we have antisymmetry under the exchange of A and B. We also have antisymmetry under the exchange of C and D. We have a pair symmetry, where swapping the pairs AB with CD doesn't change anything. And then we also have something known as the first Bianchi identity, which has to do with cyclic permutations of the indices. And so all of those symmetry conditions boil down the 256 components of the Riemann curvature tensor into just 20 independent components. Now, I don't know about you, but when I hear that a tensor has 20 independent components, I think to myself, gee, I wish I didn't have to deal with that tensor. Make it go away, please, I don't want it. Well, fortunately, there is another curvature tensor, known as the Ricci curvature tensor, and this you can think of as a dimensionally compressed or a boiled down version of the Riemann curvature tensor. That is to say, you have your rank 4 Riemann curvature tensor, and then you're going to pick out some particular spacetime directions A and B, you're going to hold those fixed, and then for each of those 16 options for A and B, you're going to put those A and B as the second and the 4th indices on the Riemann curvature tensor, and then you're going to sum, like taking a trace, over all of the components with those A and B that have the same first and third indices. So all that's to say, the Ricci curvature tensor is a contraction of the Riemann tensor, where we take the trace over one pair of indices and thereby collapse some of the directional information of the Riemann tensor. So then you see that the Ricci curvature tensor is rank 2, therefore it only has 16 components. But it also has symmetry in that RAB is equal to RBA, and so the 16 components are actually only 10 independent components. You have 4 components along the diagonal, and then on the off-diagonal, you have 6 ways. And 4 plus 6 is equal to 10. So the Ricci curvature tensor has half of the number of independent degrees of freedom as the Riemann tensor. And 10 is still a lot, but it's like, all right, well, whatever, we can deal with that. It's okay. So now what does the Ricci curvature tensor mean? Well, it tells us something about how a small ball of test particles gets squeezed or expanded as it floats through our curved spacetime. Hey, if anyone's watching this who is an engineer, have you ever had this experience where management comes to you and they're like, hey, we need you to put a number on this quantity for the board meeting or whatever. And you're like, well, that's not really a scalar quantity. It's more of like a vector or a tensor. There's some nuance here. And the manager's like, look, we just need a number for the investors, so make it a scalar. And you're like, oh, geez, okay, well, I'll define some kind of way of boiling this down into a scalar. Well, you can imagine that we might want to do something similar for the concept of curvature. And so this is the concept of the scalar curvature. So if you find yourself in a curved spacetime, you might want to have a scalar field that just tells you something about what is the strength of the curvature at each point in spacetime. Well, a good way to calculate that is to just take the trace of the Ricci curvature tensor. You often see this written as R upstairs A downstairs A, which, if you want to write this out explicitly, is going to be a sum over the product of the inverse metric with all the possible components of the Ricci curvature tensor. So in this equation, A and B are both repeated, and so imagine summing this G times R expression over all possibilities for A and B. So in other words, we're boiling down the Ricci curvature tensor into a single number at each point in spacetime. So essentially, the scalar curvature just tells us how much curvature do we have, and is it positive or negative, but it doesn't give us any directional information. Alright then, that brings us to the last and the most important curvature tensor that I want to talk about today, and that is the Einstein curvature tensor. Now all the Einstein tensor is the Ricci tensor minus half of the scalar curvature times the metric. Now the reason we take this particular combination is because this is the unique, symmetric, divergence-free second-rank tensor built from the metric and its first and second derivatives. The fact that the Einstein curvature tensor is divergence-free is what lets it play such a fundamental role in the Einstein field equations, which we're going to talk about next. But long story short, if you neglect the expansion of spacetime at very large scales, and just think about the relationship between matter and energy and spacetime curvature, then you'll find that by the conservation of energy and momentum, you'll want to have a curvature tensor that is divergence-free. Now I know there's a lot here, and if you're seeing all this for the first time, it can be a bit overwhelming, but you don't have to know everything about all these things all at once, because as we return to these concepts throughout the video, and as we use them and see how they work, it's totally okay to use that as the way that you learn about these concepts. So you don't have to be an expert right from the start. In fact, no one is, that's not a thing. Expertise is often proportional to the integral of confusion across time. So don't give up. But anyway, one final comment I want to make before moving on from this section is, if you think about it, you'll notice that all of these concepts here can all be defined simply in terms of partial derivatives and the metric. And so the Christoffel symbols, the covariant derivative, the Riemann curvature, the Ricci curvature, the scalar curvature, the Einstein curvature, all of these ideas can be traced back to the idea of a partial derivative and the metric tensor. Well, alright then, so now let's go ahead and see what the big deal is with the Einstein curvature tensor. Alright, my friends, now it's time to talk about the centerpiece of general relativity, that is, the Einstein field equations. So you may have heard this famous quote from John Archibald Wheeler, which is that spacetime tells matter how to move, and matter tells spacetime how to curve. But what exactly does that mean? How does matter tell spacetime how to curve? We need an equation for that, right? Well, here's the equation. First of all, the ingredients of this equation are the Einstein tensor, which we talked about earlier. The Einstein tensor encodes the curvature of spacetime. Then we have the cosmological constant, lambda, which is a super, super tiny number. It's almost zero. In fact, for everything that follows today, we're going to use the approximation that lambda equals 0, and we're going to delete this term involving lambda and the metric tensor g. But before we delete it, I'll just say a few words in passing about it. So the cosmological constant is what sets the rate of the expansion of the universe. And if you're thinking about the whole universe, like on an intergalactic scale, you can see that it is expanding, and the rate at which that's happening is ultimately tied to lambda. However, if you're thinking about things on the scale of a solar system or even a galaxy, the expansion of spacetime is really not relevant, because even at a galactic scale, the expansion of spacetime is just a very weak effect, and so we can ignore it. So then all we have left in our Einstein field equations is the Einstein tensor on the left side, and then on the right side we have 8 pi times something known as the stress-energy tensor, which we'll talk about in just a moment. The stress-energy tensor encodes the distribution of matter and momentum and pressure in spacetime. And so in other words, when we say that matter tells spacetime how to curve, what we mean is that the stress-energy tensor, T, is proportional to the Einstein tensor, G. Oh, and just a comment about units. In SI units, this 8 pi would actually be 8 pi times the gravitational constant g divided by the speed of light to the 4th power. But today, we'll be using geometric units, which are very convenient for general relativity. And in this system of units, both big G and the speed of light, c, are equal to 1. And so in our Einstein field equations, we simply have an 8 pi. Oh, and also, you might be wondering, why do we call this the Einstein field equations, plural? It's just one equation, right? Well, bear in mind, we're dealing with a couple of rank 2 tensors here. And so this equation can be broken up into components and written as a bunch of coupled partial differential equations. And so that's why we call them the Einstein field equations. For today, we're actually not going to have to unpack the Einstein field equations. We're going to keep everything at the level of the Einstein tensor and the stress-energy tensor. And we're just going to use the Einstein field equations a few times to convert back and forth between G and T, depending on the context and what we're trying to derive. All right, then, so let me say a few words about the stress-energy tensor. The definition of the stress-energy tensor, TAB, also known as the energy-momentum tensor, is that it encodes the flux of the A component of 4 momentum across a hypersurface of constant xb. Now it's like, hey, hold on now, what does that mean? Well, 4 momentum, just think of that as a 4-vector which combines energy and momentum, and then xb, just think about that as time and space. And so T is a tensor that encodes energy density, energy flux, momentum density, and spatial stresses, that is, pressure and shear, in one convenient package. So for the sake of becoming familiar with this tensor, imagine that we're dealing with Minkowski spacetime and Cartesian coordinates. So just think about spacetime as t, x, y, and z. Well then, you can think about the stress-energy tensor as this matrix, with energy density, energy flux, momentum density, pressure, and shear. Or if you want to be fancy, you can write it with some symbols like so. So why is this the case? Well, first of all, look at energy density for the 0, 0 index. The 0 component of 4 momentum is energy, and the 0th component of the 4-vector x is time. So think about the flux of energy across time. Well, that's just going to be how much energy is there somewhere that's just right there experiencing the passage of time. In other words, that's energy density. Now look at those other terms on the top row, energy flux. Well, again, we have the 0 component of 4 momentum, so that's energy. But now we have the flux of that energy across the 3 dimensions of space. So we have the energy flux along x, the energy flux along y, and the energy flux along z. That is, if you have some point and there's some energy at that point, and you go a little bit along x, y, or z, how much flux is there in the energy as you move along in space? Now, if you go down the first column, you see we have momentum density. And that's because as we go down in the columns, we end up with the spatial components of 4 momentum, which is momentum, and we're taking the flux of that across the 0th component of x, so that's going to be time, and so that's going to give us 3 components of momentum density. Now, if you look at the pressure and shear terms, those on their own you can think of as the stress tensor. So if you've studied mechanical engineering, you've heard about the stress tensor. That's what that is. Now, in mechanical engineering, you think of stress as force per area, but in physics, we can also think about it as a momentum current. These things are equivalent because force is the time derivative of momentum. And so the purely spatial part of the stress-energy tensor encodes pressure and shear stress. Now, if this seems a bit abstract for now, that's okay. Later on, in equation 20, we'll see a specific example of a stress-energy tensor. But for now, the main thing to remember is that the Einstein field equations, when we neglect the cosmological constant, simply tells us that the Einstein tensor, which encodes spacetime curvature, is directly proportional to the stress-energy tensor. And all that's to say that matter tells spacetime how to curve. Now, I know this is all very abstract, so next I want to compare and contrast 3 very specific and very famous spacetimes: Minkowski spacetime, that is flat spacetime, as well as Schwarzschild spacetime, which is the spacetime around a non-rotating black hole, and also Kerr spacetime, which is the spacetime around a rotating black hole. So these will give us some specific and relevant examples of how spacetime gets curvy in general relativity. Alright, so first off, Minkowski spacetime. Let us cast our imagination into flat spacetime and imagine that we have 2 points that are very close to each other, so 2 events that are separated by a little amount in time, dt, a little step in the x direction, dx, and likewise for y and z. Well, now that you're an expert on the Minkowski metric, you know that there's going to be a tiny little spacetime interval, ds, between these 2 events, and we can calculate ds from the equation ds squared equals negative dt squared plus dx squared plus dy squared plus dz squared. So for the spatial part, it's the distance formula, and then we set that against the time interval part via the Lorentzian signature. So now suppose that we define the tiny little distance between these 2 nearby points in spacetime as the 4-vector dxa, whose components in Cartesian coordinates are dt, dx, dy, and dz. Well then, as we saw before, we can also write the spacetime interval squared as a metric sandwich with dx as the bread. Actually, previously I wrote this formula with the g on the left side and then the 2 vectors on the right, but everything here commutes, so that's all good. So if you want to think about the spacetime interval squared as a metric sandwich with dx bread, that's totally fine. Or, better yet, if you like simple formulas, we can define the covector, dx downstairs a, as the metric gab, contracted with the vector, dx upstairs b. So rather than the full sandwich, we define the covector as an open-faced metric sandwich, and then the vector, dx upstairs a, is another piece of bread that we slap onto that, thereby constructing the entire sandwich by simply contracting a vector and a covector. So that's all stuff that we've seen before, but now consider this. Suppose we write exactly the same vector, dxa, but with the spatial part written in spherical coordinates. So we're still going to use t for time, but rather than x, y, z, we're now going to use r, theta, and phi. So the definition of spherical coordinates is that r is the radial direction between the origin of our coordinate system and a point in space, theta is the angle coming down from the North Pole to that point in space, and phi is the azimuthal angle, that is the longitudinal angle in space. And so any point with an x, y, and z could also be written as r, theta, and phi. But now the question becomes, what is the spacetime interval when we're dealing with spherical coordinates? Well, in the equation for ds squared, we're still going to have a negative dt squared, because we're not messing around with time, but then the spatial part is given by dr squared plus r squared d omega squared, where d omega is the angular step that depends on the little tiny step in theta and also in phi. So if you like, that term r squared d omega squared, you could forget about d omega entirely and just write that as r squared times the quantity of d theta squared plus sine squared theta d phi squared. And this is pure geometry, because when it comes to the spatial part of the spacetime interval, this is purely the distance formula. It's like the Pythagorean theorem in 3 dimensions, you know? And so the question is, if you take a little tiny step in r, theta, and phi, what is the little tiny step in space that results from that? Well, if you take a step along r, that is a step in space, and so that's just going to contribute with the simple dr squared. But then if you take a step in the angle, and you want to know how much of a step in space do we get from taking a certain step in the angle, well, that depends on how far away you are from the origin of the coordinate system. If you're close to the origin, a step in the angle is a little step in distance. But if you're way far away from the origin, then the same step in the angle is going to give you a much bigger distance. And from the geometry of the arc of a circle, you can show that a small step in the angle omega is going to contribute to the ds squared formula as r squared d omega squared. Now then, thinking about this in terms of the metric tensor, GAB, we find the equation shown here, which is now to be interpreted in spherical coordinates. So in other words, you think about making a ds squared in terms of a metric sandwich with vector bread. Well, if your vector has components of dt, dr, d theta, and d phi, then the metric in the sandwich has to have the form shown here, so that on the d theta term we slap on an r squared, And on the d phi term, we slap on an r squared sine squared of theta. So as you can see, the definition of the metric tensor written here comes entirely and only from our equation for ds squared. But now there's a very important point that I want to make here, which is that these two metrics, the -1, 1, 1, 1, as well as the one with the more complicated diagonal, these are fundamentally both the Minkowski metric. It's just written in two different coordinate systems. So the metric itself you can think of as a real object. It's a real thing. It's a genuine tensor. But the way it's written in terms of its components might look different depending on what coordinate system we use. So there's actually no physical difference between these two metrics written here. But the way we've written the metric in spherical coordinates does give us an interesting insight as to the meaning of the metric tensor. And that is, the metric tensor encodes the way the space-time interval depends on little changes in our coordinates. And in the case of spherical coordinates, the components of the metric are going to vary as a function of r and theta, but that's not due to the curvature of spacetime, but rather that's due to the nature of spherical coordinates. However, when spacetime gets curvy, as we're about to see, then the components of the metric do change from place to place, but now in a way that doesn't just represent the shape of the coordinate system, but rather reflects actual curvature in the geometry of spacetime. And that brings us to perhaps the most famous example of a curved spacetime, Schwarzschild Spacetime. Schwarzschild spacetime describes the spacetime geometry around a non-rotating black hole that has no electric charge. Given the spherical symmetry of the situation, naturally we'll want to use spherical coordinates, which in this context are often called Schwarzschild coordinates. So in the presence of this black hole, space and time get curved in a way that's encoded in this formula for ds squared. We find that a tiny little space-time interval squared is going to be -f dt squared plus 1 over f dr squared plus r squared d omega squared, where f is a dimensionless factor, 1 minus 2m over r, where m is the mass of the black hole. Bear in mind, we're using geometric units, where mass and length have the same units. And also, you can see Poisson equation 2.3.7 for more information on where f comes from. So then, taking this formula for ds squared, we can do exactly what we did before and write our metric tensor, GAB, as the matrix shown here. Before we explore the properties of the Schwarzschild metric, I just want to make a historical comment. So the Schwarzschild metric was actually the very first solution to the Einstein field equations. Back in 1915, a scientist by the name of Karl Schwarzschild took the Einstein field equations and imagined a spacetime that was totally empty except for one single point mass. And at the time that Schwarzschild came up with the solution, he wasn't even thinking in terms of black holes. He was just thinking about the Einstein field equations and the relationship between matter and energy and the curvature of spacetime, and he was like, hey, wouldn't it be cool if we had an analytical closed-form solution for the spacetime geometry around a single point mass in an otherwise empty spacetime that's governed by the Einstein field equations. And so at the time, this was sort of a mathematical result. But as it turns out, the Schwarzschild metric is also exactly how we describe a non-rotating, non-electrically charged black hole. So there's the singularity, which you can think of as a point mass, and then there's the curvy, warped spacetime around it. So anyway, that's a bit of the history of where the Schwarzschild metric comes from. The Schwarzschild solution is actually somewhat complicated, so in the interest of time, we're not going to derive it here, but if you look up Schwarzschild solution to the Einstein field equations, you can read more about it. Oh, by the way, Schwarzschild figured this out while he was on the front lines of World War I. I guess he wanted a challenge. Anyway, let's go ahead and compare the Schwarzschild metric to the Minkowski metric in spherical coordinates. The first thing you'll notice right away is that these metrics are almost identical. In fact, if you look at the theta and the phi components, that is r squared and r squared sine theta, there's no difference at all whatsoever. And that tells us that even in Schwarzschild spacetime, where the black hole warps the spacetime, that warping does not have an effect on the way that changes in your latitude and longitude will change your spacetime interval, or for that matter, the distance in space between 2 points. So the only dimensions that get warped in Schwarzschild spacetime are time and the radial direction, because those components in the metric, instead of being -1 and 1, are now -f and 1 over f. Now, if you look at the definition of this factor f, you can see that as r approaches infinity, so as we go super far away from the black hole, the factor of -2m over r becomes smaller and smaller and smaller, approaching 0. And so when we are way out there in space, far away from the black hole, f approaches the number 1. And likewise, our metric approaches the Minkowski metric. So this is a specific and very clean example of asymptotic flatness. So what do we know so far? Well, we know that we have spherical symmetry. We know that moving in latitude and longitude isn't weird. We know that if we're far away from the black hole, then the Schwarzschild metric approaches the Minkowski metric. And another subtle point, but an important point, is that all of the off-diagonal terms of the Schwarzschild metric are 0. That is to say, when we look at the equation for ds squared, we only have terms with dt squared, dr squared, d theta squared, and d phi squared, but we don't have any terms that mix time and space or mix space and space. So that's nice. Now then, if we examine this factor f, we see that there are two values for r for which f is weird. The first and most obvious one is when r equals 0, f becomes undefined, because we're dividing by 0. That is to say, if we are right at the center of the singularity of the black hole, where the radial coordinate is 0, then the math breaks down. Space-time becomes infinitely sharp and curvy and weird, and it just doesn't make any sense. Presumably, some future theory of quantum gravity or something can tell us what's going on exactly at that infinitely sharp point, but for now, we can take Schwarzschild spacetime as a bit of an idealization anyway, and so we don't have to be too bothered by the fact that it has an infinitely sharp singularity at the center of the black hole. That singularity is sort of there from the start anyway. Now then, the second interesting radial coordinate is when r equals 2m, because at that point we have 1 minus 2m over 2m, which is 1 minus 1, which is 0. So then in our metric, we end up with a 0 and also a 1 over 0, so our metric becomes undefined. That's really weird. So what's going on there? Well, that radial distance away from the center of the black hole is the radius of the event horizon. So for a Schwarzschild black hole, the radius of the event horizon is twice the mass of the black hole in geometric units. Now the event horizon is the point of no return, where if you're on the event horizon, even if you're a beam of light pointing straight out trying to escape, you'll never be able to escape. So naturally, it makes sense that our metric gets a little weird at the event horizon. But how disturbed should we be by the fact that the radial term in our metric is divided by 0 on the event horizon? Well, actually not as disturbed as you might think. So even though there is an apparent singularity in this 1 over f term on the event horizon, this is actually a pathology of using Schwarzschild coordinates, that is spherical coordinates, to describe what's going on with a black hole. And this pathology is loosely similar to trying to describe the north or south pole of a sphere in spherical coordinates, where your longitude becomes undefined. But of course the geometry is different than that. Essentially, the way to think about it is from the perspective of an observer who's far away from the black hole. See, because the way to think about Schwarzschild coordinates is the time dimension t is time as measured by a clock that's super far away from the black hole. And then the radial dimension r is defined implicitly based on the circumference of a circle at that distance away from the black hole. So anyway, when you're thinking in terms of that notion of time and that notion of the radial direction, the metric tensor becomes pathological on the event horizon. However, that's not a real singularity in spacetime itself. And if you're interested, you can look into Eddington-Finkelstein coordinates for an example of a coordinate system which can describe a Schwarzschild black hole without encountering any mathematical singularities on the event horizon. But for the purposes of today's video, we don't have to get into Eddington-Finkelstein coordinates. I just mentioned that in passing, because if we restrict our attention to the space-time outside of the event horizon, even including the space right up next to the event horizon, then the Schwarzschild metric is totally fine for describing the geometry of that spacetime. So how can we think about the warped spacetime around a Schwarzschild black hole? Well, first of all, if you look at the time component of the metric, that negative f term, that directly governs how the square of the spacetime interval depends on the square of a little step in time. And so that f factor controls gravitational time dilation. Specifically, because ds squared depends on negative f dt squared, take a square root of those two things, and you see that the square root of f, that is the square root of 1 minus 2m over r, is our time dilation factor. And that's actually what this cool little animation indicates. So imagine that we sprinkle the spacetime all around a black hole with these beacons that pulse at a constant rate from their point of view. So all these little dots, think of that as a beacon that has a certain pulse rate, and every single beacon from its point of view has exactly the same pulse rate. Now, in order for these beacons to stay in place, you have to put a little rocket engine on each one so that it doesn't fall in gravitationally, but instead it can maintain a constant radial distance away from the black hole. So if you imagine that thought experiment, you can see how time dilation looks around a black hole. From the spherical symmetry of the situation, we can plot this through an equatorial slice of the black hole without any loss of generality. So imagine rotating this picture around. So that gives you some feel for gravitational time dilation around a black hole. Things that are closer to the event horizon are going to be slower and more redshifted from the point of view of an observer who's far away from the black hole. Hey, by the way, if you want to see how to make this animation using Python, please consider supporting my channel on Patreon. If you sign up on Tier 1, you'll have access to the Python code that makes this animation, as well as all the others, and also video note PDFs which contain equations and figures from this video. For a video like this, that PDF is going to be particularly helpful, I think, given all the equations and stuff. Also, if you're feeling especially generous and you sign up on Tier 2, then I'll put your name in the end credits of future videos, because these videos truly would not be possible without your support. Thank you all for allowing me to indulge my physics video obsession. This work is super fun, I love it so much. So that's time dilation, but then if you look at the factor of 1 over f in the radial part of the metric, you can see that radial distances are stretched compared to what they should be in flat spacetime as we step along the radial coordinate r. And that's because as f approaches 0 on the event horizon, 1 over f grows and grows and grows towards infinity. And so a little step in the radial direction has a huge effect on the spatial part of the spacetime interval if you're next to the event horizon. And because the distance depends on dr squared divided by f, then the stretch factor is going to be 1 over the square root of f, which blows up as we approach the horizon. That is to say, there's more space between a radial coordinate of 2.1 m and 2.2 m than there is between 100 m and 100.1 m, even though the coordinate separation along r is the same. Now this radial stretching is quite a trip, and it's really counterintuitive, but there is a way to imagine it, thanks to a little something called Flam's paraboloid. To imagine Flam's paraboloid, imagine the same equatorial slice that we've been looking at, and then introduce a fictitious dimension that only exists for the purpose of visualization.
Flam's paraboloid.
Imagine that you are a little ant walking on Flam's paraboloid. Then you see that as you get closer to the event horizon, the distance you walk along the paraboloid is bigger relative to your radial coordinate. So if you're an ant on Flam's paraboloid, you can figure out your radial coordinate by walking around in a circle of constant radius and then dividing by 2 pi. Right, so that's your radial coordinate. But then you can see, based on the way Flam's paraboloid is curved, that the distance you have to walk on the paraboloid to change your radial coordinate changes as you get closer to the black hole. So far away from the event horizon, in the asymptotic flatness, the paraboloid approaches a flat sheet. But as you get closer to the event horizon, there's more and more distortion, and so there's more space along the radial direction than you would expect. I mean, it's like, whoa, that's so cool. Now you have to be careful with Flam's paraboloid, because the third dimension here is a fictitious extension of the equatorial slice, which lets us embed this paraboloid into a mathematical space, thereby visualizing the radial stretching in Schwarzschild spacetime. But this picture only shows us the spatial stretching at one instant of time. It doesn't tell us about time dilation, it doesn't tell us about the dynamics of motion around a black hole, and the depth of the funnel here is not a physical direction that anything falls into, and this is also not a depiction of the gravity well. It's purely a depiction of the radial stretching in Schwarzschild spacetime. Alright, so now that we're experts on the Schwarzschild spacetime around a non-rotating black hole, let's go ahead and rotate the black hole. And that gives us something known as Kerr spacetime. Alright, so I just want to say a few words about the Kerr metric without getting too lost in the algebraic details. Because, as you can see, the equation for the spacetime interval in Kerr spacetime is pretty complicated. So I'll just say a few comments in passing, comparing and contrasting the Kerr metric to the Schwarzschild metric. So first of all, let's just go ahead and write everything out here. One thing that's nice about the Kerr metric is that this is actually a closed-form analytic solution to the Einstein field equations. And so if you spend some time with all of the algebraic details shown here, you can really get to know the geometry of the spacetime around a rotating black hole that has no electric charge. So without getting into all of these details, let me just point out a couple of things. Well, first of all, the most salient difference between the Kerr metric and the Schwarzschild metric is that the Kerr metric has non-zero off-diagonal terms. Because you see, there's a term that mixes dt and d phi. And you can see that too in the equation for ds squared. When you look at that term, d phi minus omega dt quantity squared, you can see in there that we're going to have a factor proportional to the product of d phi and dt. That is, around a rotating black hole, the spacetime interval is going to depend on the product of a step in longitude as well as a step in time. And that fact leads to the phenomenon of frame dragging, which is where the spacetime around a rotating black hole is actually dragged in the direction of the black hole's rotation. It's sort of like a spacetime whirlpool, very loosely speaking, of course. So this is a very surreal effect. And also, this effect drops off the farther away you are from the black hole. So if you go super, super far away from the black hole, your r-coordinate approaches infinity, and so therefore this quantity sigma over rho squared, whose definitions you can see there on the left, is going to approach 0. So as you go very far away from a rotating black hole, way out there, the frame-dragging effect drops off and goes away. And in fact, when you examine all of the algebraic details of the Kerr metric, you see that way out at spatial infinity, the metric converges to the Minkowski metric in spherical coordinates. That is to say, Kerr spacetime is asymptotically flat. Oh, and another thing is that if you look at the rho and sigma parameters, you see that those depend on the angle theta, that is the angle away from the North Pole. So that right there shows us that Kerr spacetime does not have spherical symmetry. Instead, it's only axisymmetric, around the axis of symmetry that goes between the North and South Pole. You can verify that it is indeed axisymmetric because the metric has no dependence on the longitude angle phi. So if you find yourself in the vicinity of a rotating black hole, if you change your latitude, you'll notice a change in the metric tensor. But if you change your longitude, then there's no change in the metric tensor. Oh, and one other thing I'll note in passing is that for a Kerr black hole, you have something known as the ergosphere. The ergosphere is a region outside of the event horizon where the frame-dragging effect is so strong that anything there is going to have to rotate around in the phi direction, whether it wants to or not. That is to say, in the ergosphere, if you want to just keep your longitude constant and not rotate, well, you'd have to move faster than the speed of light in order to do that, and so you can't do that. And so within the ergosphere, spacetime is getting dragged so strongly that everything in there is rotating along with the black hole. So just a bit of foreshadowing, when we get to equation 8, that's why there's a rotational component to the null vector that's tangent to the generators of the horizon. We'll talk about that in more depth later on. Well, alright then, so I hope that gives you a good sense of the metric tensor and a few different examples of how spacetime gets curvy. All right, but before we get back to the paper, I want to hop back into Minkowski spacetime for a moment and introduce to you the concept of a null dyad and then also a null tetrad. To understand what a null dyad is, imagine that we take a slice of spacetime that has time as well as one spatial dimension. So for example, the TZ plane. Well, naturally, when you think about the TZ plane, you imagine it being spanned by a unit vector in time and a unit vector in z. Which is to say that if you have some arbitrary event with coordinates given by the 4-vector x, then you can write that 4-vector as t, 0, 0, z, where t and z are how far along the event is along the time axis and the z-axis, respectively. So in other words, we can write the coordinates x as t times the time unit vector plus z times the z unit vector. And then when you think about the physical meaning of the coordinates x in the TZ plane, you realize, okay, we have one space and one time, so this 4-vector x corresponds to an event that's somewhere along the z-axis at some time t. But now I want to tell you about the concept of a null dyad, which is the idea of using a different set of basis vectors to span the TZ plane, where now each of our basis vectors is going to be light-like, also known as a null vector. So for example, consider the spacetime direction of a photon moving in the positive z direction. Let's call that vector L, and because we're using natural units where the speed of light is 1, we can see that L is just going to be the sum of the time unit vector and the z unit vector divided by a factor of 1 over root 2 to normalize it, and so we can write L as 1 over root 2, 0, 0, 1 over root 2. Now then, for our other null vector, let's imagine a photon that's going the other way, along the negative z direction. So that vector is going to be the same thing, but now with the minus sign on the z unit vector, because it's going the other way along z. So if we call this vector n, we can see that n is 1 over root 2, 0, 0, negative 1 over root 2. What's really cool about these vectors L and n is that they're light-like vectors. That is, the Lorentzian norm of L and n are both 0. And so each of these vectors is tangent to the light cone, where the spacetime interval between events is 0. You can imagine that in some contexts, using this basis set to span the TZ plane is going to be mathematically convenient. Oh, and by the way, why are we calling these L and n? Well, of course, we're calling it L because of light, because this is the spacetime direction of a beam of light, and then n stands for another beam of light. Now then, conventionally, we normalize n and L such that their inner product is -1. So suppose, for the sake of convenience, that we're considering Minkowski spacetime. Well then, to take the inner product, we simply multiply together the time components of each of these vectors, times the minus sign from the Minkowski metric, and then we add on to that the product of the z components of these vectors. And as you can see, that equals -1. Now then, as I mentioned before, this set of basis vectors, L and n, this null dyad, null because they're light-like, dyad because there's two of them, this can span the TZ plane. Because imagine we're looking at the same coordinates, x, that we were looking at earlier, that's some amount z along the z-axis, and some amount t along the time axis. Well, that same event is going to be some amount v along the l-axis, and some amount u along the n-axis. And if you work out the geometry of the coordinate transformation, you can see that u is equal to t minus z over root 2, and v is equal to t plus z over root 2. And all that's to say that the TZ plane, which we originally thought about in terms of one spatial dimension and one time dimension, can also be thought of in terms of two light-like directions. So that's a neat concept, isn't it? Look at it this way. Say you're throwing a party on the z-axis. Well, if you're inviting a friend to the party, you can say, hey, meet me at the point z at the time t. Or if your friend is a beam of light, you can say, hey, go forward along z for v units, and then reflect and come backwards along z for u units, and I'll see you there. So this is another way of thinking about the coordinates of an event in a plane that has one spatial dimension and one time dimension. You can also think of that plane in terms of two light-like null directions. And this concept is going to be very useful throughout this video. But naturally, the question comes up of, hey, if we can span the TZ plane with a null dyad, L and N, so that the coordinates of any event in the plane can be expressed as a sum over those two null vectors, then could we do something like this for all of the directions of spacetime? Like somehow constructing a null tetrad, where the coordinates of any event in the full four-dimensional spacetime could be expressed as a sum over four null vectors? Well, in order to do that, we would need to find a pair of null vectors which span the xy plane. But there's a problem. The xy plane is a spatial plane, and any space-like vector x is going to have a positive Lorentzian norm, and positive is not zero. Positive is greater than zero. So there are no real null vectors in a purely spatial subspace. They all have positive Lorentzian norm. You see, because earlier, when we were dealing with the TZ plane, we had a dimension of space and we had a dimension of time, and so we can span that plane with light-like vectors, because light-like vectors kind of combine space and time, right? So we were able to do that in that case. But if we're trying to span a spatial plane with null vectors, well, how do we do that? We need some time or something, right? So what do? Do we give up on the concept of spanning a spatial plane with null vectors? Well, actually, there is something we can do. This is an idea put forward by Newman and Penrose, which is to use complex numbers to make space-like null vectors. Now, I want to be clear, this is just an accounting trick. It's a mathematical technique that we use for algebraic convenience. In reality, the xy plane is not complex. And this complex null vector technique that we're going to use does not require us to imagine that space is complex. This is purely an accounting trick, as we're going to see, but it's all legit. This is all okay. All right, so the way this trick works is that we're going to define a pair of space-like null vectors as the complex conjugate pair m and m bar, defined as m equals the unit vector along x plus I times the unit vector along y, divided by a normalization factor of root 2. So we can write that as 1 over root 2, 0, 1, I, 0. And then the complex conjugate of that, m bar, is going to be the same thing, but with a minus sign on the imaginary y term. So we can write that as 1 over root 2, 0, 1, negative I, 0. Now right away, when you think about these vectors, you realize they're complex conjugate pairs, and so they are not independent of each other. If you know m, then you know m bar, and vice versa. So that's a little weird, because you're thinking to span a two-dimensional plane, you should have two independent vectors, right? Well, but then remember, each of these vectors is now complex, so it has twice as many degrees of freedom as a real vector. And so at the end of the day, we still have two independent degrees of freedom in this situation with the m and the m bar. And we'll get into that in more detail in just a moment, so that we can see exactly how m and m bar span the xy plane. But for now, let's go ahead and notice that the Lorentzian norm of both of these vectors is 0, because in both cases, when you evaluate the Lorentzian norm, you end up with a 1/2 plus a negative 1/2, which is 0. And also, if you take the inner product of m and m bar, you end up with 1/2 plus 1/2, which equals 1. And so our vectors are very conveniently normalized. So that's all good. And so now, using m and m bar, we have a null tetrad, comprised of the light-like vectors L and N, which span the ZT plane, and also this pair of complex conjugate vectors, which allegedly span the xy plane. But now the question becomes, how exactly do we convert between our usual picture of a 4-vector having components along time, x, y, and z, and this picture of spacetime being spanned by a null tetrad? Well, let's go ahead and draw some pictures and do some equations. All right then, so as we know, an event in spacetime, that is, somewhere and some when, can be written as a sum over the unit vectors in time as well as x, y, and z. So like we saw before, let's go ahead and use the 4-vector x to represent the coordinates of our event. And we can draw the projection of x in both the zt as well as the xy planes, in order to see its components in terms of t, x, y, z. Now these diagrams here have a different size, I don't mean to imply anything by that. I just drew them like this so they can fit on the screen, along with the equations that we're about to write. So now the claim is that our 4-vector X can also be written as a sum over the basis vectors of a null tetrad, with 2 light-like null vectors L and N spanning the TZ plane, and 2 complex conjugate null vectors M and M bar, which together span the real, space-like XY plane. So the picture with L and N we've already seen. L is the direction of a beam of light, N is the direction of another beam of light, and X can be thought of as going V units along L, and U units along N. So for L and N, we have a very easy visual picture, but the same is not exactly true for M and M bar. In fact, when thinking about how M and M bar span the XY plane, I think it's actually best to try to not over-visualize it. Now, usually I'm a huge advocate for trying to visualize math, but in this case, I think it's more helpful to take a step back and tell yourself that this thing involving M and M bar is just an accounting trick, and don't try to think about it overly geometrically, at least for starters, but instead just think in terms of the algebraic definition of M and M bar. Because if we go ahead and write out the definitions of L and N and M bar, you see that they're all very similar. In both cases, we're adding or subtracting some unit vectors, then we divide by a √2 normalization factor, and then on the complex conjugate pair, we bring in the imaginary unit. Alright, so then we already know that our 4-vector X can be written in terms of t units along time, plus x units along x, plus y units along y, plus z units along z. And now the claim is that the same vector can be written as v units along L, plus u units along n, plus a coefficient zeta bar units along m, plus zeta units along m bar. And in just a moment, we'll get into the definitions of zeta and zeta bar. But first, just a quick recap of what we saw earlier. For the L and N directions in the ZT plane, we have that the coefficient u is t minus z normalized by √2. Likewise, the coefficient v is t plus z normalized by √2. And if you flip that around, you can find that the time coordinate t is going to be u plus v normalized by √2, and the z coordinate is going to be v minus u normalized by √2. So those are the rules for how the coordinates transform when we hop back and forth in terms of t and z versus L and N. And we can write a very similar set of equations for x and y, as well as zeta and zeta bar. So here, zeta and zeta bar are analogous to the coefficients u and v, but instead of having 2 real independent coefficients, u and v, we now have one independent complex-valued coefficient zeta, given by the x-coordinate, plus I times the y-coordinate, normalized by √2. And then zeta bar is simply the complex conjugate of zeta. And if you switch that around, you can show that the x-coordinate can be written as a normalized sum of zeta and zeta bar, and the y-coordinate can be written as zeta minus zeta bar times negative I over √2. And so in that way, we have a recipe for translating between the x and y components of our 4-vector and this complex conjugate pair of coefficients, zeta bar and zeta, multiplied by our complex conjugate pair of null vectors, m and m bar, respectively. So now I'm going to show some algebra on the screen, and without getting into detail, we're just going to go through this real quick, and you can pause if you want to go into this in more detail. But I just want to make a couple of comments in passing about how you can check for yourself that these transformation rules are in fact true. So first of all, for the ZT plane, if you write your 4-vector in terms of v times L plus u times n, and then go ahead and put in the definitions of all those things in terms of t and z and the unit vectors along t and z, then you do some algebra, and you'll recover the fact that the 4-vector x can be written in terms of t times the unit vector in time, plus z times the unit vector in z. And you can also run that train of thought in the other direction, and go the other way, starting with t and z, and ending up in terms of L and n. So that's all good, the math checks out. And then we can also do exactly the same thing for our complex conjugate null vectors m and m bar, with a coefficient of zeta bar and zeta respectively. Yet again, we simply write the definitions of all those things in terms of x and y and the unit vectors along x and y, and then you work out the algebra, and you recover the fact that the 4 vectors x and y components can indeed be written as x times the unit vector along x plus y times the unit vector along y. So all we've done here is we've proven true this transformation rule between the xy picture and the m bar picture. But notice in this there is a profound insight, which is that even though we have the complex coefficients zeta bar and zeta, as well as the complex null vectors m and m bar, the way everything is defined here in terms of complex conjugate pairs ensures that we'll always end up with real x and y components in the xy plane. And when you see that, you realize that this idea of complex conjugate null vectors, it works. It's all good. Yes, it's an accounting trick, but when you look at the machinery of how it operates, you realize, oh, okay, this is just another way of spanning the xy plane using this pair of complex conjugate null vectors with complex conjugate coefficients. And even though it's a bit algebraically weird, it's going to make a lot of our equations actually simpler because of the convenient properties of m and m bar. All right, then just to wrap things up, let's go ahead and say a few concluding remarks about the concept of a complex null tetrad. Oh, and by the way, the Wikipedia article for the construction of a complex null tetrad is actually pretty good, so check that out if you want to learn more about this concept. Well, in any case, the basic idea is that we often think of spacetime as being spanned by basis vectors along t, x, y, and z, or perhaps, for example, t, r, theta, and phi if you want to use spherical coordinates. But in any case, such a set of 4 basis vectors, which are often chosen to be orthonormal, is called a tetrad, from the Greek tetris, meaning group of 4. By the way, that's also why the game Tetris is called Tetris, because all the shapes have 4 blocks. Well, anyway, as we've seen, we can also span spacetime with a complex null tetrad, where time and one spatial dimension are together spanned by 2 light-like vectors, L and N, and then the other 2 spatial dimensions are spanned by the complex conjugate pair, m and m bar, which comprise an algebraically convenient complex basis for the space-like 2-plane. Now then, L and N are a pair of real null 4 vectors, normalized such that the inner product of L and N is equal to -1, while m and m bar are complex null vectors. M and m bar are complex conjugates, so they're not independent, but because they're complex, all you need is for one of them to be independent, and you can span a real 2-dimensional space-like plane, as we demonstrated earlier. Of course, the defining property of a null tetrad is that all of our basis vectors are null. That is, the Lorentzian norm of L as well as N and M bar are all equal to 0, and that's a very convenient fact. Another fact is that the null vectors L and N are orthogonal to the complex null vectors M and M bar, which we would totally expect given the orthogonality of the ZT plane relative to the XY plane. So the inner product of L and L and M bar and N and M and N and M bar are all equal to 0. So that's also really convenient. Then we have our normalization conditions, which is that the inner product of L and N is equal to -1, while the inner product of M and M bar is equal to 1. And then finally, there's another fact, which is that we can reconstruct the metric tensor G from this expression here involving summing over the various downstairs components of L and N and M bar. We're going to go ahead and import this as a mathematical fact for the purpose of this video. And if you want to read more about this, you can Google metric reconstruction from a null tetrad, and you can read more about it. But the basic idea is that because of the way we've defined these null vectors, in terms of them being null and being orthogonal and being normalized, it's necessarily true that the A-B component of the metric tensor can be written as the sum of these various A and B components of the downstairs covector L, N, M, and M bar. And we're going to use this equation later on in the paper. Alright, so having seen this concept of a complex null tetrad, I want to give you an example of where this concept is actually really convenient. So imagine that you're on the event horizon of a Schwarzschild black hole, that is, a non-rotating black hole that has no electric charge. Well, you want to think about the instant you cross the event horizon, never to return to our universe ever again. And in that moment, when you're right on the event horizon, you think to yourself, Before I leave reality behind, I want to do one last exercise in general relativity, and you want to think about all the directions of spacetime from your point of view on the event horizon. Well, from the spherical symmetry of the black hole, you might think about the radial direction pointing away from the singularity, and also time, and then you also have a plane that's tangent to the two-sphere of the event horizon. So that's sort of one way to think about spacetime from your point of view on the event horizon. You have a radial direction, you have time, and you have a tangent plane to the two-sphere. But you'll notice that actually a complex null tetrad could also be used in this situation, and is actually quite a natural fit, because we can use the null vectors L and N to span the radial and the time dimensions, where L is the spacetime direction of a photon that's on the horizon, going straight outwards trying to escape, but being perfectly stuck forever on the event horizon. And in that sense, you can think of L as being tangent to the generators of the horizon, where the generators are the null geodesic curves that flow along the event horizon and that are forever stuck in place, like a photon always trying to escape, but always remaining on the event horizon. The vector L is pointing in that direction in spacetime. And then the null vector N is another beam of light that's going directly into the black hole, gleefully accepting its fate. So in the instant that you're on the horizon, if you have two laser beams, you point one out away from the hole and you point the other one straight in, the direction in spacetime of those two laser beams are going to be L and N respectively. So then you see how together L and N span all of the possible radial and time directions within the light cone of an observer on the event horizon. But then something really weird is going on the event horizon, because even though a photon moving along L is trying to escape, it never actually gets out of the horizon. And so in that sense, the light cone is tilted vertically on the L side, in that there's no escaping the horizon. At most, even if you're a photon at the speed of light trying to get out of there, the best you can do is stay in place, as viewed from an observer way outside of the black hole. And when you think about that, you realize that in that moment that you're on the event horizon, it's like your fate is sealed, because your light cone's vertical on one side, so you're not going out. You're only going in. You're going in the hole. That's just how it is. So that's the radial and time dimensions, also known as the L and N dimensions. But then we also have the plane that's tangent to the two-sphere, and so we might as well go ahead and span that with the complex null vectors m and m bar. And we're using those purely as a matter of algebraic convenience. Remember, the physical plane itself is not actually complex. We're just using m and m bar as an accounting trick, which is totally valid and doesn't make us have to believe anything weird about space being complex. But no, it's just a convenient bookkeeping move that lets us span all four dimensions of spacetime with a set of four algebraically convenient null vectors. The null vectors L and N genuinely are null vectors in the sense that they are light-like vectors, but m and m bar are just a way of encoding a space-like plane in a mathematically convenient way, as we'll see later on. In fact, the situation described here is pretty much exactly what we're going to do later on in parts 2 and 3 of the paper. The only difference being that in the paper, we're going to be dealing with a Kerr black hole, which is rotating. And so there's going to be some mixing of rotation and time, as described in equation 8. But we'll get into that later on. For now, this is a good picture to keep in mind as far as what a complex null tetrad is, and how it can be useful on the event horizon of a black hole. Alright, next up, I want to say a few words about integral curves. This is a concept that you see a lot in relativity, and we're going to see later in the paper. So suppose we have some vector field, call it V. Now V can exist in any number of dimensions, but because your screen is two-dimensional, let's go ahead and imagine it as a vector field in 2 dimensions. And suppose that the field is not changing in time, so that we can think about it just as like a geometric pattern. Now, associated with this vector field, there's the concept of integral curves, and to see what these are, suppose we sprinkle some dots throughout the field, and then we're going to let them flow with the velocity given by the vector field v at each point. So you see how the dots are moving in accordance with the vector field? At every moment, for every dot, if you look at how fast is it going and in what direction, the answer to that is v. The vector field is a velocity field for these dots. That's what we're imagining. So then in this situation where you have all these flowing dots, the path of each dot, call that x of t, traces out an integral curve of the vector field. So that's what an integral curve is. Now the essential property of an integral curve is that its tangent vector, call that x prime, is always the vector v at each point. In other words, from the curve's point of view, the vector field v is like a derivative field. Although I've never heard someone say the term derivative field, people do say integral curves, but derivative field I don't think is really a technical thing. The reason I bring it up is because we think in terms of integrals and derivatives as being two sides of the same coin. Well, here you can imagine a vector field growing these integral curves as various points flow around in the field. Or if you want to think about it from a perspective that emphasizes the curves, you can then think of the field as representing the derivatives of all these curves at each point. If we want to get mathematical about this, we can write x prime equals v evaluated at x. That is to say, the tangent vector x prime is simply the vector field v evaluated at the position x. And because these dots are flowing in time, x prime and x are both functions of time. Now I should point out that technically speaking, the dots would still trace out the same integral curves if they had different speeds along the same direction field. And so these integral curves can actually be created by a slightly more generic rule than just have the dot's velocity equal the vector field. Because at the end of the day, when you look at these curves, what's not so important is at what time was the dot at each point along the curve. No, what matters is what is the shape of the curve and the position of the curve and the tangent vectors of the curve. So all that is to say, we're thinking about velocity and time in order to parametrize these curves, in order to create them as the time variable goes forward, but there are different ways to parametrize the curve and end up with the same result. The main thing is just to see that the tangents of the curve are the field itself. All right, so that's the concept of an integral curve. All right, now there's one more concept that we have to talk about before finishing our mathematical warm-up and getting back into the paper. And that is the concept of killing vector fields, also known as killing fields. Now you might be thinking, whoa, hey, well, hold on now, what are we getting ourselves into here? Because if you've studied history, you know that a killing field is always some dreadful thing. But in physics, it's different. In physics, a killing field is a good thing, because it means that we're dealing with symmetry, and symmetry is nice. Symmetry simplifies. And so killing fields are going to make our equations simpler and more fun. So first of all, the definition of a killing vector field, call it K, is that this vector field generates a symmetry of the spacetime. So think about a killing field as a vector field where as you flow along the integral curves of that vector field, we're not going to have a change in our spacetime metric. And we'll get into some specific examples in just a moment to make this concrete. But first, I want to tell you about the killing equation, see Poisson 1.21, which is that a vector field K is a killing field if and only if K downstairs A semicolon B plus KB downstairs semicolon A is equal to 0. That is to say, a vector field is a killing field if and only if the covariant derivative along the downstairs covector K is antisymmetric when you swap those A and B indices around. So that is the defining constraint on how a vector field has to be in order for it to be a killing field. Now the reason that this equation is the defining equation for a killing field is because this is actually equal to the Lie derivative of the metric along the vector field K. So what that means on the left side here, we have L sub K GAB. That is going to be the derivative of the metric tensor along the flow of the vector field K. Now for all vector fields, it holds true that the Lie derivative of the metric along K is equal to the expression shown here with the K downstairs A semicolon B plus K downstairs B semicolon A. So that's generically true for all vector fields, but what makes a killing field special is that that quantity is always equal to 0. So in other words, as you flow along the integral curves of the vector field K, the metric does not change. So now's a good time to get into some specific examples. Well, first of all, if you imagine Minkowski spacetime, that is flat spacetime, you find that it is maximally symmetric as it can be, with a whopping 10 killing fields. First of all, we have the 4 translations. So these are the 4 ways that you can offset your coordinates in time and space, respectively. So for example, for the time translation, you can imagine a vector field that's constant everywhere and points purely in time. And then if you were to flow along that vector field pointing purely in time, well, the metric isn't changing, right? There's a symmetry of that situation. All that's to say, Minkowski spacetime has time translational symmetry. And the same is true of spatial translational symmetry. If you imagine a constant vector field pointing purely along x, and then you flow along x, so you take all the things you're considering and you give them a constant offset in x everywhere in spacetime, you find that nothing changes. So Minkowski spacetime has a spatial translational symmetry. And also, you can take any constant combination of these offsets and combine them to make a more generic spacetime translational killing field. And so we can say that Minkowski spacetime has 4 spacetime translational killing fields, by which we mean 4 independent killing fields, that together you can think of as a kind of basis set, which span all the possibilities for spacetime translations. Then we also have 3 rotational killing fields for Minkowski spacetime, and these have the form shown here. To rotate about the z-axis, we can flow along a field where the y-offset depends on the x-coordinate, and the x-offset depends on the negative y-coordinate, and likewise for rotations about the y-axis, as well as rotations about the x-axis. Now these rotational killing fields are more interesting than the translational killing fields, because you see how they swirl. And a good exercise is to show that the vector fields shown here in the magenta text for rotations satisfy the killing equation. But also, we don't have to overcomplicate it. We can think more abstractly and say Minkowski spacetime has 3 rotational killing vectors. And of course, here again, what we mean by that is 3 independent rotational killing vectors, which together generate the rotational symmetry of Minkowski spacetime. And then finally, another aspect of the symmetry of flat spacetime is that we have 3 boosts. And these are sort of like rotations in a spacetime plane. So to imagine a boost, suppose that you're floating in space, and then your friend comes floating by along the x direction. Well, if you boost into their reference frame, you can do so using the killing fields shown here. Now admittedly, the boosts are harder to think about than the rotations, but these represent the fact that in Minkowski spacetime, all observers in inertial reference frames have a valid claim to the description of reality. So you can hop from your inertial frame into a frame that's moving relative to you along some arbitrary direction in space, and when you hop into that other inertial frame, you have to find yourself in a description of reality that corresponds to the description of reality you had in your other reference frame when you take into account special relativity. Now then, taken together, these 10 killing vectors generate the Poincaré group, which is the group of isometries of Minkowski spacetime. By isometry, all we mean is a transformation that leaves the metric unchanged. So now it's worth looking at a situation where we don't have all of these killing fields. For example, when you think about the spacetime around a non-rotating black hole, you realize there's only 4 killing vectors in that situation. Assuming the black hole has settled down and is in a stationary state, then you have a time translational killing vector, as well as 3 rotations, with the black hole at the center, by the spherical symmetry of a non-rotating black hole. So all that's to say, if you have a non-rotating black hole, and you think about what are the ways you can move in spacetime without changing the metric, well, you can rotate around in 3 independent ways by spherical symmetry, and there's also a sense in which you can translate forward in time because of the stationarity of the situation. But now you have to be careful because that time translational killing vector is not exactly the kind of thing that you would find in flat Minkowski spacetime. Far away from the black hole, it still is. Out there, your time translational killing field is very much the same kind of thing that it is in flat spacetime because of asymptotic flatness. But when you're close to the black hole, and specifically when you're right up on the event horizon, then in that case, your time translational killing vector is actually going to be a null vector, a light-like vector, which you can imagine as the space-time direction of a photon trying its best to escape the horizon, but forever staying in place as viewed from outside. That is to say, if you find yourself on the event horizon of a black hole, and you're like, all I want to do is experience the passage of time as viewed from an observer far from the black hole, well, you better be traveling at the speed of light. So anyway, the black hole is going to mix time and the radial direction together a little bit, but we still have this notion of a time translational killing field. However, we no longer have our spatial translations, nor do we have our boosts. These are not killing vectors around a non-rotating black hole. The reason being, if you're somewhere in space, and then you translate to a different point in space, well, in general, the metric is going to change when you do that, because you've got a black hole in your spacetime, and that's warping the metric from one place to another. And a similar thing also holds true for boosts, when you think about the way that's going to kind of skew the spacetime and you think about the way the metric changes around a black hole. Boosts are no longer killing fields. So you see, when you're dealing with a non-rotating black hole, you're like, oh no, we only have 4 killing fields now. So the spacetime is more complicated and not quite as symmetric as Minkowski spacetime. And this gives you a real good appreciation for the simplicity of Minkowski spacetime, with all of its symmetry and all of its killing fields. And then you realize, okay, yeah, killing fields actually are a cool thing, not because our enemies have been laid to waste, but because it's nice to have some symmetry in your equations. And the more complicated your spacetime gets, the less symmetry you have. On that topic, in the paper, we're dealing with a rotating black hole. And when the black hole is rotating, now we only have 2 killing vectors. First of all, we still have a time translational killing vector, which corresponds to the fact that even a rotating black hole is going to settle down into a stationary state, where even though the black hole is rotating, the metric exhibits a kind of time translational symmetry as encoded in our time translational killing field. And also, for a rotating black hole, we still have 1 rotational killing vector, but that's only for rotating around the axis of symmetry of the black hole. So a rotating black hole is going to be axisymmetric. That is to say that you can change your longitude without the metric changing. But if you change your latitude, as you move in the north or south directions around a black hole, the metric is going to change as you move along. So we don't have a full SO3 symmetry like we had before for a non-rotating black hole. So as we get into the paper, we're going to use K for our time translational killing vector, and K tilde for our rotational killing vector. And even though we only have 2 killing vectors, and not the full 10 of Minkowski spacetime, even still, we can use these to constrain the structure of our equations in spacetime. So K and K tilde are going to be super helpful in simplifying our equations, and giving us a way to mathematically think about the symmetries of the spacetime around a rotating black hole. All right, my friends, now that we're all mathematically warmed up, let's go ahead and return to the paper and get into part 1. All right, let's get into part 1, Introduction. Part 1 is pretty similar to the abstract, with just a couple extra things, so we'll go through it pretty quickly. It is generally believed that a gravitationally collapsing body will give rise to a black hole, and that this black hole will settle down to a stationary state. And here, by stationary state, what we mean is that there's going to be a time-like killing vector, and so the metric is going to stay constant with respect to translations along that killing vector. If the black hole is rotating, the stationary state must be axisymmetric. You can see a proof of that in reference 1, and an improved version of this theorem, involving weaker assumptions, is outlined in reference 2, and is given in detail in reference 3. So what do we have so far? We know that our black hole is going to be stationary and axisymmetric. In other words, we're going to have 2 killing vector fields, one for translations in time, and another for rotations about the axis of symmetry. It has been shown that stationary axisymmetric black hole solutions, which are empty outside the event horizon, fall into discrete families, each of which depends only on 2 parameters, the mass m and the angular momentum j. See references 4 through 6 for more information on that. But all that means is that if you have a black hole and it's empty outside the event horizon, including no electromagnetic fields out there, then all you need to know to describe that black hole is its mass m and its angular momentum j. And by the way, that pertains to something called the no-hair theorem. Well, anyway, the Kerr solutions for m to the fourth powers greater than j squared are one such family. Now let's think about what that means. On the left-hand side, we have a power of the mass of the black hole, and that provides an upper bound on the square of the angular momentum of the black hole. Another way to look at this is m squared is greater than j. And so what this means is that if you have a spinning black hole with some angular momentum j, the maximum value that the angular momentum can have is m squared. One way to think about that is if the black hole gets too spinny, you can imagine it's too spinny to be a black hole. I mean, maybe that's kind of an informal way to think about it, but yeah, there's an upper limit to how much angular momentum a black hole can have for a given mass. The paper then goes on to say that it seems unlikely that there are any others, by which they're referring to discrete families of solutions. And all that's to say is that probably the Kerr solutions, where you have angular momentum bounded by mass squared, is the only solution for a stationary axisymmetric black hole, which is empty outside the event horizon. It also seems reasonable to suppose that the Newman-Kerr solutions for m to the fourth is greater than j squared plus m squared q squared, where q is the electric charge, are the only stationary axisymmetric black hole solutions which are empty outside the event horizon, apart from an electromagnetic field. So with the Newman-Kerr solutions, what you want to imagine is a black hole with some mass m, some angular momentum j, and some electric charge q. And in that case, you have a very similar limit on how much angular momentum such a black hole can have. But notice that now we have that term m squared q squared. And so the more electric charge the black hole has, the lower the upper limit is on the angular momentum that it can have. One way I like to imagine this is that if the mass is what's holding the black hole together, then angular momentum, as well as electric charge, are wanting the black hole to fly apart. And that's not exactly a formal way to think about it, but that's kind of the right intuition to have. All right, so we have the Kerr solution for a rotating black hole with no charge, and we have the Newman-Kerr solution for a rotating black hole that does have some electric charge q, and these can all be very neatly described by the parameters of the mass, the angular momentum, and the electric charge. On the other hand, there will be an infinite-dimensional family of stationary axisymmetric solutions in which there are rings of matter orbiting the black hole. All that means is we're going to have much more of a variety of solutions when you consider all the possible kinds of rings of matter you can put around the black hole. In this more generic context, you need to know more than just the mass, the angular momentum, and the charge of the black hole, but you also have to know something about the distribution of matter outside the black hole. So, in sections 2 and 3 of this paper, we shall derive formulae for the mass of such a solution, equation 13, and for the difference in mass of two nearby solutions, equation 34. So that's exactly what we already talked about in the abstract of the paper. The main results of this paper are going to be deriving a mass formula in part 2, and then varying that to find a differential mass formula in part 3. And then the interpretation of those formulas is what leads us to the analogy between black hole mechanics and thermodynamics. These mass formulas generalize the expressions found by Smar, see reference 7, and Bekenstein, see reference 8, for the Kerr and Newman-Kerr solutions. And later on, we're going to talk more about that, but basically these mass formulas, because they account for the matter outside the black hole, they let us generalize relative to the analysis where we don't have any matter outside the black hole. Then, when interpreting these equations, we show that the quantities appearing in these formulae have well-defined physical interpretations. Of particular interest are the area A of the event horizon and the surface gravity Kappa, which appear together, as you can see. These have strong analogies to entropy and temperature, respectively. Pursuing this analogy, we are led in section 4 to formulate 4 laws of black hole mechanics, which are similar to, but distinct from, the 4 laws of thermodynamics, which by now you've heard many times, so, we're good to go. We're ready to get into part 2. So part 2, this is where things start to get a little intense. I mean, it's no part 3, but it is part 2. So we're going to start to be diving into some mathematics. In particular, the part 2 starts off by talking about the killing vectors, k and k tilde, associated with a stationary axisymmetric, asymptotically flat spacetime. So, in such a spacetime, there is a unique time-translational killing vector, call that k, which is time-like near infinity, so really far from the black hole. And far from the black hole, we have it normalized such that the contraction Ka is -1. That is to say, our time-translational killing vector can be thought of as a unit time-like vector at the flat spatial infinity far from the black hole. And the existence of this killing vector is what we mean when we say that the spacetime is stationary. The word stationary means that there's some symmetry associated with the progression of time as encoded in this killing vector field. Now, of course, you gotta remember this is general relativity, and so time is a weird concept, but we'll get into all that as we go along. Your common sense applies far from the black hole, and then as you get closer to the black hole, things get a little more tricky, but we'll get into it. And then secondly, because the spacetime is axisymmetric, that means that we're going to have a unique rotational killing vector, call that k tilde, whose orbits are closed curves with parameter length 2 pi. And all that's to say is that our spacetime is axisymmetric. So if you draw a line between the north and south pole and rotate about that line, then that's going to be an axis of symmetry, and so the metric isn't changing as you rotate along this killing vector k tilde. And so really all we've done here by introducing these killing vectors k and k tilde is we've taken the concept of a stationary axisymmetric asymptotically flat spacetime, and we've converted those adjectives into these mathematical concepts of killing vectors, and then the properties of these killing vectors are going to be very useful for constraining and analyzing the various equations that are happening and going on in this spacetime. So to that end, the paper goes on to list a whole bunch of properties of these killing vectors. And I'm just going to put all this text here on the screen, and then we're going to go through and look at each part of this one at a time. For starters, let's go ahead and look at equation 1. Well, equation 1, it has 2 parts, one for the time-translational killing vector k, and another one for the rotational killing vector k tilde. But you'll notice in both cases these are exactly the same equation. And this equation is a very special equation. This is called the killing equation. See Poisson 1.21. Don't worry, it's nonviolent. It's okay. It's peaceful. And this is actually the defining equation for whether or not a vector field is a killing field. And so let's go ahead and unpack this and see what it really means. For the sake of simplicity, let's only consider the first equation involving k and ignore the one involving k tilde because they're the same equation. So we only have to pick one and understand that one, and then we understand the other. Well, first of all, if you go ahead and look at the right-hand side of the equation, there's this term k underscore brackets a semicolon b. And here, the square brackets around our indices refer to anti-symmetrization. By definition, anti-symmetrization of a thing means you take 1/2 of the thing minus the thing with the indices switched around. So then k underscore brackets a semicolon b is going to equal 1/2 of k a semicolon b minus kb semicolon a. Okay, so now we've got those brackets out of the way. We went ahead and unpacked that. And now just remember that we're using a semicolon to denote the covariant derivative. So for example, k with a downstairs a semicolon b, that means that we're taking the covariant derivative along the b direction of the downstairs killing covector ka. And likewise then, the second term here, k underscore b semicolon a, that is the covariant derivative along the a direction of the b component of the downstairs killing vector, a kb. So now all we've done here is we unpacked the anti-symmetrization and replaced those square brackets with the definition of what they mean. So returning to equation 1, we see that k, a semicolon b downstairs, equals 1/2 k, a semicolon b downstairs, minus KB semicolon A downstairs. Now, if you go ahead and subtract from both sides 1/2 KA semicolon B, and then multiply everything by 2, you find the equation KA semicolon B equals negative KB semicolon A. And because all we've done here is some algebraic maneuvering, you can see that equation 1 is really nothing more than the statement that downstairs KA semicolon B is antisymmetric, in the sense that if you switch the indices around, you pick up a minus sign. And that fact, the fact that the covariant derivative of a killing field is antisymmetric in the sense shown here, is the quintessential property of a killing field. So for the purpose of this paper, we're just going to import equation 1 as a mathematical fact. And if you want to read more about it, see Poisson, equation 1.21, or just search online the killing equation, and you can read all about where that comes from and why that's the case. All right, then next up, we're going to go ahead and move on to equation 2, which says that time translations and rotations commute. That is to say, if you flow forward in time and then flow around rotationally, you end up with the same result as if you flow around rotationally and then flow forward in time. If we want to be a little more precise about it and take this equation literally, we can say that the covariant derivative of downstairs Ka in the direction of upstairs K tilde B equals the covariant derivative of downstairs K tilde A in the direction of upstairs KB. But sometimes you want to zoom out from the equation and say, what does this really mean? Why do we care about this? Well, as I mentioned earlier, all this equation really means is that flowing along one killing vector leaves the other invariant, in this particular case. It's worth pointing out that equation 2 is not true of killing fields in general, in contrast with equation 1, the killing equation, which is generally true of all killing fields. But no, equation 2 is an equation that happens to be true when our killing vectors are time translations and the rotation around our axis of symmetry for a stationary axisymmetric spacetime. You might be thinking, hey, what's an example of a situation where killing vectors don't commute? Well, imagine a non-rotating black hole, that is a Schwarzschild black hole, which has spherical symmetry. Then in that case, you actually have 3 independent rotational killing vectors, one for each of the ways you can rotate around a thing in 3 dimensions with spherical symmetry. But as you know from 3-dimensional rotations and how they don't commute, in that case, the order does matter. So anyway, all you have to know about equation 2 is that rotations around the axis of symmetry and time translations commute. Now next up, we have equations 3 and 4, which, if you look at them, are actually the same exact equation in both cases. It's just that one of them applies to the time translational killing vector k, and the other one applies to the rotational killing vector k tilde. And both of these equations are telling us that the D'Alembert operator of a killing vector field is sourced entirely by the Ricci curvature acting on that killing vector field. To see why that is, it might help to write the left-hand side of this equation in other notational formats. So the notation used in this paper is quite concise, but just to clarify, when they write k upstairs A semicolon B downstairs B, what they mean is that if you want to write this in nabla notation, then you have a downstairs nabla contracted with an upstairs nabla acting on Ka, and so that sort of has the flavor of a second derivative, and actually that is the definition of the D'Alembert operator, which is often symbolized with the square. Now, what to say about equations 3 and 4? Well, I guess there's a couple of things. Well, the first thing is that if we were operating in a flat spacetime and everything's all nice and flat and simple and life is good and easy and everything's fun, well then the Ricci curvature tensor would be 0, and so then we would find that the D'Alembert operator acting on a killing field is 0, which is to say that in flat spacetime, a killing field would be harmonic. Here again, we find a qualitative difference between physics and history. But then in a curved spacetime, when you have a non-zero Ricci curvature, that's going to give us some non-zero D'Alembert in our killing field. Naturally, you're wondering why this is and how do we know this is true? And that's a great question, although it does take a little bit of unpacking, and in the interest of time, I do want to go ahead and just import equations 3 and 4 as mathematical facts. But I will tell you this. If you're interested in this question, you want to look at Poisson, problem set 1.13, and in particular problem 9. The second half of problem 9 is literally the question of prove this equation to be true. And they give you a little hint as well. And if you read the previous few pages, you can work out the math and you can go ahead and prove that. So it is something that can be done. It's not something we have to take on faith, but it's also a generic property of killing fields in general relativity. And so in the interest of time, we're just going to go ahead and import these as mathematical facts. All right, then the paper goes on to mention the definition of the Ricci tensor, RAB, which, as we talked about earlier, is a contraction of the Riemann curvature tensor. You can read more about that in Poisson 1.38. And on that topic, the paper then goes on to define the Riemann curvature tensor in terms of the extent to which the covariant derivative of any vector field does not commute, like we mentioned earlier as well. Here they use a rather concise notation involving those antisymmetric brackets on the BC, but if you want to go ahead and unpack that antisymmetrization and then multiply everything by a factor of 2, you can see directly that what they're saying here is that the Riemann curvature tensor encodes the extent to which covariant derivatives do not commute. So that's all good. That's all standard differential geometry definitions. So again, we'll import that as a mathematical fact, and we'll use these as analytical tools as we go along in the paper. Oh, and then one final note about our index naming convention. Throughout the paper, we are using something called abstract index notation, which was popularized by Penrose, and sometimes you also hear this described as slot naming index notation. In this notation, we use indices as placeholders, not as components in a particular basis. So for example, consider our time translational killing vector, Ka. Well, that is a 4-vector field, which is independent of any coordinate system. You know what I mean? The thing exists before we define a coordinate system and make a coordinate chart and then have specific numbers applied to the values of its components, right? The 4-vector itself is a thing that exists, so we can just call it Ka. So anyway, you'll see as we go along how the mathematical machinery of abstract index notation works. This paper is actually a really good example of how to use abstract index notation. So that's cool. That's a good learning experience. All right, so now we're going to define a hypersurface S as well as its boundary. And this is going to let us make global integral statements about integrals on the hypersurface as well as integrals on the boundary of the hypersurface. And those integral statements are then going to lead into our integral mass formula, which is what we're trying to derive here in part 2 of the paper. So first, I want to go through the next few sentences somewhat quickly, just to get it all out there on the screen, and then we're going to go back through it carefully to see what exactly each part of this means. So first of all, go ahead and imagine around our black hole, we're going to have a space-like hypersurface, call that S. Bear in mind, when we're working within a 4-dimensional spacetime, a 3-dimensional subspace of that is going to be a hypersurface, in much the same way that in a 3-dimensional space, a 2-dimensional subspace can be thought of as a surface. So at a first glance, and this isn't entirely correct, but if you just want to imagine the space around the black hole going off to infinity, that's kind of a good intuitive starting point, bearing in mind that it's not actually going to be a surface with global simultaneity. But we'll talk about that more in just a moment. For now, the important thing is to see that the boundaries of this space-like hypersurface can be thought of in 2 parts. First, we can think about the boundary of the black hole itself, that is the intersection of our hypersurface S and the 2-sphere part of our event horizon. And then the other part of the boundary of the hypersurface you can imagine as a bubble that's way out infinitely far away from the black hole. And don't get too hung up on the infinity, of course. That just means something that's very far away, and then you take the limit as very far approaches infinity. So then we see that the boundary of our hypersurface is comprised of the boundary of the black hole, as well as this boundary at infinity. Now then the paper goes on to say that since the covariant derivative of the covector Ka along the dimension B is antisymmetric by equation 1, the killing equation, one can integrate equation 3, that is, that the D'Alembertian operating on the killing field is encoded by the Ricci curvature tensor. We can integrate that over a hypersurface S and transfer the volume on the left to an integral over a 2-surface bounding S. And that leads to equation 5, where we have the integral over the boundary of S with differential element d sigma AB, and the integral over the space-like hypersurface S with the differential element d sigma A. Now that sentence and that equation requires a whole lot of unpacking. And don't worry, in just a moment we're going to go through this in detail, and we're going to see what that means. But I just want to say a few more sentences to get it up on the screen before we go ahead and investigate exactly what everything here means. But a couple more things while we're here is that we shall choose our hypersurface S to be space-like, asymptotically flat, tangent to the rotation killing vector, k tilde, and to intersect the event horizon in a two-surface. And so, as we've seen, the boundary of our hypersurface S consists of the boundary at the event horizon, as well as a two-surface at infinity. Okay, so now with these ideas on the screen, let's take a moment to talk about the details here and figure out what exactly all this means. Well, first of all, let's talk about these conditions on our hypersurface. Well, when we say that our hypersurface is going to be tangent to the rotation killing vector k tilde, that means that if we flow along that rotational vector and we are within S, we're going to stay within S. So imagine you're at some point in our hypersurface S, and you're rotating along the rotational killing vector k tilde. That motion, that rotation, is not going to poke you out of the hypersurface S. No, you're going to stay in the hypersurface. Another way to put it is that at each point in our hypersurface S, the directed volume element, d sigma A, can be written as NA dvs, where NA is a unit normal vector, and dvs is a volume element. And so you can think of d sigma A as an infinitesimal volume element with some vector orientation, which is normal to the hypersurface. In this case, because our hypersurface is chosen to be space-like, what that means is that our normal vector, NA, is everywhere going to be time-like. So if you think about a space-like hypersurface embedded within four-dimensional spacetime, the vector that points out of the hypersurface in a perfectly normal direction is going to be a time-like vector. Now that doesn't mean it's going to point purely in time, and accordingly, the fact that our surface is space-like doesn't mean it's going to have global simultaneity, because bear in mind that a time-like interval is just something within the light cone, and a space-like is something that's outside of the light cone. So anyway, the reason I bring that up with regards to our hypersurface being tangent to k tilde is that if you think about taking the product NA k tilde A, that's going to be 0 everywhere on our hypersurface, which in other words is to say that the rotation killing vector k tilde A does not poke out of S. So that's an important property of our space-like hypersurface. Now then, as mentioned just a moment ago, because we're choosing our hypersurface S to be space-like, what that means is that for everywhere on S, the normal vector n is going to be time-like. Then we also have the asymptotically flat condition, and what that means is that our metric is going to approach the Minkowski metric at spatial infinity. That is to say, if we go very, very far away from the black hole, then way out there, the curviness of spacetime becomes totally negligible. And that makes sense, because black holes make spacetime all curvy and weird, but the effect is going to drop off as you go far away from the black hole. And when you think about going far from the black hole, our space-like hypersurface S you can think of as asymptotically orthogonal to the time-like killing vector k, and in other words, you can imagine the hypersurface S approaching a surface of constant asymptotic time. And so if you're far away from the black hole, you can imagine the hypersurface S as being sort of like a now slice of constant time, but as you get closer to the black hole, it's important to bear in mind that the hypersurface S is not globally simultaneous. Because if you think about the Kerr solution for a rotating black hole, you're going to have frame dragging, which is going to twist time into space in a really confusing way. And so all that's to say, if you imagine these time-like normal vectors n living at each point along our space-like hypersurface S, it's not the case that n is going to be pointing in exactly the same direction in time everywhere you go. But no, it's a more curvy situation. Now later on in the paper, we can define a time coordinate t as the distance from our hypersurface along the integral curves of our time-like killing vector k. But we'll talk about that later. One final comment on the selection of this hypersurface is that the criteria stated here, that is, space-like, asymptotically flat, and tangent to the rotation killing vector k tilde, it does not uniquely determine our choice of space-like hypersurface. So the following arguments are going to be somewhat generic with regards to what specific hypersurface we choose. But the three conditions stated here are going to be sufficient to allow us to derive our integral formula for the mass of the black hole. So now I'd like to say a few words about Stokes Theorem, not with the same amount of detail as Poisson goes into in section 3.3.3, but just big picture. Stokes Theorem tells us that the integral of the exterior derivative of a form over a region equals the integral of that form over the boundary of the region. And that is a very abstract and generic way to think about Stokes Theorem. But in the context of this paper, you can think about it more specifically. So first of all, imagine we take equation 3, and we simply integrate both sides over our hypersurface S. Well, so then we have two integrals over the hypersurface S, and if you look at the left-hand side, that is the thing that we're going to apply Stokes Theorem to in order to get the left-hand side of equation 5. And notice that the right-hand side of equation 5 is simply the integral of the right-hand side of equation 3 over the hypersurface S. As I was making this video, I realized it is actually important to go into a little more detail on what exactly is happening here, and so in just a moment we'll talk about this in more depth. But before we zoom in to those details, I want to draw an analogy to electromagnetism. So in my video, Electromagnetism as a Gauge Theory, about an hour and 35 minutes in, we used Stokes Theorem to derive Faraday's law of induction by turning a surface integral over the curl of the electric field into a line integral of the electric field around the perimeter of that surface. And you see this kind of move very often in electromagnetism. So in this context, what we did is we had a flux integral across the surface ds of the curl of the electric field. And then we converted that into a circulation integral around the perimeter of that surface of the electric field itself. And one way this is often described is that all the swirls that live on the surface add up to the big swirl around the perimeter of the surface. And so this is kind of a good analogy for what we did to get from equation 3 to equation 5 on the left-hand side of the equation. When we converted from an integral over the hypersurface S to an integral over the two-dimensional boundary of S, that's sort of like a dimensionally upgraded version of going from an integral over a surface S to an integral around its perimeter. Now in this case, we have a three-dimensional hypersurface instead of a two-dimensional surface, and therefore we have a two-dimensional boundary as opposed to a one-dimensional perimeter. But in both cases, we have Stokes Theorem, and so it's the same kind of idea. But now instead of thinking in terms of three-dimensional space, with two-dimensional surfaces that have one-dimensional perimeters, we're thinking in terms of a four-dimensional spacetime with three-dimensional hypersurfaces that have two-dimensional boundaries. Alright, now because getting to equation 5 is such an important part of the paper, I do want to say a few more words about the technical details of how we get from equations 1 and 3 to equation 5. So the first thing to do, as we talked about, is you take equation 3. Equation 3 tells us that the D'Alembertian operator acting on our time-lag killing field is encoded in the Ricci curvature tensor. And that is a local statement that applies throughout spacetime. So therefore, if we go ahead and integrate that over our space-like hypersurface S, we end up saying the same thing, but now it's a global statement, because we're adding it up all over our hypersurface. So that's a legit move. We're allowed to integrate a local statement into a global statement. Now then equation 1, bear in mind this is Killing's equation, which tells us that the covariant derivative of the covector Ka along the direction b is going to be antisymmetric. That is, if you flip a and b around, this term picks up a minus sign. And that fact is required in order to let us apply Stokes Theorem in this context. And so then by applying Stokes Theorem, we can convert our integral over the hypersurface S into an integral over the boundary of S. And that's equation 5. But what exactly does equation 5 mean? Why does this matter? Well, let's get into the details. So first of all, if you look at d sigma A, that is the directed volume element of our three-dimensional hypersurface S, which is embedded in spacetime, and we can write that as d sigma A equals NA dVs, where n is a unit covector which is normal to S, and because S is space-like, therefore n is going to be time-like. So then if you think about this term, Ka semicolon b, b d sigma A, that is the contraction of the D'Alembertian operating on our time-like killing field with the directed volume element d sigma A. In other words, before we apply Stokes' theorem, that integral on the left-hand side over S, you can think of that as being the flux of the D'Alembertian operator acting on K through the hypersurface S. So, in 3 dimensions, you have a 2-dimensional surface, it has normal vectors, and you can take a flux integral by taking the dot product of some vector field with those directed surface elements. Well, now just go ahead and increase that by 1 dimension, so you're imagining our 3-dimensional hypersurface in spacetime. It has a directed volume element with a time-like normal vector, and so you can think about this integral as a kind of flux integral through that hypersurface. And so in your imagination, that is what sets the stage for you thinking about maybe we can apply Stokes Theorem and can convert that flux through the hypersurface into an integral around the boundary of the hypersurface. And to do that, imagine that our surface S and its boundary have the same time-like normal vector, but the boundary of the surface is also going to have a space-like normal vector, call that lowercase s, which is going to be perpendicular to the boundary of the surface, but is going to live within the hypersurface S. So then, with our time-like normal n and our space-like normal s, we can construct a directed area bivector, d sigma AB, of the two-surface boundary of S, and specifically, we can write d sigma AB in terms of an antisymmetric product of n and s times an area element dA. You can read more about the details of that in Poisson 3.21, and note that his convention includes a factor of 2 baked into the differential element. But for now, all you really need to know is that this term involving the n and the s and the brackets and the a and the b, all that means is NASB minus NBSA divided by 2. So as we saw previously, the brackets denote anti-symmetrization. And if you're familiar with the wedge product, you can look at this and say, oh, that's the wedge product of n and s, which is sort of like an oriented plane based on the vectors n and s. So just imagine that as something that has an area and an orientation. All right, well anyway, with all that said, let's now think about it big picture. What have we done to get to equation 5? Well, we start off with the idea that the D'Alembert acting on K is encoded by the Ricci curvature tensor. We integrate that over a space-like hypersurface S, and then we apply Stokes Theorem to the left-hand side to convert that from an integral over the hypersurface S to an integral over its boundary. Now bear in mind that the boundary of S includes 2 different regions. We have the boundary that intersects the event horizon in a 2-sphere, and we also have the boundary that's way out at infinity. So next, we're going to go ahead and evaluate this integral over the boundary, and we're going to split it up into 2 terms, the integral over the 2-sphere that intersects the event horizon, and the integral over the surface that lives way out there at infinity. So now that we have equation 5, we can go ahead and bring in the concept of mass using what's known as the Komar mass formula. So to do that, the first thing we want to do is write equation 5, but on the left-hand side, we're going to break up that integral over the 2-dimensional boundary of our hypersurface S into its 2 constituent parts. One of them being an integral over the boundary that intersects the event horizon, that 2-sphere, and then the other part of that boundary is the bubble that we're sending way out to infinity. So the left-hand side is still the same thing as before, but just broken up into the 2 different parts of the boundary of our hypersurface S. Now this is where the Komar mass formula comes in. You can see Poisson 4.86 for more information on the Komar mass formula, or you can look it up if you want to read more about it. But the basic gist of the Komar mass formula is that if you have a stationary spacetime, like what we're dealing with here, then the mass contained within that spacetime can be calculated in terms of a flux integral at the boundary of that spacetime, as shown here. And specifically, what we're integrating over is the derivative of a time-like killing vector contracted with the directed area element of our surface. Now, for the purpose of this paper, we're just going to go ahead and import the Komar mass formula. We'll take it as a given. But by way of analogy, one way to think about this is it's sort of like Gauss's law for electricity, wherein the charge contained within a bubble is equal to the flux of the electric field through that bubble. In fact, you can write Gauss's law for electricity using the similar kind of notation that we've written here, and you see that there's actually a deep structural similarity between the Komar mass formula and Gauss's law of electricity. The reason I bring that up is you can think about, in general relativity, assuming you're dealing with a stationary spacetime, and thinking about how much mass is contained within a space-like hypersurface, well, the amount of mass is going to be encoded on the boundaries of that surface as the flux of the derivative of the time-like killing vector through that surface. And so that formula, that Komar mass formula, is what's going to allow us to bring mass into our analysis. You see, because if you compare this formula to the second integral in the left-hand side of our equation, you see that there's a match, up to a factor of -4 pi. But okay, so let's go ahead and rewrite our equation as an integral over the part of our boundary that intersects the event horizon minus 4 pi m, where m is the Komar mass. And then on the right-hand side, we just bring down what we had before. Well, then now all we have to do is scoot some things around, and we can write the mass of our system in terms of an integral over our space-like hypersurface of the Ricci curvature tensor contracted with our time-like killing vector and the oriented volume element within our hypersurface, and an integral over the boundary of the hypersurface that intersects the event horizon of the derivative of our time-like killing vector contracted with the two-dimensional area elements of that two-sphere boundary. And so because we're able to bring in the Komar mass formula and do that move, the paper goes on to say, for an asymptotically flat space, the integral over the infinite bubble part of the boundary of S in equation 5 is equal to -4 pi m, as we've seen, where m is the mass as measured from infinity. That is, suppose you're way out away from the black hole, looking at the situation and saying how much mass is there. Well, that's going to be the Komar mass m. Thus, the paper goes on to write equation 6, which is very similar to what we've just written here in our little note bubble at the bottom of the screen. However, you'll notice that there is one important difference, which we're going to get into in just a moment, which is that the Ricci curvature tensor in our equation has been replaced in equation 6 with some terms involving the stress energy tensor T. But that's okay because we know from the Einstein field equations that there's going to be a relationship between R and T. And so all we have to do to get equation 6 is take what we have so far, apply the Einstein field equations, and write that first integral in terms of T. And we'll do that in just a moment, but first I want to look at what exactly these two integrals are in equation 6. Well, the first integral can be regarded as the contribution to the total mass of the matter outside the event horizon, and the second integral may be regarded as the mass of the black hole. Now, why is that? Well, because look, equation 6 is a formula for the mass. One of them is an integral over the space-like hypersurface outside the event horizon, and the other one is the integral over the boundary of that hypersurface, which intersects the event horizon. And so, yeah, the equation naturally breaks up into the contribution from the mass outside the event horizon, as well as the mass of the black hole, which is apparently encoded in this integral over the boundary of the hypersurface S that intersects with the event horizon. All right then, so before moving on, the last thing we have to do is show how the equation that we derived a moment ago involving the Ricci curvature tensor can be massaged into the first integral of equation 6. So let's go ahead and do that. It's just a matter of applying the Einstein field equations, neglecting the cosmological constant. That is, we're imagining asymptotically flat spacetime. And so we have that the Einstein curvature tensor is equal to 8 pi times the stress energy tensor. Now here we've gone ahead and written out the Einstein curvature tensor in terms of its definition as the Ricci tensor minus 1/2 times the scalar curvature times the metric. And you can see this equation in the paper right after equation 6. So now the first move I want to do is to compare the scalar curvature, which remember is the trace of the Ricci curvature tensor, to the trace of the stress energy tensor T. So if you take the Einstein field equations, and for all the terms in the equation, let's go ahead and slap on the inverse metric. That gives us the equation shown here. Now this first term here, G upstairs AB, R downstairs AB, that is the definition of the scalar curvature R. So think of that term simply as R. Then on the second term, we have a contraction of G upstairs AB and G downstairs AB. So we have every component of the inverse metric times every corresponding component of the metric summed over for all possible components. Now, because of the definition of the inverse metric relative to the metric, this contraction is actually going to be the trace of the 4x4 identity matrix. So therefore, we're going to have 1 plus 1 plus 1 plus 1, which equals 4. So that second term is negative 2r. Then on the right side of the equation, 8 pi g upstairs AB, downstairs TAB, that is simply going to be the trace of the stress energy tensor T. So we can replace GAB TAB with simply the letter T. So then on the left side, we have r minus 2r, which is negative r, and on the right side, we have 8 pi t. Therefore, we can write r equals negative 8 pi t. That is to say, the trace of the Ricci curvature tensor is going to be negative 8 pi times the trace of the stress energy tensor. Now then, using that fact, we can return to the Einstein field equations and substitute for the scalar curvature r, negative 8 pi t. And then the negative 1/2 and the negative 8 crunch together and give us a 4. Then we scoot that over to the right side of the equation and we get a negative 4. So we see that the Ricci curvature tensor is 8 pi times the stress energy tensor minus 4 pi times the trace of the stress energy tensor times the metric. From there, all we have to do is raise the A index, and we end up with the expression shown here. So we raise the A index on R, we raise the A index on T, and when we raise the A index on the metric, we end up with the Kronecker delta. So then when you consider this, you see that all we've done here is we've massaged the Einstein field equations to turn an expression involving R upstairs A, downstairs B, into an expression involving T. And if you look at the integral over the space-like hypersurface of equation 6, you find that's exactly the expression they have. So that's how we get to equation 6. Okay, so if you think back to what we just did, we started with equation 3, we integrated that to get equation 5, and then we applied the Komar mass formula and the Einstein field equations to get to equation 7. And now we're going to do basically the same thing all over again, but for angular momentum instead of mass. And this time we're going to go through it more quickly because it's literally pretty much the exact same thing, but instead of starting with equation 3 for our time-like killing vector k, we're going to start with equation 4 for our rotational killing vector k tilde, and then we're going to use that along with the Komar formula for angular momentum to arrive at an expression for the angular momentum. And as we do this, you're going to be like, whoa, I've seen this before. Déjà vu. It's the same thing. So check it out. First, we're going to start with equation 4. Now go ahead and integrate both sides of equation 4 over the space-like hypersurface S outside the black hole, and then apply Stokes Theorem to the left-hand side. And that gives us an equation that let's go ahead and call 5 tilde, because you'll see this is exactly the same thing as equation 5, but the only difference is that now it pertains to our rotational killing vector, k tilde, instead of our time-like killing vector, k. So now what is our next move? Well, let's go ahead and write out the Komar formula for angular momentum, see Poisson 4.87, and that is the statement that the angular momentum contained within our space-like hypersurface can be written, much like for the Komar mass formula, as a flux integral of the derivative of our rotational killing vector contracted with the oriented surface elements of the infinite bubble boundary of our hypersurface. And so spiritually, the Komar angular momentum formula is very similar, in many ways the same, as the Komar mass formula. But whereas for mass we had a time-like killing vector giving rise to the mass, here we have a rotational killing vector, k tilde, and so that is going to give rise to the angular momentum, j. From here, the derivation proceeds exactly as before. On the left-hand side of equation 5 tilde, imagine breaking that up into two integrals, one integral over the surface of the two-sphere that intersects the event horizon, and another integral over the infinite bubble. But then, doing some pattern matching with the Komar angular momentum formula, we can write that second integral simply as 8 pi j, where j is the angular momentum contained within our space-like hypersurface. And then on the right-hand side, we simply have the right-hand side of equation 5 tilde. And now all we have to do is scoot some things around and divide by 8 pi, and we have the equation shown here, where we've expressed the angular momentum contained within our space-like hypersurface in terms of an integral over the space-like hypersurface S outside of the event horizon, as well as an integral over the surface of the event horizon. So this is exactly the same thing as we saw before. And then, just as we did before, the last move simply involves converting that curvature in our hypersurface integral into a term involving our stress-energy tensor. And how do we do that? Well, we apply the Einstein field equations. So if you think about the Einstein field equations, and go ahead and slap a factor of k tilde onto both sides, you see we have the equation shown here. Now notice here we have mixed indices on our tensors, an upstairs A and a downstairs B. And that's all good. All we've done is we've raised the A index on the Einstein field equations. So we have the Ricci curvature tensor upstairs A, downstairs B, minus 1/2 the scalar curvature, and whereas before when everything's downstairs, we would have GAB, when you raise an A index, and you think about the way the metric and the inverse metric give you a Kronecker delta, you see that the metric term is simply the Kronecker delta of A and B, which equals 1 when the indices A and B are the same, and is otherwise equal to 0. And then on the right side of the equation, we have a T upstairs A, downstairs B. So that's the Einstein field equations with the A index raised, and then we've contracted everything on both sides with our rotational killing vector, k tilde, upstairs B. So now let's go ahead and scoot things around, move that scalar curvature term on over to the right side of the equation, and while we're at it, we'll contract the Kronecker delta with the k upstairs B, and you think about how the Kronecker delta turns off all the possibilities for which B is not equal to A, and then you see that the scalar curvature term simply becomes 1/2 r k tilde A. Now if you look at the left side of that equation, you see we have an r upstairs A, downstairs B contracted with k tilde upstairs B. But that's exactly what we have in our integral over the hypersurface S. Right, so that's the term that we want to massage into the stress-energy tensor term of equation 7. And we almost have it, because if you look at the right side of this equation, you see that we have an 8 pi T upstairs A, downstairs B, k tilde B, which is exactly what we want to have in order to get equation 7. So all that remains is to show that that scalar curvature term goes away. Now on its own, this expression 1/2 r k tilde A is not necessarily equal to 0. In fact, in general, it's not equal to 0. However, if you integrate that term over our space-like hypersurface S, the integral does in fact equal 0. The reason why is that our rotational killing vector k tilde is tangent to S, right? Because if you flow along the rotational killing field k tilde, you're just circling around in our hypersurface by definition. You're not poking out of S. And so if you think about our oriented volume element, d sigma A, as a time-like normal vector that encodes the direction in spacetime orthogonal to our hypersurface, times a volume element dv, and then you think about the fact that because k tilde is tangent to S, the contraction of that normal vector with k tilde has to equal 0, then you realize that the contraction of k tilde with our oriented volume element equals 0. So therefore, when you integrate that scalar curvature term over our space-like hypersurface, it equals 0, so that term vanishes, and then all that's left is equation 7. Well, all right then, so what is the big picture here? What have we done? Well, we started with equation 4. We integrated it over the space-like hypersurface S outside the black hole. We applied Stokes Theorem to write the left-hand side in terms of an integral over the boundaries of the hypersurface. Then we applied the Komar angular momentum formula to recognize the integral over the infinite bubble as the angular momentum contained within the space-like hypersurface. And then we scooted some things around and converted a curvature into a stress-energy tensor using the Einstein field equations, and we ended up at equation 7. And when you interpret equation 7, what do you find? Well, you find that the first integral on the right-hand side of equation 7 is the angular momentum of the matter outside the black hole, and the second integral can be regarded as the angular momentum of the black hole itself. And as you can see, this is very much exactly the same thing as we saw before when going from equation 3 to equation 5 to equation 6, but the only difference now is we've used the rotational killing vector, k tilde, rather than the time-like killing vector, k, and as a result, we've ended up with an expression for the angular momentum as opposed to the mass. But you see how these two lines of reasoning are very much in parallel with each other. It's pretty much the same thought process in both cases. The paper then goes on to define a time coordinate t, as well as a null vector L, which is tangent to the generators of the event horizon. One can introduce a time coordinate t, which measures the parameter distance from our hypersurface S along the integral curves of our time-like killing vector. In other words, the gradient of t contracted with the Killing vector is 1. Which is to say, if you imagine any point in the hypersurface S, and then extrude from that point along the integral curves of the time-like Killing vector, so you flow along k away from our hypersurface S, then however much distance you go along that integral curve, that distance, by definition, is going to be our time coordinate t. And so that definition of t is sort of, in a way, kind of tautological, because it comes sort of right out of the definition of our time-like Killing field. When you think about the way in which flowing along k is going to flow us forward in time. Now then, the null vector L, which is tangent to the generators of the horizon, can be expressed as L equals k plus omega h k tilde, where omega h is the angular velocity of the black hole, and is the same at all points of the horizon. See reference 9 for more information on that. So what exactly is L? Well, to see what this is, first imagine the simple case when omega h is 0. That is, we have a Schwarzschild black hole, which is not rotating. Well then in that case, L is just going to equal k, the time translational Killing vector, and on the horizon, you can think of that as the direction in spacetime of a photon that is trying as hard as it can to escape outwards away from the black hole, but because it's right on the event horizon, it remains forever in place as viewed from outside. So the photon might think it's going forward. It's like, I'm a photon, I'm going forward, that's what I do as a photon. But if you think about it from the perspective of someone outside the black hole, the photon is going to be stuck right there on the event horizon. If you want to think about it from the perspective of the space-time waterfall picture, which you got to take with a grain of salt because it's not exactly right, but it's kind of right, then if the horizon is the place where the waterfall is coming in at the speed of light, of course a photon is always going to be stuck there, never able to escape. Now, when omega h is not equal to 0, the picture becomes more complicated, because now we have a rotating horizon. And so now, in order to be tangent to the generators of a rotating horizon, you can imagine a photon that's trying to escape, but it has to rotate with the horizon in order to be tangent to the generators of the horizon. Think about it like this. If you look at equation 8, you can see that for every 1 unit of k, we have omega h units of k tilde. That is, for every 1 unit of the passage of time, we have omega h units of rotation around the black hole. And so what is it called when you have omega h of rotation per 1 unit of time? Well, that's called an angular velocity. And so that's going to be the angular velocity of the event horizon. Another way to think about this, and an important fact about equation 8, is that L, the null Killing vector generating the rotating event horizon, is the unique combination of time translation and axial rotation, which is null, or light-like, on the horizon. So if you imagine the generic set of 4 vectors, a times k, plus b times k tilde, you'll find that the only vector that's light-like is going to be that given by equation 8, k plus omega h k tilde, or a scalar multiple thereof. Right, because if you scale up and down the vector, that doesn't change whether or not it's null, but you can see that the simplest definition of this vector is simply that which is given in equation 8. Alright, so now using this definition of L, the paper goes on to say a few things. And I'm going to say these quickly just to get them out on the screen, and then we're going to pause and investigate why this is the case. Alright then, using L, one can rewrite equation 6, which is an expression for the mass involving an integral over the hypersurface S outside the black hole, as well as an integral over the event horizon, as the form shown in equation 9, in which that second integral, the one over the 2-sphere of the event horizon, has been replaced with the quantity 2 omega hjh plus an integral over the horizon's 2-sphere of L upstairs A semicolon B contracted with the surface element d sigma AB. Now in equation 9, the quantity jh is the angular momentum of the black hole, as we saw earlier when we were looking at equation 7. Because if you look at the second part of equation 7, you see exactly the integral shown here for the definition of jh, which is negative 1 over 8 pi, times the integral over the 2-sphere of the horizon of k tilde upstairs A semicolon B contracted with d sigma AB. Okay, so now let's pause and think about why that's the case. How do we get from equation 6 to equation 9? Well, we simply use equation 8. So first of all, if you look at the second integral of equation 6, you see that it involves our killing vector k. Now then, by equation 8, if you subtract omega h k tilde from both sides, you see that you can replace k with L minus omega h k tilde. Well then, having made that substitution, we can go ahead and split up the integral into two integrals, like so. And then if you look at that second integral involving omega h and k tilde, well then by equation 7, you can recognize that integral as 2 omega h jh. So that is how we go from equation 6 to equation 9. Okay, so what's the big deal about equation 9? Why do we care about equation 9? What is it going to tell us? Well, we can learn about the surface gravity, Kappa, at the event horizon. So in order to get into the surface gravity, first, let's go ahead and write out equation 9, like so. Now, if you look at the last term of equation 9, we have an integral over the two-sphere of the event horizon, and so therefore, one can express the directed area element d sigma AB as this antisymmetric product involving LA and B, dA. So essentially the wedge product of L and N times an area element, where N is the other null vector orthogonal to the surface, and normalized such that N contracted with L is equal to -1. And dA is the surface area element of the two-sphere of the horizon. So the way to think about N is that if you're right there on the event horizon of a rotating black hole, well, as we've seen, there's going to be a vector tangent to the generators of the horizon, that is L, so that L points in a specific direction in spacetime. But then you're also going to have the two-sphere of the event horizon, and at some point on the horizon, you can imagine the tangent plane to that two-sphere, and that plane is going to span two additional dimensions that are orthogonal to L. And so then, if you think about the direction that L is pointing, as well as the plane that's tangent to the two-sphere, you see that's 3 dimensions, but we have a 4-dimensional spacetime, and so therefore there's going to be another null vector, which is orthogonal to that tangent plane, that will then give us a complete set of ways to point all the different directions in spacetime on the event horizon. And by the way, in just a moment, we're going to define an entire null tetrad on the horizon using this L and this N, as well as the complex conjugate null vectors M and M bar. We'll get into that in just a moment. But for now, the important thing to see is that d sigma AB is simply an area element of the two-sphere of the horizon times the wedge product of L and N. And so we have a sort of oriented area element d sigma AB. Okay, so now the paper goes on to make a very interesting observation, which is that the right term of equation 9 can be written as 1 over 4 pi times the integral over the two-sphere of the event horizon of kappa dA, where dA is an area element, and kappa, the surface gravity, is defined as -L downstairs A semicolon B contracted with N upstairs A, L upstairs B. And one way to think about the surface gravity kappa is that it represents the extent to which the time coordinate t is not an affine parameter along the generators of the horizon. In just a moment, we'll get into what that means, but first, let's go ahead and demonstrate that the last term on the right of equation 9 can indeed be written as 1 over 4 pi times the integral of kappa dA. Well, to do that, all we have to do is write out the last term of equation 9, and then we can go ahead and write out our surface element, d sigma AB, as its definition in terms of an antisymmetric product of the covectors L and N, times an area element, dA. So then recalling the meaning of those antisymmetrization brackets, that means you take the thing minus the thing with the indices switched around, divided by 2. So the 1 over 4 pi becomes a 1 over 8 pi from the 1/2 in the definition of antisymmetrization, and then we also have LANB minus LBNA. Now our next move is to use Killing's equation, with the indices raised upstairs, to leverage the fact that because L is a Killing vector on the horizon, L upstairs A semicolon B equals -L upstairs B semicolon A. So we can use that antisymmetry to simplify our integrand. To see how this works, we can write out our integrand like so. having distributed through the L upstairs A semicolon B. And then for the right term, you'll notice that we've done an index swap for A and B. Now that's a legit move because everything contracts on that term, and we end up with a scalar quantity. So we don't have to worry about having relabeled any free index or anything like that. But no, it's all self-contained, and so we're able to do that index swap, and it doesn't change anything. But then, using that anti-symmetry property that comes from Killing's equation, we can transform that L upstairs B semicolon A on the second term into a negative L upstairs A semicolon B. When we do that, the two minus signs annihilate each other, and then you see that the first and second terms are the same, and so we simply have twice that term. And so actually our integrand can be written in the simpler form shown here. Now we can go ahead and massage this into the definition of kappa by doing an index swap on this term, and then once again swapping the indices back on only the L term, thereby picking up a minus sign. And then the final maneuver is to go ahead and lower and raise indices as shown here, which is exactly equal to what we had before, just written in a slightly different way. So then, if we go ahead and pop our integrand back into our integral, you see that we have the integral shown here, and by inspection, you can see that this does indeed equal 1 over 4 pi times the integral over the 2-sphere of kappa dA, where kappa, as you can read from this integral, is necessarily negative L downstairs A semicolon B, contracted with the vectors n upstairs A, L upstairs B. And so that is how you transform the last term on the right of equation 9 into this integral involving the surface gravity of the black hole. Alright, so now let's talk about this comment about kappa representing the extent to which the time coordinate t is not an affine parameter along the generators of the horizon. First, we'll talk about this mathematically, and then we'll talk about a way to think about it visually. So if you look at our definition of kappa, which is negative L downstairs A semicolon B, n upstairs A, L upstairs B, you should know that this definition of kappa is often written as L upstairs A downstairs semicolon B, L upstairs B equals kappa L upstairs A. See, for example, Poisson equation 5.41. To see that these two equations are the same, it's easiest if we work backwards. Starting off with Poisson equation 5.41, we can contract both sides with the covector n downstairs A. Then on the right-hand side, you see that we have kappa, L upstairs A, and downstairs A, but we know that if you contract the vector L with the covector n, that always equals negative 1, by the normalization condition in the definition of n relative to L. So then on the right-hand side, we have a negative kappa. Switching things around and moving around the minus sign, we have that kappa equals negative L upstairs A, downstairs semicolon B, L upstairs B, and downstairs A. Kind of a mouthful. But in any case, that expression is equivalent to the same thing, with the A's and the B's raised and lowered like so, which is exactly equal to our definition of kappa. Now the reason I mention Poisson equation 5.41 is because if our time coordinate t were an affine parameter along the generators of the horizon, then, by Poisson equation 1.14, we would have that L upstairs A downstairs semicolon B contracted with LB equals 0. Now, if you're interested in the technical details of where that equation comes from and how it relates to an affine parameter, and like what even is an affine parameter, then you want to see Poisson 1.14 and in general Chapter 1. But in any case, we then see in Poisson 5.41, which is equivalent to our definition of kappa, that the right-hand side, rather than being 0, is equal to kappa times our null vector L, and that is very much not 0. And so that is the precise mathematical sense in which the surface gravity kappa represents the extent to which the time coordinate t is not an affine parameter along the generators of the horizon. So that's a bit of math, but visually what does this mean? How can we interpret the geometry of the situation? Well, the paper goes on to say that one can think of kappa as the surface gravity of the black hole in the following sense. A particle outside the horizon, which rigidly co-rotates with the black hole, has an angular velocity of omega sub h, the angular velocity of the event horizon, and a four-velocity v, which is given by k plus omega h k tilde, scaled by a time dilation factor vt. That is to say, if you're a little particle and you're right outside the event horizon, and you're rotating along with the event horizon, then, for the same reason equation 8 is true, your forward velocity is going to be this combination of our time-translational killing vector k with your rotational killing vector k tilde, and then all of that's going to be scaled by a gravitational time dilation factor vt. Now then, the acceleration forward vector is given by the covariant derivative of va along the b direction, contracted with vb. So that formula is how you go from a forward velocity to a forward acceleration. Now then, if you think about the magnitude of the acceleration of this particle, multiplied by the inverse of this time dilation factor, to convert from change in velocity per unit proper time to change in velocity per unit coordinate time t, that is going to tend towards the surface gravity kappa when the particle is infinitesimally close to the event horizon. Now there's a subtlety here, which is that we're imagining a particle which is infinitesimally close to the event horizon, but not exactly on the horizon. And that's because if we were exactly on the horizon, then our time dilation factor blows up and becomes infinite. And so you have to imagine we're ever so slightly outside of the horizon, so our time dilation factor remains finite, and that way we're able to convert between the change in velocity as viewed from the particle, that is per unit proper time, to the change in velocity as viewed from way outside the black hole, that is the change in velocity per unit coordinate time. And so all that's to say, if you're this particle that's really close to the horizon and rotating around with the black hole, and you think about what is the magnitude of your acceleration as measured by a clock that's far from the black hole, well, that acceleration is going to converge towards the surface gravity kappa when you're right up next to the event horizon. All right, so that's the definition of the surface gravity kappa, and next we're going to go ahead and prove the 0th law of black hole mechanics, which is that the surface gravity kappa is constant everywhere on the event horizon. And this is going to be a very deep and a very profound result. All right, so next up, we're going to prove that the surface gravity kappa is constant everywhere on the event horizon. To do this, we're going to use a null tetrad, comprised of L, which is a null vector tangent to the generators of the horizon, as well as another null vector n pointing the other way, and then we're going to span the plane tangent to the two-sphere of the event horizon with the complex conjugate null vectors m and m bar, like we saw earlier during our warm-up. So now our goal is to prove the 0th law of black hole mechanics, that is, the surface gravity kappa is constant on the event horizon. To do this, we want to prove that the covariant derivative of kappa contracted with m equals 0. See, because if k downstairs semicolon a, m upstairs a equals 0, then what that means is that the way in which the surface gravity kappa changes from one point in space-time to another doesn't project at all onto the plane that's tangent to the event horizon. And by rotational symmetry, you see that if this statement is true, then it follows that kappa is going to remain unchanged as you move around on the two-sphere of the event horizon, which is to say that the surface gravity kappa is constant on the event horizon. So, to prove the 0th law, all we have to do is evaluate this expression, k downstairs semicolon a, m upstairs a, and prove that it equals 0. Well, to do that, the first thing we can do is go ahead and write out kappa in terms of its definition as negative L downstairs A semicolon B, contracted with N upstairs A, L upstairs B, as we saw earlier. Now you'll notice here that when substituting in that definition of kappa, because we already used the A and B indices for that definition, we're going to go ahead and pull that in, and then change that green index from an A to a C. So of course this is totally a legitimate move, because it doesn't matter what we call our indices, so long as we keep track of which is which. So now the next move is to evaluate that covariant derivative, semicolon C, by using the product rule to expand things out like so. So all we've done here is we've distributed that covariant derivative along the C index onto each of the three terms in our definition of kappa. Now let's go ahead and address each of these three terms one at a time. Well, first of all, because L is a killing vector on the event horizon, the expression L downstairs A semicolon BC can be written in terms of the Riemann curvature tensor contracted with L upstairs D. To see why this is, you want to check out Poisson equation 5.99 and also problem 9 in the problem set for section 1.13. Now in Poisson, the order of these indices is a little bit different, but by the symmetry and antisymmetry of the Riemann tensor under index swapping, you can show that R dCBA is actually the same as R ABCD. So with that in mind, you'll see that the equations in Poisson actually do map on to this statement here. But for now, let's go ahead and import this as a mathematical fact about killing vectors in curved spacetime. Well then, we can apply this fact in order to rewrite our first term like so, having replaced the L downstairs A semicolon BC with this expression involving the Riemann curvature tensor contracted with the upstairs LD. From there, all we have to do is relabel dummy indices, swapping A and D, as well as B and C, to put that first term in the form that appears in the paper. Alright then, so that's the first term in our product rule expansion of this derivative. Next, what we want to show is that the second and third terms are going to cancel each other out, so that all we're going to end up with is the first term on its own. Now, in order to show that the second term and the third term cancel each other out, we're going to massage both of them into the same form. At this point in the paper, they invoke the fact that the metric can be reconstructed from the null tetrad, as shown here, and as we talked about earlier. And this fact sort of defines and reminds us of the normalization conditions and the definition of our null tetrad. And we'll use that fact in just a moment. But actually, the first thing I want to do is look at that second term, and just go ahead and rewrite it like so, by scooting that L upstairs B on over towards the L downstairs A semicolon B. So you see, we've done nothing here other than moving some terms around. And everything here commutes, so that's all good. And the reason we wrote things like so is because now we can recognize L downstairs A semicolon B contracted with L upstairs B as the surface gravity kappa times L downstairs A. To see why that's the case, you can see Poisson 5.78, which tells us that L upstairs A downstairs semicolon B, L upstairs B, is equal to kappa L upstairs A. So you can take that, lower the A index on both sides, and then you end up with the equation shown here. Regarding why Poisson equation 5.78 is true, well, there's a lot of technical details behind the scenes there, but it essentially boils down to the fact that the surface gravity kappa represents the extent to which the time coordinate t is not an affine parameter along the generators of the event horizon. So Poisson 5.78 follows from the definition of the surface gravity kappa. Well, alright then, we can go ahead and make that substitution and write the second term like so. Alright, so now if you look at this expression, we have an L downstairs A contracted with a covariant derivative along the C index of N upstairs A. And when you think about the fact that L contracted with N is equal to -1, you think, oh, maybe there's a way we can somehow simplify that expression. But then you think about it and it's like, well, actually the covariant derivative only applies to N, and so it's not actually L contracted with N, it's L contracted with the derivative of N. But then it's like, wait a minute, what about the product rule? See, because one thing we can say for sure is that the covariant derivative of L contracted with N is going to equal 0, because L contracted with N is just -1 by the definition of our null tetrad, and the derivative of a constant is 0. So we know for sure that the covariant derivative of L contracted with N is 0, so then by the product rule, if we expand that out and scoot one of the terms on over to the other side of the equation, we can show that L contracted with the covariant derivative of N is equal to -L downstairs A semicolon C, N upstairs A. And now we can use that fact to rewrite our expression like so. You see, because on the left side here, that's just the second term that we've been looking at. And then on the right side of the equation, we've gone ahead and substituted this insight that came from this insight about the covariant derivative of L contracted with N being 0. So, having massaged the second term into that form, all we have to do now is show that the third term equals the negative of that form, so that the second and third term cancel each other out. Alright then, now let's go ahead and deal with the third term. At this point, the paper mentions that on the event horizon, we have a vanishing of the shear and the convergence of the horizon generators, and these facts are encoded in the equations shown here. Now before we take these equations and run with them, I want to say a few words about what they mean geometrically. So if you picture the event horizon, it's a null surface threaded by null generators. Topologically, imagine the two-sphere of the event horizon, and at each point you have a null generator growing out of the two-sphere, sort of like the hair on your head, if your head were a complete two-sphere. But in any case, if you pick a little patch of the two-sphere, and imagine a bunch of neighboring generators passing through that patch, well, as you flow along L, that is the vector tangent to the generators of the horizon, so tangent to these geodesic null generators, then that bundle of generators could potentially do a few different things. The generators could expand or contract, or the bundle could shear, meaning that it stretches in one direction and squeezes in another. So imagine you have a circular bundle of straws and you squeeze them into an elliptical bundle. That would be shear. Or the whole bundle could twist and rotate around. But on a stationary event horizon, none of these things happen. In fact, the horizon generators are perfectly rigid in the sense that they maintain their spacing and their shape as they flow along. So mathematically, we can encode these conditions in terms of how the vector L tangent to the generators of the horizon changes as we move across the two-sphere. By the definition of our null tetrad, the two-sphere directions are spanned by our complex conjugate null vectors m and m bar, and the convergence is given by the first expression here, L downstairs A semicolon B contracted with m upstairs A, m bar upstairs B. That quantity represents the isotropic expansion or contraction of our little bundle of generators that we're looking at on a patch of the two-sphere. And so by the fact that our generators neither converge nor diverge on the horizon, that has to equal 0. Likewise, the shear is represented by the other term, L downstairs A semicolon B contracted with m upstairs A, m upstairs B. That measures the anisotropic distortion, the squeezing of a circle into an ellipse. And by the vanishing of the shear on the horizon, that also has to equal 0. Now, one of the consequences of the vanishing of the shear and the convergence on the event horizon is that the expression L upstairs B downstairs semicolon C contracted with m upstairs C is going to be directly proportional to L upstairs B. Let's use the real number lambda for the proportionality constant. Now, what this equation means is that if we nudge sideways a little bit across the two-sphere of the horizon in the MC direction, then the covariant derivative of L along the C spacetime index, contracted with m upstairs C, encodes how the generator L changes as we nudge a little bit along the horizon. Now, by the vanishing of the shear and the convergence, we know that the null vector L tangent to the generators of the horizon is not going to pick up any component in the m or the m bar directions that are tangent to the two-sphere. And it also can't pick up a component along n, because that's on the other side of the light cone. And so the only possibility we have left for how the generator can change as we move along the horizon is that the change has to be proportional to the generator direction itself. And that is what this equation with the lambda means. And likewise, we can go ahead and lower the b index on both sides, and the equation is still true. Now let's go ahead and isolate this proportionality factor lambda by contracting both sides of our equation with the null vector n upstairs b. That gives us the equation shown here. All right, now with this equation for lambda, notice what we can do. Consider the third term in this big equation that we've been analyzing. That is negative L downstairs A semicolon B, n upstairs A, L upstairs B downstairs semicolon C, m upstairs C. Well, by pattern matching and using our equation for lambda with some indices raised, you'll notice that we can write that third term in terms of lambda and L and n and L, like so. But then, if you look at that expression and recall the definition of kappa, you realize, oh, that's lambda kappa. So the third term that we've been looking at is this proportionality factor lambda times the surface gravity kappa. Wow, that really simplified nicely. But it gets even better, because now let's go ahead and unpack lambda in terms of L and n and m, like we saw just a moment ago when we solved for negative lambda, and we can go ahead and write our third term in the form shown here. And now at this point, you'll notice, hey, we've put our third term into a form that is exactly equal and opposite to the second term. And so the second and third terms cancel each other out. Woohoo! And that means that this whole equation, the derivative of the surface gravity along the direction m on the horizon, is only given by this first term, which we've written in terms of the Riemann curvature tensor as well as L and M and N. And that is how we get to equation 11. So just a big picture reminder of what we're doing here. This term kappa downstairs semicolon A contracted with M upstairs A is the way that the surface gravity changes as we move along the two-sphere of the event horizon. Our goal is to show that that quantity is zero, because if that's the case, then that demonstrates that the surface gravity kappa does not change as we move along the horizon. And so that's why we've been evaluating this expression and trying to put it in the simplest possible form to show that eventually everything's going to go away. All right, so now let's work towards getting equation 12. To do that, let's recall that on the event horizon, our generators neither converge nor diverge, and so the convergence given by L downstairs A semicolon B contracted with M upstairs A M bar upstairs B equals 0 everywhere on the horizon. And so therefore what also equals 0 is this more complicated expression shown here, which you can interpret as the way the convergence of the generators changes as we move along the horizon. Well, that doesn't change as we move along the horizon because the convergence is 0 everywhere. So we know that this has to equal 0. But then this thing that has to equal 0, we can rewrite in a different way using the fact that L is a Killing vector, and so therefore L downstairs A semicolon BC can be written as a contraction of the Riemann curvature tensor with L. Now technically we have to do a product rule here on the left side of equation 12, but when you break this out into two pieces, you see that the second term is going to go away by the fact that the horizon generators have 0 convergence on the event horizon. So then it's simply a matter of replacing L downstairs A semicolon BC with the Riemann curvature tensor contracted with L. Okay, so now we've derived equation 12, which is that this expression shown here with the Riemann curvature tensor contracted with L and M bar is equal to 0 by the vanishing of the convergence of the generators on the event horizon. Now this fact is ostensibly independent of the derivative of kappa that we've been evaluating. However, the reason we bring this up is because we're going to use the fact that this equation is equal to 0 to show that the remaining term in equation 11 is equal to 0, and therefore that the surface gravity is constant on the event horizon. So that's why we've derived equation 12. The paper goes on to write equation 12 in the form shown here, with one term involving the Ricci curvature tensor and another term involving the Riemann curvature tensor. So let's take a moment to see how we're able to modify equation 12 in that way. Well, really, it all comes down to this concept of the reconstruction of the metric from the Null tetrad. So this is the concept that relates the metric tensor, GAB, to the sum over the various products of the downstairs components of N and L and M bar. So now if we take that equation and raise up all the indices, and then move the MA M bar B term onto the left side, while moving the G term on over to the right, and multiplying everything through by a -1, we get the equation shown here. So you can see that we can write M upstairs A times M bar upstairs B as the metric plus these expressions with N and L and M bar and M. So then if we take equation 12, and you notice that it contains M upstairs A times M bar upstairs B, well then use the equation we just derived, and you can expand that out like so. Now I know this is quite a mess, but fortunately only the first two terms are non-zero, and the second two terms are both 0. So first of all, if you look at this first term here, when we contract the Riemann curvature tensor R downstairs ABC with the inverse metric G upstairs AB, that's going to pop up an index on the Riemann curvature tensor, and when we evaluate R downstairs DABC contracted with G upstairs AB, that is going to equal -RDC. So we're doing a contraction of the Riemann curvature tensor and getting the negative of the Ricci curvature tensor. So if you take that term, -RDC, and bear in mind we're contracting this with L upstairs D times M upstairs C, so we can go ahead and take that and then just do a dummy index relabeling, swapping B and C, and that's exactly the first term in this modification of equation 12 in the paper. Alright then, so for the second term, you can see that it's basically exactly what we already have for the second term that we're looking for, but we just have to do a little bit of index gymnastics. So the first move is to notice that we have two factors of L. We have L upstairs D and L upstairs B. Therefore, if we take our expression and do a dummy index relabeling, swapping D and B, well then we end up with R downstairs BADC, and you would think that we would have LB and then LD, but those things commute, and so we may as well keep the LD and LB in place. So this lets us effectively swap the first and third indices on our Riemann curvature tensor, which in general is not a symmetry of the Riemann curvature tensor, but in this context, when you evaluate the full contraction, and because of the fact that the L vector appears here twice, then the full object does in fact have symmetry under the exchange of B and D. So then the next move in our gymnastics routine is to swap the indices A and D, as well as B and C. And this is just a dummy index relabeling, so that's all good. That's a passive move. And then finally, by the pair swap symmetry of the Riemann curvature tensor, see Poisson equation 1.33, we can swap the pairs AB and DC, and then that is going to put our expression exactly in the form of equation 12. So now all that remains is to show that the second two terms are both zero. Well, in the first case, you'll notice that the Riemann curvature tensor is antisymmetric under the exchange of the A and D indices, by Poisson equation 1.33. But at the same time, L upstairs D times L upstairs A is symmetric under the exchange of A and D. So when you think about that and you realize we're summing over all possibilities for A and D, you're going to find that half of them are going to balance out the other half, and they're going to sum up to zero. So that term goes away. And then for the final term, we can apply precisely the same reasoning, noting that R is antisymmetric under the exchange of the B and C indices, and that the product of M upstairs B, M upstairs C is symmetric under the exchange of B and C. And so for the same reason, when we sum over all these possibilities, everything's going to cancel out to zero. So that gets us to the final form of equation 12. Now the paper goes on to invoke the Einstein field equations to say that the Ricci curvature tensor, R downstairs dB, contracted with L upstairs D times M upstairs B, is equal to 8 pi times T downstairs BD, contracted with L upstairs B, M upstairs D. But now you might be thinking, hey, wait a minute, the Einstein field equations, shouldn't we have a scalar curvature term, which involves the scalar curvature R as well as the metric tensor? Well, yeah, we should. But notice that what we've done here is we've slapped on L upstairs D, M upstairs B to both sides of the Einstein field equation. So if you imagine the term that involves the scalar curvature and the metric, then the metric, G downstairs CD, contracted with L upstairs D, M upstairs B, is going to give you an L downstairs B contracted with M upstairs B, that is the inner product of L and M, but by the definition of our null tetrad, L and M are orthogonal, so their inner product is zero. Oh, by the way, you'll notice in the paper, for the final form of equation 12, they write R downstairs dB, but then in the Einstein field equation line, they write R downstairs BD. But because in both cases, we're contracting with L and M, and so D and B are both paired up and summed over, whether we do dB or BD, either way it's the same, so long as we swap everything around consistently. But in any case, from here on out, we're able to replace the Ricci curvature tensor with the energy momentum tensor T. Now the paper then goes on to argue that this term, 8 pi TBD LBMD, is equal to 0, by invoking two principles that I'll mention in passing. The first principle is the dominant energy condition. So the dominant energy condition tells us that for any future-directed null vector, like L, the quantity T downstairs BD contracted with L upstairs B is a non-space-like vector. But then we also know that T downstairs BD contracted with L upstairs B, L upstairs D is 0 on the horizon because of the vanishing of the shear and the convergence of the generators on the horizon. And that fact, technically speaking, follows from a principle known as the Raychaudhuri equation, which in the interest of time we won't get into for now. You can look it up if you're interested. But the long story short is that because on the event horizon of the black hole, the generators have no shear and they have no convergence, then that quantity has to equal 0. So then that tells us that T downstairs BD contracted with L upstairs B is non-spacelike and also orthogonal to the null vector L upstairs D. But the only vectors orthogonal to a null vector that are themselves non-spacelike are either 0 or proportional to L itself. So in either case, this term T downstairs BD contracted with L upstairs B, M upstairs D has to equal 0. Because if T downstairs BD, L upstairs B is 0, then that term is trivially 0. Or the other possibility, if T downstairs BD contracted with L upstairs B is parallel to L, well then in that case the expression is 0 because L and M are orthogonal. So if you contract a quantity that's proportional to L with M, that's going to be 0. So that reasoning turns off the first term in the final form of equation 12, which leaves us with the observation that R downstairs ABCD contracted with L upstairs A, M upstairs B, L upstairs C, N upstairs D has to equal 0. But wait a minute, look at equation 11. That's the same thing, up to a minus sign. And so therefore, the covariant derivative of the surface gravity kappa along the A spacetime index contracted with M upstairs A equals 0. And that's the result we were looking for. Nice. That right there tells us that the covariant derivative of the surface gravity kappa does not point at all in any direction tangent to the two-sphere of the event horizon. That is to say, the gradient of the surface gravity kappa has no component within that two-sphere. And so therefore, we've just proven that the surface gravity is constant all around the event horizon. Now, I guess if we want to be super pedantic, we can also say, well, hey, the surface gravity kappa is also going to be constant along the generators of the horizon, in the sense that if you take the covariant derivative of kappa contracted with L, that is also going to equal 0. And if you like, you can do a very similar argument to what we've just done to show that that equals 0. But there's actually a simpler argument that the surface gravity kappa is constant along the generators of the horizon, and that is stationarity and rotational symmetry. You see, because L is a killing vector, we're going to have symmetry as we flow along it. And so therefore, by the symmetry of the situation, the surface gravity kappa is going to be constant along the generators of the horizon. So when you think about the whole topology of the event horizon as a null surface comprised of a two-sphere, and then at each point on the two-sphere you can imagine these null geodesic curves, these generators of the horizon, well, we've just proven that the surface gravity kappa is going to be constant both around the two-sphere of the horizon as well as along the horizon generators. So everywhere throughout the event horizon, the surface gravity is constant. And that is the proof of the zeroth law of black hole mechanics. Okay, so we've thought about the surface gravity kappa, and we've proven that it's constant on the horizon. Next, the paper goes on to take the integral mass formula of equation 9 and rewrite it in a slightly modified way with some of the insights we've just developed about the surface gravity kappa, and that gives us equation 13. So let's go ahead and talk about equation 13. So now that we have our integral mass formula, given by equation 13, let's take a moment to interpret this formula and figure out what it means, and what it can tell us. Well, we have the formula shown here, involving an integral over the spacelike hypersurface outside the event horizon, as well as some terms involving the angular velocity and angular momentum and surface gravity and area of the event horizon. And you'll notice that this equation can be thought of in terms of two parts. One, there's the part involving the matter outside the black hole, so that's that integral over the spacelike hypersurface. And then the rest of it, the omega h, jh, kappa, a, those terms pertain specifically to the black hole. And so, when t equals 0, that is, when the space outside the event horizon is empty, this formula, equation 13, reduces to that found by Smar for the Kerr solution. And you can read more about that in reference 7. But I will go ahead and just make a note here because Smar's formula is kind of like a famous thing, so you want to be aware of it. All we have to do is take equation 13 and delete the integral over the spacelike hypersurface because we're imagining that there's no matter outside the black hole, in which case you end up with the equation that the mass of the black hole is going to be 2 omega h jh plus kappa over 4 pi a. Now that equation is known as Smar's formula. You can read about it in reference 7 and also Poisson 5.84, and that was discovered by Larry Smar in 1973, the same year this paper was published. And as you can see, Smar's formula relates the mass of a black hole to the angular velocity, angular momentum, surface gravity, and surface area of the event horizon. And so the mass formula that we've derived in this paper, equation 13, is basically just Smar's formula plus an integral that pertains to the matter outside of the event horizon, which ultimately comes from the Komar mass formula if you think back to how we went from equation 5 to equation 6. Well, anyway, the paper goes on to list some of the results for the Kerr solution, that is, for a rotating black hole with no electric charge. So equations 14 through 16 of the paper give us expressions for the angular velocity, the surface gravity, and the surface area, respectively, in terms of the mass and the angular momentum of the rotating black hole. So that's included here for reference, but let's go ahead and take a moment to look at these equations and see what they mean and what they can tell us about the physics of black holes. Well, writing out the equations like so, you can see that all of these on the right-hand side are some expression involving mass and angular momentum. And if we want to easily understand the shape of these equations, we can go ahead and define the dimensionless parameter alpha as the angular momentum divided by mass squared, and doing that is going to let us really simplify these equations and investigate their structure. So what exactly is this alpha parameter? Well, when alpha equals 0, you have a non-rotating black hole. On the other hand, when alpha equals 1, that is the maximum angular momentum allowed for a black hole of mass m. So that corresponds to a Kerr black hole rotating with the maximum allowed angular velocity. Alright then, so let's go ahead and plot the equations like so. First off, looking at equation 14, we have the angular velocity of the event horizon as a function of this dimensionless angular momentum parameter, alpha. Now you'll notice that when simplifying this equation, we've gone ahead and moved a factor of m on over to the left side of the equation. So that way we get a simple curve shown here. And you'll notice that it goes from 0 in the case of a non-rotating black hole, which makes sense because a non-rotating black hole is going to have no angular velocity. And then, if you go all the way to the right, to the maximally rotating black hole, you can see that this factor, mass times angular velocity of the horizon, approaches a maximum value of 1/2, as you can see from the equation. And so in other words, if you want to flip that around, you can say that for a maximally rotating Kerr black hole, the angular velocity is going to be 1/2m. So that equation gives us the relationship between the angular velocity of the horizon and the angular momentum of the black hole. Likewise, now if we look at equation 15, we can plot the mass of the black hole times the surface gravity kappa, also as a function of this dimensionless parameter alpha. And if you look at this equation, you see that the value for m kappa starts off at 1/4, 0.25, for a non-rotating black hole, and then for the maximally rotating black hole, it drops all the way down to 0. So that is super interesting, because if you think about it, that means a non-rotating black hole is going to have a surface gravity which is 1/4m. But for the maximally rotating black hole, the surface gravity approaches 0. And that kind of makes sense. If you want to think about like a really spinny black hole, the event horizon is sort of loosely bound on account of all that angular momentum. And when you think about that, you might be tempted to think that a more spinny black hole with a more loosely bound horizon is going to have an event horizon that's farther out. But no, that's actually not the case. It's the other way around. Because if you look at equation 16, you can plot the area of the event horizon, normalized by the mass squared, as a function of the dimensionless parameter alpha, and you see that for a non-rotating black hole, when alpha equals 0, the ratio between the area of the event horizon and the mass squared of the black hole is going to be 16 pi, which is about 50. But then if you imagine a black hole that's rotating, you can see that the area of the event horizon actually decreases relative to its mass. And so even though the surface gravity is going to be lower at the event horizon because of equation 15, you can see that the event horizon actually shrinks for a more rotating black hole of the same mass. But it doesn't shrink all the way to 0. Even if you have the maximally rotating black hole for a particular mass, where alpha equals 1, then in that case, the ratio between the area of the event horizon and the mass squared of the black hole is going to reach a minimum possible value of 8 pi, which is about 25 or so. And so anyway, equations 14 through 16 can give us some insight into the character of Kerr black holes across a variety of possible angular momenta. The paper goes on to say, for a Kerr solution with zero angular momentum, that is JH equals 0, or likewise alpha equals 0, the total mass is represented by the last term in equation 13. That is kappa over 4 pi times A. Because if you look at equation 13, we have an integral over the space-like hypersurface of the matter outside the black hole, so neglect that. And then if the black hole is not rotating, then that angular momentum term goes away, and so then all of the mass of the black hole is given simply by kappa over 4 pi A. But now consider what happens if we imagine a black hole that is rotating and has some angular momentum. Well, as the angular momentum increases, holding mass constant, then the surface gravity is going to have to decrease until it is 0 in the limiting case, where angular momentum squared equals m to the 4th power, or in other words, where angular momentum equals m squared. At that limit, where the black hole is rotating as much as it can for its mass, then all of the mass is represented by the rotational term in equation 13, 2 omega h jh. And so that's sort of the opposite of the non-rotating black hole. When the black hole is non-rotating, all of its mass is in the kappa over 4 pi A term, and when the black hole is maximally rotating, then all of its mass is in the angular term 2 omega h jh. And you can see that by looking at the plot we've shown here for equation 15, that is that green curve for m kappa, where we can see that there's a reduction of the surface gravity with angular momentum. The more angular momentum you have, the less surface gravity you have, if you hold the mass of the black hole constant. And you can think about that as a centrifugal effect. The more the thing is spinning around, the weaker the surface gravity is at the event horizon. So then, when the angular momentum is near the limiting value, that is, as alpha approaches 1 and kappa approaches 0, the horizon is, in a sense, very loosely bound, and a small perturbation can raise a large tide. So to think about that, imagine a non-rotating black hole with an event horizon which is going to have a maximally strong surface gravity relative to its mass of, kappa equals 1 over 4m. But now imagine a black hole of the same mass that's rotating very, very quickly, close to the maximal allowed angular momentum for its mass. Well, then you're going to have a very low surface gravity, and the horizon is sort of this loose thing that's not as tightly bound as in the case of a non-rotating black hole. Well, all right, then, that brings us to the end of part 2. We went ahead and derived the mass formula, and then we interpreted what it means, and we compared it to some of what's known about the Kerr solution for black holes. And so now we're really starting to get a handle on what are the things that determine the mass of a black hole, and how are these related to angular velocity, angular momentum, surface gravity, area, the matter outside the black hole. We have a really good analytical handle on that now. And so next, in part 3, we're going to jiggle this integral mass formula, and thereby cook ourselves up a differential mass formula. My friends, welcome to part 3 of the paper. This is where it gets tough. It's going to be mathematical, but you got this. It's all good. So in this part of the paper, we're going to start with the integral mass formula that we derived in part 2, and then we're going to use the tools of variational calculus to jiggle this formula into a differential formula that's going to give us the difference in mass between two very similar black holes. So the way to think about that is that equation 13 gives us a formula for the mass as a function of some stuff about the matter outside the black hole, as well as some properties of the event horizon of the black hole. And so we want to know if we jiggle all of these things and give all the variables a little nudge, well then there's going to be a little variation in the mass, a little change in the mass. And so we want to figure out what is the formula that tells us the little change in the mass as a function of the little changes in all the things that it depends on. So part 3 of the paper is all about getting from equation 13 to equation 34. For simplicity, we shall consider only the case in which the matter outside the horizon is a perfect fluid in a circular orbit around the black hole. Oh, and also, if you're interested, there's a differential mass formula for rotating stars without the black hole terms in reference 12. And you can also find a treatment including electromagnetic fields, which allows the matter to be an elastic solid, in reference 6. All right, so now the next step of our analysis is to write an expression for our energy momentum tensor, T, also known as the stress energy tensor. You hear these terms interchangeably. Anyway, we're going to write T in terms of the properties of the matter that's swirling around the black hole. Now, as we talked about, for the sake of simplicity in our analysis, we're considering a perfect fluid that's circling around the black hole. And a perfect fluid means that we're neglecting viscosity, we're neglecting heat conduction, we're neglecting shear stresses, and we're imagining that everything about the fluid is isotropic in its local rest frame. So then if you think about what is the defining quantity, the defining scalar that goes with a perfect fluid, well, it's going to be the energy density, epsilon. So you want to think about the energy density of the fluid, that is the energy per unit volume at each point on the fluid, as being the defining quantity that represents what's going on with the fluid. But now, there's different kinds of energy. And so our energy density can be a function of the particle number density, n, and also the entropy density, s. And this is like standard thermodynamics. You often think about epsilon as being epsilon as a function of n and s. Because when you think about it in those terms, then the temperature theta, the chemical potential mu, and the pressure P are defined by equations 17 through 19. That is, the temperature is the partial derivative of the energy density with respect to the entropy density. And this is very standard in thermodynamics. You can think about the temperature as being, by definition, how much the energy is going to increase if you do a little increase in the entropy of the system. So in a way, you can think about it like that's what temperature is. It's sort of the slope in the energy versus entropy plot. And similarly, we can define this chemical potential, which you can think of as the slope of the energy density with respect to the number density n. So think about it like this. You have a perfect fluid, and you want to add additional particles to it, so now it's more crowded with particles. Well, there's going to be a change in the energy associated with doing that. And that rate of change in the energy with the addition of new particles is what we mean by chemical potential. So then finally, we can define the pressure as being the chemical potential mu times the number density n plus the temperature theta times the entropy density s minus the energy density epsilon. And this is known as Euler's relation. So if you want to look up Euler's relation, thermodynamics, you can read more about where this comes from. But this equation you see all the time in thermodynamics. And by the way, you often see it with a V on the left side. So you often have pressure times volume, and then on the right side, instead of number density, entropy density, and energy density, you often just see particle number, entropy, and energy. So here we've written the Euler relation and divided through by volume, so that we're looking at each individual point along the fluid. Well then, with all of those definitions in mind, we can go ahead and define our energy momentum tensor, TAB, as equaling epsilon plus p, VAVB, plus p, GAB, where V is going to be the unit for velocity of the fluid, and G is the metric. Let's go ahead and unpack V a little bit. Well, imagine that you have some 4-vector u that is tangent to the flow lines of the fluid. Well, then all we're going to do is go ahead and normalize that by dividing out this quantity negative ub to the negative 1/2 power. That is 1 over the Lorentzian norm of u. So basically you have this 4-vector u that's tangent to the flow lines of the fluid, and then by definition we're going to go ahead and normalize that to end up with a unit 4-vector v that's tangent to the flow lines. Oh, and by the way, what is that vector u anyway that's tangent to the flow lines? Well, that's going to be our time-like killing vector k, plus some scalar multiple of our rotational killing vector k tilde, where that scalar multiple, omega, is the angular velocity of the fluid. So you can see here how this 4-vector u is something that, to some extent, it just goes forward in time, and to another extent it goes around and around, and the extent to which it goes around and around is proportional to its angular velocity. And then v, all that is just u that's been normalized. Okay, so now as a sanity check, I want to go ahead and write TAB explicitly as a 4x4 array of numbers in the fluid's rest frame. So this is a very specific and very simple way of looking at what our energy momentum tensor is in the rest frame of the fluid. So imagine that you're flowing along with the fluid so that the fluid doesn't have any velocity relative to your point of view. Well, in that case, then you can think of t as being 0 everywhere except the diagonal, and then along the diagonal, its time component is going to be the energy density, and the three spatial components are going to be the pressure. And then because there's no off-diagonal terms, you have no momentum flux in the rest frame of the fluid. So when you look at t in the fluid's rest frame, you look at it and you're like, oh, okay, yeah, that kind of makes sense. That's sort of the kind of objects that we would expect t to be. And then when you think about all the different forms that t might take on, when you're considering various frames relative to the fluid, and now the fluid is flowing from your point of view, and so you're going to get momentum flux and you'll have off-diagonal terms, you can imagine that in general it's more complicated than what's shown here in the matrix. But if you look at equation 20, that gives us a fully generic way of writing an expression for the energy momentum tensor t. And so that's what we're going to use going forward. So to sum up what we've done so far is we've written down an expression for the energy momentum tensor that describes a perfect fluid swirling around a black hole in a circular orbit. The paper then goes on to say that the angular momentum, entropy, and number of particles of the fluid can be expressed as the following integrals. If you look at these integrals, in all cases we are integrating over the space-like hypersurface S outside of the black hole, where the fluid lives. So that makes sense. And then the second and third integrals here for entropy and number of particles, these you can read directly based on how they're defined, because we're multiplying the entropy density and particle number density, respectively, with the unit 4 vector tangent to the flow lines contracted with the time-like directed volume element of the hypersurface in both cases, and so those are going to add up to the total entropy and the total number of particles of the fluid. And similar reasoning applies to that first integral regarding the angular momentum. In that case, we're contracting our energy momentum tensor with our rotational killing vector and our time-like oriented volume element, and that's going to give us an expression for the total angular momentum of the fluid swirling around the black hole. All right, so we're in a good position to start to think about how to jiggle our integral mass equation, thereby deriving a differential mass equation. But the thing about jiggling is, how do you jiggle something? Because if you imagine the integral mass formula that we derived in equation 13, you can imagine a whole space of possible solutions for that equation, and then we want to poke around in that space and see how the mass varies with respect to variations in all the various things. And so then you have to be careful about, as we're doing this jiggling, is there anything that we're holding constant, and in what ways are we allowing things to vary? So in more formal words, the paper goes on to describe the situation as, when comparing two slightly different solutions, poke a solution and kind of jiggle it a little bit and imagine one solution here and a little nudged solution there is a certain freedom in which points are chosen to correspond. That is, there's a kind of definitional freedom in what you want to hold fixed and what you're allowing to vary. So we shall use this freedom to make the hypersurfaces S, the event horizons, and the killing vectors, k and k tilde, the same in the two solutions. Because you can imagine that when comparing these two nearby solutions, we could change in the variation what we mean by the hypersurface, we can change how we're looking at the event horizon, and we could even imagine nudging the killing vectors and kind of redefining those to some extent. But when you think about all those things, you realize, actually, for our analysis, we should hold those constant. Let's be a little more formal about it, okay? Instead of talking in terms of jiggling, let's go ahead and say equation 21, which is that delta k and delta k tilde are both equal to 0. That is to say, as we nudge our equation and we're thinking about the original and the nudged equations and the two different things, from one solution to the other, there's going to be no change in our killing vectors, no change in k, and no change in k tilde. Now then you have to be careful, because just because the killing vectors are the same does not mean that their downstairs covectors are going to be the same. Now at first you'd think, well, they should be, right? But no, because bear in mind, we're dealing with general relativity where everything's confusing and complicated, and if the metric changes, then even though our killing vectors don't change, the covectors, the downstairs killing vectors, those can change. And how will they change? Well, their change comes from the definition of a covector, which is just that k downstairs A is going to be the downstairs metric GAB contracted with the upstairs KB. And so varying that concept, you get equation 22, where we see that the variation in the covectors, the downstairs killing vectors, are going to be given by the downstairs HAB contracted with the upstairs KB. Likewise for K tilde, where HAB we're going to define as the variation in the metric from one solution to the other. So our metric is GAB, and in general, the variation of our metric can be non-zero. So we have to account for this quantity, delta GAB. And rather than writing delta GAB all the time, we're going to go ahead and define that as HAB. So when you see HAB, all that is just the variation in the metric GAB. All right, so now the paper goes on to give us equation 23, which is a statement about the variation of the upstairs L, that is, the variation of the null vector tangent to the generators of the horizon, and that is going to be the variation of the angular velocity of the event horizon times the rotational killing vector k tilde A. Now to clarify, the delta here applies only to omega h, not to the product of omega h and k tilde A. And then likewise, the paper also tells us in equation 24, the variation of the downstairs L, which looks a whole lot like the variation of the upstairs L, but with symmetric terms that have to do with the way the covector varies, as sort of like what we saw in equation 22, with the downstairs killing covectors. Now the proofs of equation 23 and 24 are pretty straightforward. To prove equation 23, first, if you look at equation 8, where we defined the null vector L tangent to the generators of the horizon, if you simply vary that, you see that we defined it as the time-like killing vector k plus the angular velocity of the event horizon, omega h, times the rotational killing vector k tilde. And to evaluate that variation, all we have to do is break up the sum into a couple of parts, and then, on the second part, apply the product rule to split that out like so. Now right away, delta k is going to disappear, because we're holding our killing vectors constant. And then for the same reason, that last term there, omega h delta k tilde, also goes away, by equation 21. And so all that remains is the variation of omega h times k tilde, which is precisely equation 23. The proof of equation 24 is very similar. We simply take the variation of our downstairs L by varying its definition in terms of the metric contracted with the upstairs L, because that's how you lower the index. And then all we have to do is apply the good old product rule to split it up like so. And in the first term, you see we have a delta G, but then recall that's what we've been calling H, right? So we have HAB, which is defined as the variation of GAB. And so then if you look at the second term here, where we have the metric contracted with the variation of the upstairs L, well, by equation 23, we can substitute that with a delta omega h k tilde, and so then we arrive directly at equation 24. So that's how we end up with equations 23 and 24, and we're going to use those later on as we do our variational analysis. Now that we have equations 23 and 24, the paper then goes on to say, since the event horizons are in the same position in the two solutions, the covariant vectors normal to them must be parallel. That is to say that the antisymmetric product of the variation in the covector L times the covector L itself is 0. And likewise, we have the same equation for the antisymmetric product of the variation of the upstairs n with the upstairs n itself. Now, when I first read this, I was a little confused, because it says covariant vectors plural, and at first I thought the plural referred to both L and N, like both of these equations in equation 25, but then you see that in the N equation, our indices are upstairs, so those are vectors, not covectors. By the way, covariant vectors and covectors are the same thing. So I thought about it for a while, and then I realized, oh, this sentence about the event horizons being in the same position and the covariant vectors normal to them staying parallel, I believe that refers only to the first half of equation 25. That is, the equation involving the L covectors. The reason I think that's the case is because this sentence would seem to justify the first half of the equation. And then, once that equation involving L is true, it follows from our definition of the null tetrad, which defines the relationship between n and L, that the second half of equation 25, involving the n vectors, would also be true. Because bear in mind, n is defined in relation to L, and so n is born with a different height index than L anyway. In any case, I'm going to go ahead with that interpretation, and now the question becomes, what is the first half of equation 25, and how do we know it's true? Well, fundamentally, equation 25 is a geometric constraint on the event horizon. And to see what this equation means, first let's go ahead and expand out those anti-symmetrization brackets so we can write this expression in an alternative form, which is perhaps a bit more familiar to those of you who have worked with wedge products. You see, because this expression you can think of as the area of the parallelogram spanned by L and the variation in L. So by equation 25, when we're saying that this expression is 0, all that's to say is that the variation of the covector L is parallel to the covector L itself. So from one solution to another, the covector L is able to stretch or shrink, but it's not going to rotate. Because as we do our perturbation, if the covector L were to rotate, then you would have some parallelogram formed by the covector L and the variation of the covector L. Equation 25 says there is no such parallelogram, and the covector L varies only along its own direction. So why is this true? Well, as we saw previously, by fiat, we're holding the event horizons in the same position as we do our perturbation. Now the horizon can become more swirly as we're changing the angular velocity of the black hole, and the horizon can even change area by virtue of changes in the metric. But between our two solutions that we're nudging from one to the other, we're holding the event horizon fixed as the same locus of points in our analysis. And so therefore, the normals to the event horizon are going to remain parallel even as we do this perturbation. Now at this point, there's a very important subtlety that we have to keep in mind, which is that the event horizon is a three-dimensional null hypersurface, which topologically is like a two-sphere with a null vector at each point on the two-sphere. The easiest way to imagine this is to imagine a Schwarzschild black hole in which the event horizon is generated by a two-sphere of photons that are all trying their best to escape the horizon and are never quite able to escape. And then, for a rotating black hole, you can upgrade that notion with equation 8, which tells us that the null vectors tangent to the generators of the horizon are now going to have a rotational component which is proportional to the angular velocity of the event horizon. And with that intuition in mind, we can revisit equation 23 and understand intuitively what it's telling us. You see, because equation 23 tells us that the variation in the null vectors tangent to the generators of the horizon is simply going to point in the rotational k tilde direction times a scale factor, delta omega h, which is the variation in the angular velocity of the event horizon. So if we imagine between our first solution and the second solution that we're nudging it towards, if the black hole spins up a little bit so that omega h increases, then delta omega h is a small positive number, and so L, the null vectors tangent to the generators of the horizon, are going to pick up an additional rotational component proportional to that increase in angular velocity. Likewise, if we were to slow down the black hole, then we're taking a little bit of k tilde out of the definition of L. So you see that as we do our perturbation, if we change the angular velocity of the event horizon, the vector L becomes more or less swirly, depending precisely on the change in the angular velocity of the event horizon. But then we have the covector L, which is related to L by the metric. But then the weirdness comes in, which is that because L is a null vector, the covector of L contracted with the vector L equals 0, right, by the definition of what it means to be a null vector. But if you think about this contraction as a kind of dot product, right, a Lorentzian product, you can see that because the inner product equals 0, the covector L is actually normal to the vector L. And that's super counterintuitive. It doesn't have a good analog in terms of Euclidean space. But you can see mathematically from the algebra that this is actually true. So anyway, all that's to say, consider the entire two-sphere of downstairs covector L, and think of those as being the normals to the event horizon. Well, then the first half of equation 25 simply tells us that as we do our perturbation, those normals remain parallel everywhere. And so the variation of the covector L has to be proportional to the covector L itself. The second half of equation 25 would then follow from that, as well as our definition of the null tetrad. Okay, so that's equation 25, and you can think about it as the geometric constraint that as we do our perturbation, the event horizons remain in the same position in the two solutions. Next up, the paper goes on to say that the Lie derivative of delta L downstairs A by L upstairs B is 0, which, if you see Poisson equation 1.18, you can see that the equation for evaluating this Lie derivative is delta L downstairs A, downstairs semicolon B, L upstairs B, plus delta L downstairs B, L upstairs B, downstairs semicolon A. And that's the definition of the Lie derivative of a covector by a vector. The geometric meaning of a Lie derivative is that you're looking at how a thing changes as you flow along a certain direction. In this case, the quantity is the variation of L downstairs A, and the direction along which we're imagining it changing is the null vector L, which is tangent to the generators of the event horizon. Now, even though this looks a bit complicated, there's actually a really good way to imagine why this is true, and that is that the vector L is tangent to the generators of the event horizon. So if we imagine ourselves sliding along L, that is, we imagine we're somewhere on the event horizon, and we're sliding along L, which is tangent to the generators of the horizon, then by stationarity and rotational symmetry, as we slide along L, we wouldn't expect anything to change. Because if it were to change, then we wouldn't actually have stationarity and rotational symmetry. Alright, so this Lie derivative being 0, it follows from stationarity and rotational symmetry, and next we're going to use this fact as we calculate the variation in the surface gravity between our two solutions. Alright, so now let's go ahead and calculate the variation of the surface gravity, that is, delta kappa. So, throughout this whole process of part 3, we're imagining two black holes that are nearby in the solution space of the integral equation that we derived in part 2. And these two solutions are separated only by little tiny nudges in all of the variables. So now we want to answer the question of, as we're nudging all these variables, what is the tiny little difference that we get in surface gravity from one solution to the other? All right, well, so far in part 3, we've already demonstrated equations 21 through 24. So we know from one solution to the other that we're not going to have any variation in our upstairs killing vectors k and k tilde. Now we will have some variation in our downstairs killing covectors k and k tilde, but that variation is only driven by the change in the metric, HAB. And then likewise, we have equations for how the vector L and the covector L will change from one solution to the other. Alright then, well, if you recall how we defined the surface gravity kappa in terms of L and N, we can write that kappa equals negative L downstairs A semicolon B contracted with the upstairs NA LB. Now on the horizon, L is actually a killing vector. And that means, by Killing's equation, equation 1, that L A semicolon B is going to be antisymmetric. That is, if you take the covariant derivative of the covector LA along the direction B, that's going to be the negative of taking the covariant derivative of the covector LB along the direction A. So you swap those indices around and you can pick up a minus sign. That's antisymmetry. Well, using that fact, we can write the surface gravity kappa in the form shown here. You see, because all we've done here is we've swapped the indices around only on that first LB semicolon A term. So we start off with A semicolon B and a minus sign, we flip those indices around, and by Killing's equation, by the antisymmetry of this expression, that minus sign goes away, and the A's and the B's get swapped around. Well now then, our next move is to swap all of the A and B indices at the same time, which we're allowed to do because when you swap all of the indices in an expression, that's just relabeling dummy indices. So it doesn't actually matter what we call A versus what we call B. As long as we do a consistent redefinition, we can go ahead and globally swap our indices around. All right then, so what have we done here with kappa? Well, if you look at what we started with for kappa and what we have now, you see that all we've done is we've been able to get rid of a minus sign while also switching around the indices on the L and the N. And what's nice about the way we've written it here is that, think about this. Think about what happens if you take the covariant derivative along the B direction of LA, that is, of the Lorentzian norm squared of L. Well, by the product rule, you can go ahead and expand that out as LA semicolon B, LA upstairs, plus LA downstairs, LA upstairs, downstairs semicolon B. And that's just the product rule, so all we're doing is expanding it out. But then you'll find that those two expressions are actually both equal to each other if you move some indices around from upstairs and downstairs. You'll find that in both cases we're adding up L downstairs A semicolon B contracted with L upstairs A, and so we end up with two of those. But then by pattern matching, if you look at the equation we have for kappa, you realize, hey, we have an L downstairs A semicolon B contracted with L upstairs A. And so we can go ahead and replace that with 1/2 of this LA quantity semicolon B. So then we arrive at a rather simple-looking expression for the surface gravity kappa, as shown here. And this is the form of kappa that they use in the paper to calculate delta kappa. See, because now that we've written everything out nice and clean like so, then all we have to do is apply the product rule to this definition of kappa. And when we apply the product rule, we end up with the equation shown here. You'll notice that in the first expression here, all we've done is we've distributed the variation along the LA, so that we end up with delta LA plus LA delta LA, and then all that remains within the covariant derivative along the B direction times N upstairs B. And then after that, the second term is just the derivative along B of LA times the variation of the vector N upstairs B. So all that is we've applied the product rule to our definition of the surface gravity kappa. Next, the paper goes on to say that this is equivalent to the expression shown here. Now this paper, it's so dense because it turns out this is true what they're saying. It is equivalent to this thing. But to get from the line we were just on to this next line shown here, it's actually a whole lot of work. So we're going to go ahead and do that work, but it takes a while just to get to the next line of the equation. So let's go ahead and break it down into a few pieces and address them one at a time. All right, so first of all, let's go ahead and focus on these highlighted terms here, and we'll go ahead and massage the terms from the first line into the terms of the second line. To do that, the first move is to use the product rule to expand the variation like so. And then the next move is to use the fact that the Lie derivative of the variation of our covector LA by the vector LB is 0. And that fact can be expressed in the equation shown here. Notice that this is the equation from the paper in the sentence right after equation 25, but we've gone ahead and fixed that little index typo so that both of our terms have the same free index. So that's the correct way to express that the Lie derivative is 0. And so the second line here is exactly the same thing as the first line, but we've just gone ahead and subtracted the first term from both sides. Now then, returning to the equation on the left side of the screen, we can use this thing about the Lie derivative being 0 to do a substitution on that second term. Because you see how we turned it from a delta LA semicolon B, into a negative delta LB semicolon A, LA. So now let's go ahead and notice that in our equation, both of these terms have a downstairs A and an upstairs A, and a downstairs B and an upstairs B. So everything contracts, leaving us with scalar quantities for both terms. Therefore, if we want to, we can go ahead and do an index swap, swapping A and B on the second term of our equation. Because when everything contracts and boils down into a scalar, it doesn't matter what we call our indices, so long as we swap things around in a consistent way. Now, having done that index swap on the second term, we see that we now have a common factor of delta LA semicolon B, and so we can go ahead and factor that out, pull that out to the left side, and we end up with the expression shown here. Now the next move seems a bit arbitrary, but our goal is to massage the expression into the highlighted terms in the bottom line on the screen. So what we're going to do is we're going to turn that minus sign into a plus sign by subtracting out delta LA semicolon B NALB. And you see, we can do that because we have a plus sign now, but then outside of that expression, we're subtracting out a term that's going to make it equal to the minus sign expression we had before. Now then the final step is on that rightmost term, we're going to once again leverage the fact about this Lie derivative being 0 in order to replace delta LA semicolon B LB with delta LB LB semicolon A. And then if you look at that expression, you can see that the first term is an exact match with the first term in the bottom line. And then the second term is also an exact match if you go ahead and swap the indices A and B, which is allowed because everything contracts and that's all good. And so therefore, we've gone ahead and demonstrated that the highlighted terms in these two lines are in fact equal. So that's all good. Next up, let's focus on the highlighted terms shown here, and we want to show that these are equal. Well, for starters, our first move is going to be to use equation 23 to replace delta LA with delta omega H K tilde A. Remember, because we saw earlier when defining equation 23 that this is going to be the variation of the null vector tangent to the generators of the horizon. And it's simply going to be the variation of the angular velocity of the event horizon times the rotational killing vector. Now, because the variation of the event horizon's angular velocity, that is, the little difference in angular velocity of the two neighboring solutions of our integral mass formula, because that's a global parameter and not a field, we can go ahead and pull that outside of the derivative, leaving us with the expression shown here. So then the next move is to go ahead and replace the covector L with the covectors K plus omega H K tilde, which we're allowed to do by lowering the index on equation 8. So then we end up with the expression shown here. Now then, if you focus on the downstairs semicolon B, that is the covariant derivative along the B direction that's operating on the terms inside the parentheses, we can go ahead and apply the product rule and expand out the derivatives of those terms like so. And I know this looks like kind of a mess, but we can use equation 1 to clean things up a little bit. So by equation 1, we have that K downstairs A semicolon B contracted with the upstairs K tilde A is going to be equal to negative K downstairs B semicolon A contracted with the upstairs K tilde A. So that's equation 1 with the K tilde A slapped onto both sides. So it's essentially just Killing's equation. So now then, if you look at that term K downstairs A, K tilde upstairs A downstairs semicolon B, if we go ahead and raise and lower those A indices, we can write that as K tilde downstairs A semicolon B, K upstairs A, which by equation 1 is equal to negative K tilde downstairs B semicolon A, K upstairs A. Now then also, we can go ahead and invoke equation 2 with the index swap on A and B to see that negative K downstairs B semicolon A, K tilde upstairs A, equals negative K tilde downstairs B semicolon A, K upstairs A. So now with those two facts in mind, equation 1 and equation 2, you see how we can write our expression in the form shown here, where those two terms involving K and K tilde have been replaced with a negative 2 K tilde downstairs B semicolon A, K upstairs A. And then while we're at it, we also went ahead and consolidated those omega H K tilde terms into a 2 omega H K tilde downstairs A semicolon B, K tilde upstairs A. Now we can go ahead and clean that up a little bit by combining the factor of 1/2 with those factors of 2, and also replacing negative K tilde downstairs B semicolon A with K tilde downstairs A semicolon B, which is a legit move because of equation 1, right? That is the famous Killing's equation. Alright then, so now let's go ahead and do some index gymnastics on the K tilde terms. Notice that K tilde downstairs A semicolon B, K tilde upstairs A, is equal to K tilde downstairs A contracted with K tilde upstairs A downstairs semicolon B, just by raising and lowering an index and swapping those terms around. So then we can go ahead and write our expression like so, having also done an index raising and lowering on that first term involving k tilde and k, and we get the expression shown here. And at this point, all we have to do is apply equation 8 once more, recognizing in our expression k plus omega h k tilde, and replacing that with L. And you see that that is precisely the highlighted term that we're looking for. All right, we're almost there, just one more part. Well, first things first, let's go ahead and apply the product rule to expand out that covariant derivative along the b direction. Now, if you look at these two expressions involving the derivatives of L contracted with L, in both cases, these can be put into the form L upstairs A downstairs semicolon B contracted with L downstairs A. So the sum of these two terms can be written as twice L upstairs A downstairs semicolon B, L downstairs A. All right, so then we end up with the expression shown here. And now the 1/2 cancels out the factor of 2. And then if you swap around the term involving the L's with the delta NB, you see that in fact this is exactly the term that we were looking for. Woohoo! All right. So that completes our derivation of this line. Quite a bit of work for one line, right? But, sometimes that's just how it is. And actually, to be totally honest, the next line is not much better. Again, we have a situation where the paper skips quite a few steps, and so we're going to pick this apart one piece at a time, and just make sure that the math actually checks out. So you know what, if you look at equation 26, and compare it to the previous line, you realize that the two equations are actually equal if only we can show that the second term and the fourth term cancel each other out. And so at this point, to prove equation 26, all we have to show is that the variation of the covector LA, contracted with L upstairs A, downstairs semicolon B, and B, plus the variation of the vector NB, contracted with L upstairs A, downstairs semicolon B, L downstairs A, equals 0. Because if that's the case, then these two gray terms disappear, and we end up with equation 26. What we want to do here is we want to go ahead and invoke equation 25 about how the covectors normal to the event horizon remain parallel as we do our variation. So as we're doing our variation and we imagine nudging one solution into another, the event horizon remains in the same place, and therefore the normal covectors LA can stretch and shrink but are not going to rotate as we do our variation. We can write that in fancy mathematical notation of equation 25 in terms of an antisymmetric product between the variation of L downstairs A and L downstairs B, and in accordance with equation 25, that is 0. That is to say, the variation of the covector L and the covector L itself do not form a parallelogram, but rather are parallel. And by the way, another way to say this is that delta LA LB equals delta LB LA. That fact comes from simply unpacking the antisymmetric product, which equals 0. And then likewise, using the second half of equation 25, we can see that delta n upstairs A and upstairs B equals delta n upstairs B and upstairs A. Now another way we can look at all of this is to say that because the variation of the covector L is proportional to the covector L, another way to write that is that delta L downstairs A equals alpha L downstairs A for some real number alpha, and likewise delta n upstairs A equals beta n upstairs A for some real number beta. Now as it turns out, alpha is going to equal negative beta. That is, these scale factors are going to be related and opposite to each other. See, because by the normalization of L and N in the definition of our null tetrad, we have that L contracted with N equals -1, which is constant. And because that contraction is constant by definition, then the variation of that contraction is 0, because a constant doesn't vary. But if we know that that's 0, then by the product rule, we can say that delta L downstairs A and upstairs A plus delta N upstairs A L downstairs A, which we can also write as alpha L downstairs A and upstairs A plus beta N upstairs A L downstairs A, has to equal 0. But there's a symmetry in both of these contractions of L and N, so we can absorb those together and write this as quantity alpha plus beta times L contracted with N, which, because L contracted with N is -1, we could also write this as negative quantity alpha plus beta. and if that equals 0, then it follows that alpha equals negative beta. That is to say that the variation of the covector L and the variation of the vector n are going to be proportional to the covector L and the vector n respectively, and the proportionality constant on the variation of the covector L is going to be the negative of the proportionality constant on the variation of the vector n. Now with all that in mind, let's go ahead and write out the expression that we're hoping is going to be 0. And now if you look at this expression, you see that we can pull a factor of the covariant derivative of the vector LA along the spacetime index B outside of the parentheses, and then inside of the parentheses we have delta LA and B plus delta NB LA. Now then, writing these variations in terms of the proportionality constants alpha and beta respectively, and then right away replacing beta with negative alpha, we see that we have alpha times the contraction of L and N minus alpha times the contraction of N and L. And when you consider summing over all possibilities for A and B, and you look at the symmetry of this expression, you realize that everything here is going to balance out and add up to 0. So yes, indeed, the expression that we were hoping is 0 is in fact 0. Therefore, we have now established equation 26. Alright, now that we have equation 26, let's go ahead and clean up that first term involving L and N. To do that, the paper goes on to invoke the fact that as the variation of the covector L is proportional to L on the event horizon, then the covariant derivative of the variation of the covector L downstairs A along the B spacetime index, contracted with M upstairs A, M bar upstairs B, is 0. And what that means visually is that the variation of our covector is not going to change in the directions tangent to the two-sphere of the event horizon, that are spanned by the complex conjugate null vectors M and M bar. Now this fact is a consequence of the fact that the variation of the covector L downstairs A is proportional to the covector L downstairs A, so L downstairs A does not rotate as we do our variation. And when you combine that with the fact that the shear and the convergence of the horizon generators vanishes, then you can see that this quantity is in fact 0. Now then, using that fact, we can rewrite our expression for delta kappa in the simpler form shown here. So notice that between equation 26 and what we've written here, the only difference is that we've simplified the first term, and then we've just gone ahead and copied and pasted the second term. So let me say a few words about how we can do that simplification, because it's not obvious. So the key maneuver is to invoke the fact that we can construct the metric from a complex null tetrad. We've seen this equation before, though here I've gone ahead and written everything with the upstairs indices, so technically this is the reconstruction of the inverse metric, but it's the same idea as what we saw before. But now here's the trick. You'll notice that we can scoot the n and the L terms on over to the left side of the equation, and move the inverse metric term to the right, and all of a sudden we have this expression, which you'll notice we have in the parentheses of equation 26, but written in terms of the inverse metric and the complex conjugate null vectors M and M bar. So just by looking at that, you can already anticipate that this is going to help us simplify equation 26. So now if you look at equation 26, you see we have that expression out front, which is a covariant derivative of the variation of our covector L. So go ahead and multiply that on to the equation we just derived, and you see we end up with the equation shown here. And now this is the point at which we can use the fact that these M terms are going to vanish, because for the reasons we just talked about, the expression involving the covariant derivative of the variation of the covector L contracted with M and M bar equals 0, because the variation of L is proportional to L, and if that's 0, then likewise the other expression with M bar A and M B is also going to be 0, by the properties of M and M bar. So then we can simply ignore all of those terms with the M and the M bar, and we end up seeing that this term in equation 26 can be written simply in terms of a covariant derivative of the variation of the covector L contracted with the inverse metric. And then we can go ahead and clean that up by using the inverse metric to pop that downstairs semicolon B into an upstairs semicolon A. And we see that the whole thing simplifies very nicely to this negative delta L downstairs A, upstairs semicolon A. And that fact is what allows us to go from equation 26 to the equation written here, for the variation of our surface gravity kappa. Now this equation is getting very close to equation 27, so to get to equation 27, we just have to do a couple of more moves. First, let's recall equation 24, which tells us that the variation of the covector L can be written as the variation in the metric contracted with the vector L plus the metric contracted with our rotational killing vector k tilde times the variation of the angular velocity of the event horizon. We can use equation 24 to evaluate this derivative of the variation of the covector L that we have in our equation for delta kappa, and massage it into the kind of thing that we have in equation 27. You see, because in that term, we simply replace delta L downstairs A with the right-hand side of equation 24. And right away, we can go ahead and simplify this like so, by splitting it up into two pieces. You'll notice on the second piece, we've gone ahead and contracted the metric with the vector k tilde in order to pop that upstairs B index into a downstairs A index. Now I have some good news for you, which is that this k tilde term is going to go away and vanish and become 0, and we never have to worry about it ever again. The reason why is if you recall equation 1, which is Killing's equation applied to the rotational killing vector k tilde, well that tells us that the covariant derivative of the covector k tilde is antisymmetric. So in other words, k tilde downstairs A semicolon B plus k tilde downstairs B semicolon A equals 0. Well, if that equals 0, then we can go ahead and slap an inverse metric onto the left side, and it would still equal 0. But that inverse metric would have the effect of popping up an index. And by the symmetry of both of these terms, we would end up with 2 k tilde upstairs semicolon A downstairs A, and so that is going to be 0. So divide by 2, and you see that k tilde upstairs semicolon A downstairs A equals 0. Therefore, that k tilde term goes away. And so we only have to worry about that first term involving H and L and upstairs semicolon A. So let's go ahead and start to unpack that using the product rule, like so. Now as luck would have it, that second term is going to go away. In order to show that the second term goes away, we're going to demonstrate that L upstairs B semicolon A is antisymmetric, in the sense that L upstairs B semicolon A equals negative L upstairs A semicolon B. You see, because if you look at the definition of L in equation 8, we find that by definition L is the sum of the time translational killing vector k and the rotational killing vector k tilde scaled by the angular velocity of the event horizon. And then by stationarity and rotational symmetry, you can see that we have symmetry if we flow along L. To make this point really concrete, we can write L upstairs B semicolon A in terms of the definition of L given by equation 8. So we have k upstairs B semicolon A plus omega h k tilde upstairs B semicolon A. Now then by definition, k and k tilde are both Killing fields, and so by Killing's equation, if we swap those indices, we pick up a minus sign from the antisymmetry of the derivative of a Killing field, and then we can apply equation 8 in reverse to package everything up in terms of negative L upstairs A semicolon B. And all that's to say, L upstairs B semicolon A equals negative L upstairs A semicolon B. And that fact is going to make our second term go away. You see, because if you look at the second term, we have H downstairs AB, which is the variation of our metric tensor, and that is going to be symmetric under the swapping of indices A and B, because the metric tensor itself has that symmetry, and so the variation of the metric tensor will have that symmetry as well. And then we also have an antisymmetry in the derivative of L, which we've just demonstrated, and we can use this symmetry and this antisymmetry to evaluate the expression H downstairs AB contracted with L upstairs B semicolon A. See, because what we're going to do is we're going to replace HAB with HBA, which by symmetry doesn't change anything, and then we're going to replace L upstairs B semicolon A with negative L upstairs A semicolon B. And so we have the equation shown here. But now on the right side of this equation, we're going to do a dummy index relabeling, swapping A and B, and this is purely a passive move, we're just relabeling our indices, which is totally fine because on both sides of the equation we're summing over all of these terms. So we're allowed to do this. But then you see we end up with the equation that hablaba equals negative hablaba. Which is like, whoa, wait a minute. If hablaba equals negative hablaba, then there is no hablaba. So therefore, the whole thing is 0. I said hablaba just now because I got tired of saying the full thing, but you know what I mean. The long story short is that the second term goes away. And at the end of the day, all that remains of the term we've been evaluating is negative h downstairs ab upstairs semicolon a, l upstairs b, which is precisely the term that we were looking for in equation 27. So there it is. We've just derived equation 27, the variation of the black hole's surface gravity. Wow, what a cool equation. Now make a note of equation 27 because we're going to use this later on when we calculate the beautiful, glorious differential formula of equation 34. But we'll get to that later. First things first, let's go ahead and do a variational analysis of the integral mass formula. Alright, so having calculated the variation of the surface gravity, delta kappa, next our goal is going to be to calculate the variation of the mass, that is delta m. And in order to do this, we're going to have to take equation 13 and write it in a slightly different form, as shown here. And then we're going to break this up into parts and vary one part at a time. And then, having done that, we're going to bring all the pieces together and eventually arrive at the beautiful equation 34. But for now, we have equation 28. Now, if you look at equation 28, you'll recognize this as the integral mass formula that we derived in part 2. But by the Einstein field equations, we've gone ahead and replaced that negative t with an r over 8 pi. And so now we're going to calculate the variation of m by varying each part individually. So first of all, let's go ahead and define m sub r as the term with the scalar curvature r. That is, m sub r is defined as 1 over 8 pi times the integral of our hypersurface S of the scalar curvature times the time-like killing vector contracted with the surface element. Now then, to vary this term and calculate delta mr, all we have to do is vary the integrand, because we're holding our hypersurface fixed throughout the variation, and so to vary the integral, we only have to vary the integrand. As you might expect, the first move is going to be applying the product rule. When we do that, we have delta r times Ka d sigma a plus r times Ka times delta sigma a. Now you may have noticed there should be a middle term here, which is where we take the variation of Ka, but by equation 21, we're holding our killing vectors constant, and so that middle term vanishes because delta Ka equals 0. So that's why I went ahead and omitted the middle term of the product rule expansion, because it equals 0. Now I also want to put a couple of notes here, which is that, remember, HAB is by definition the variation of our metric tensor, GAB. And let's also go ahead and define the scalar quantity, H A upstairs, A downstairs, which we define as the upstairs metric, GAB, contracted with the variation of the downstairs metric, GAB. And so that is going to be a scalar quantity associated with how much the metric is varying as we do our variational analysis. And specifically, H upstairs A downstairs A is actually going to be the trace of the tensor H, which is the variation of our metric tensor. So now then, let's go ahead and focus on this term delta r in our equation for delta m sub r. This is the variation of the scalar curvature, which we can evaluate by taking the definition of r, which is the contraction of the upstairs metric with the downstairs Ricci curvature tensor. So then we go ahead and expand that out with the product rule like so. Now if you look at that first term involving the variation of our inverse metric, g upstairs cd, as you can imagine, that term should be something like an h upstairs cd. And essentially it is, but there's actually a minus sign that comes in as well. So in this little note bubble here, I've showed the reasoning for where this minus sign comes from. And if you're interested in those technical details, you're welcome to pause the video and explore them. But the long story short is that a minus sign comes in when you think about the product rule and the definition of the inverse metric. Okay, so now the next thing I want to look at is how do we evaluate the variation in the oriented volume element, that is, delta d sigma a. Alright, so when you think about the variation of d sigma a, the oriented volume elements, you want to think about the fact that we're holding fixed our hypersurface S. And so these oriented volume elements, d sigma a, which you can think of as a tiny little volume of the hypersurface times a normal vector, which encodes how the hypersurface is oriented in spacetime. Well, if the hypersurface S is held fixed, then our surface elements d sigma are really not going to change very much. But they might change a little bit, because the metric is going to vary, and you can imagine those variations in the metric having the effect of shrinking or expanding our volume elements. So to calculate the variation of d sigma, let's use Poisson equation 3.15 to write our surface element as the square root of negative g times ds, where g is the determinant of the metric. So in Lorentzian spacetime, negative g is going to be a positive number under the square root, and then ds is a coordinate surface element built from the Levi-Civita symbol. Now ds depends only on the coordinates of the surface S, which are held fixed throughout our variation. And so this object ds is not going to vary as we do our variational analysis. Now there's a lot of technical details behind Poisson equation 3.15, and you can read Poisson for more information on that. But the main thing to see is that we can calculate the variation of d sigma simply by varying that scale factor. So when we take the variation of the square root of negative g, you end up getting the trace of h times the square root of negative g divided by 2. So here I'll put a note bubble if you're interested in the technical details of how to take that variation, but in the interest of time I'm not going to narrate all those algebraic details. I just put them on the screen for reference if anyone's curious. Well anyway, the next move is to go ahead and absorb the square root of negative g times ds into a d sigma. And so we end up with 1/2 of the trace of h times d sigma. So all that's to say, as we do our variational analysis, the variation in our oriented volume element d sigma is going to point in the same spacetime direction as d sigma, and its magnitude is going to include a scale factor of 1/2 of the trace of the variation in our metric. So throughout the hypersurface, as the metric varies, it'll have an effect on the magnitude of our oriented volume elements. Now if you look at the definition of HAB as the variation of our metric, as well as the trace of h as the inverse metric contracted with the variation of our metric, then you can see that we can write this equation in the form shown here, where we've written the trace of h as the metric contracted with h upstairs CD. And by the way, that expression is the same as g upstairs CD, h downstairs CD. So you can directly see by the definition of the trace of h that this equation is legit. So then with all that in mind, let's go ahead and compile the pieces here together. And we can write that the variation of m sub r is negative 1/8 pi times the integral over our hypersurface of the integrand shown here, where we've evaluated this expression for delta r, and then the term that depends on the variation of the oriented volume element, we've brought that in terms of the metric and h upstairs CD, and d sigma a over 2. So all we've done there is we're putting the pieces together. So now if you compare what we have so far to equation 29, you can see that we basically already have equation 29. But there's one little difference that we have to prove now is not actually a difference. And that is, in the equation we've derived, we have a g upstairs CD, delta downstairs RCD. But in equation 29, that term becomes a 2h upstairs c semicolon d downstairs brackets c semicolon d. And in a minute, we're going to explore that complicated h term in more depth. But for now, the point I want to make is that the final step of deriving equation 29 is simply to show that these two expressions are in fact the same. Now to do this, it's a little complicated, but first we want to invoke something called the Palatini identity, which tells us that the variation in the Ricci curvature tensor can be written in terms of this expression involving variations of the derivatives of the Christoffel symbols. So now then, we can make the left-hand side of that equation look like the term that we have in our integral by contracting both sides with a negative inverse metric. From there, we can leverage the principle of metric compatibility, see Poisson equation 1.10, to pull the metric inside the derivatives, like so. And then on the second term, you'll notice that we're able to swap around the a and the d indices if we want to, because both are repeated, and so you may as well swap them around. And when you do that, you realize then that the covariant derivative on the second term is in the a direction, and so we can absorb the two terms together, like so. So now notice that inside the parentheses, we have these variations of the Christoffel symbols. And by varying Poisson equation 1.11, we can express those variations of the Christoffel symbols in terms of the inverse metric contracted with the derivatives of the variation of the metric. And that fact is shown in the equation here, the variation of Poisson equation 1.11. So then using that equation, we can write the expression inside the parentheses of the previous equation in the form shown here. Because we've used equation 1.11, and then we've distributed the inverse metric through, and various things canceled out, so we're starting to clean things up here, because instead of these terms with the metric and the variation of the Christoffel symbols, now we just have these terms involving the variation of our metric tensor. And you'll notice these look suspiciously similar to the expression involving the 2 and the h with the complicated indices of equation 29 that we're trying to show is equal to the expression involving the metric and the variation of the Ricci curvature tensor. So all we have to do now is a little bit of massaging to show that these things are in fact identical. Well, first of all, let's go ahead and write this out as the inverse metric, contracted with our terms involving h, but now written in terms of two downstairs indices. Alright, so at this step of the derivation, we can go ahead and package things up very concisely using anti-symmetrization brackets, which by definition is 1/2 of a thing minus the thing with the indices switched. So we can absorb both of these h terms together into this one antisymmetric term, and here the factor of 2 comes from the 1/2 in the definition of the anti-symmetrization brackets. So all we've done there is we've packaged things up in a more concise way. But then bear in mind, this was the expression inside the parentheses from the previous equation. But the terms inside of those parentheses, we were then taking a covariant derivative of along the a index. So remembering that derivative, we have the equation shown here. And fortunately, this equation cleans up pretty nicely, because by metric compatibility, we can pull the inverse metric outside of the covariant derivative, and then use it to pop the downstairs semicolon a into an upstairs semicolon b. And that gives us the expression shown here. And now then, all we have to do is one simple dummy index relabeling, replacing b with d, and there it is. So all that's to say, it is in fact the case that the negative inverse metric times the variation of the Ricci curvature tensor can be written as this expression with the 2h and the complicated indices. So that is how you get from equation 28 to equation 29. Alright then, we've now derived equation 29, so now we want to work towards getting to equation 31. Alright, so having defined this term, m sub r, as the part of equation 28 containing the scalar curvature r, we've just proven that the variation of m sub r can be written like so, which is equation 29. Now then the paper goes on to say that that complicated expression in equation 29, involving the 2 and the h and the indices upstairs and downstairs and the brackets and the semicolons, can be written as another expression involving k's and indices and brackets and semicolons, using this equation that a whole bunch of things add up to 0. So now we're going to take a moment to see exactly why that's the case, and what this all means. Well, first of all, this equation that all these h and k things equal 0, that is precisely the statement that the Lie derivative along our time translational killing vector is equal to 0. And you can see why these two statements are equal if you look at Poisson problem set 1.13, problem 4. But the point is that the derivative of h in the direction of the time translational killing vector is 0. And the reason that's the case is because we're working in a stationary spacetime, and as we do our variation, our little perturbation of the equations, it's going to remain a stationary spacetime. And so when you think about the variation of the metric that we get when we nudge one black hole solution towards another, the metric is going to vary, and in quite a complicated way, but that variation is not going to evolve along the time symmetry of our stationary spacetime. So that's why that Lie derivative equation is true. So then to prove equation 30, first what we want to do is apply the product rule to the right-hand side of equation 30 to expand it out like so. Then right away, we'll use the fact that our killing field has no divergence to delete that third term on the right-hand side of the equation. And this fact is actually true of any killing field. A killing field always has no divergence. The reason being, killing fields pertain to symmetry, and so if you imagine various points in spacetime flowing along a killing field, they're not going to be expanding or contracting, but rather things are just going to flow along in a divergence-free way. And the fact that the divergence of a killing field is zero can be proven from Killing's equation. Now, if you go ahead and look at the left-hand side of equation 30, you'll recognize that that is equivalent to the second term in the right-hand side of the equation that we have now, with the upper and lower indices switched around in a way that doesn't actually affect anything. So then we can write our stuff as the left-hand side of equation 30 plus twice these expressions with the k and the h and all these crazy upstairs, downstairs indices, semicolons, brackets, that whole mess. But if you look at that mess, it's actually not quite as messy of a mess as it seems to be, because we can recognize this expression as having the form of a Lie derivative of a 4-vector. You see, because if you look at the definition of a Lie derivative, given in Poisson 1.17, and you do some pattern matching, you can see here that indeed our complicated-looking expression is actually nothing more than the Lie derivative along the killing field k of h downstairs c, upstairs brackets, c semicolon a. And we know that it's a legit move to apply this definition of the Lie derivative along a vector field in this case, because this quantity h downstairs c, upstairs brackets, c semicolon a, is a vector. Because even though it looks complicated, the c indices are going to contract, right? We're summing over those because those indices are repeated, and we end up with one free index of a upstairs. So that is indeed a vector quantity, and so therefore Poisson equation 1.17 is applicable. But my friends, it gets even better, because k is our time translational killing field, and as we're doing our variational analysis, we're imagining two nearby solutions for a stationary axisymmetric black hole with some matter around it. But because both solutions are stationary, and we're not varying our killing fields, then the Lie derivative of this vector quantity along our killing fields has to be zero, by the stationarity of our perturbation. See, because without even thinking about what kind of a thing is this h downstairs c, upstairs brackets c semicolon a, we can still answer the question of how does it change as we flow forward in time. Well, by the stationarity of the situation, it doesn't change as we flow forward in time. So now we've just proven that the right-hand side of equation 30 equals the left-hand side of equation 30. And that completes our proof of equation 30. Now then, we can use equation 30 to write the last term in equation 29 in the following form. So you look at equation 29, consider that last term in the integrand, the one with the 2 and the h and the indices and the k contracted with the d sigma. Well, if you look at that term on its own, then you see in the integrand that's the left-hand side of equation 30, so we can go ahead and write that instead as the right-hand side of equation 30. Now, at this point, notice that the covariant derivative, semicolon d, is being applied to the entire integrand, and so we can go ahead and use Stokes Theorem to convert from an integral over the hypersurface S to an integral over the boundary of S, while dropping the covariant derivative along d. And this is very similar to what we did at the beginning of part 2, when we derived equation 5 and equation 7. So one can therefore transform the last term in equation 29 into the two-surface integral shown here. And this is equation 31. So when you consider all of the math shown on the screen here, that is how you get from equation 29 to equation 31. Okay, so after writing out equation 31, the paper then goes on to say in one sentence that the integral of equation 31 over the infinity bubble is negative delta m, and the integral of equation 31 over the two-sphere of the event horizon is an expression involving the variation of the surface gravity and the variation of the angular momentum. Now, those are pretty big claims, and you might think, oh, it's only one sentence. How complicated can it be to demonstrate that this one sentence is true? Well, you're about to find out. So first of all, looking at the first part of the sentence, we'll have to prove that integrating equation 31 over the infinity bubble is going to be negative delta m, that is the negative variation of the mass of the black hole and the matter that surrounds it. Well, all right then, let's go ahead and do it. So first we'll write out equation 31, and then we'll remember that equation 31 is an integral over both boundaries of the hypersurface S, that is the infinity bubble as well as the two-sphere on the event horizon. So we're going to split up this integral into two integrals, one integral over each of those boundaries, and we're going to take those on one at a time. So first of all, starting at the bubble of infinity, we can write our surface element as an antisymmetric wedge product of a unit time-like vector t, as well as a unit radial vector r, times an area element dA. So the picture you want to have in mind is a perfect sphere that's super big, with a radius that approaches infinity, and then imagine an area element on that sphere, and think about what is the plane in spacetime that's orthogonal to that surface element of the sphere way out there at infinity, where our spacetime is asymptotically flat. Well, there's going to be a purely spatial vector, which is going to be a radial outwards vector, a vector that points directly out in space, away from the plane tangent to the sphere, so that's r. And then because we're dealing not just in space, but in space-time, we're also going to have a purely time-like vector, t, which doesn't point anywhere in space, but points only in the time direction. So then you see that the two-dimensional plane in spacetime that's orthogonal to the area element of the infinity sphere is spanned by that radial vector as well as the time vector. That's equivalent to the statement that you can move arbitrarily in the radial direction as well as in time without moving around the sphere. So this is a really imaginable example of two planes being orthogonal in spacetime. Well, all right then, let's go ahead and take equation 31, evaluated over the infinity bubble, with the surface element written out in terms of t and r. Fortunately, this integral can be simplified using antisymmetry, because look at how we have TARD minus TDRA. So you can imagine splitting this out into two different integrals, one for TARD and the other one for TDRA, and then on the TDRA integral, you go ahead and do a dummy index relabeling, swapping a and d, but then in the other part of the integrand, involving the k's and the h's, you can swap a and d back, and because that part of the integrand is antisymmetric, doing that is going to give you a minus sign that ends up canceling out the minus sign on the original negative TDRA. So the long story short is that by antisymmetry, we can take the first half of our integral and simply double it up. And so the 1 over 8 pi becomes a 1 over 4 pi. Now then, because we're doing this integral all the way out at the infinity bubble, we find that out there, k, our time translational killing vector, is a unit time-like vector. And so it's orthogonal to the radial vector, that is, k contracted with r is 0, and it's going to point in the same direction as our unit time-like vector t, which is to say that k contracted with t, or equivalently k contracted with k, is going to equal -1, where the minus sign comes from the fact that we're dealing with the Minkowski metric and a time-like vector. And so those two facts allow us to really simplify our integral, because if we go ahead and write out the integral here, we can see that that second term is going to vanish because it contains a contraction of k upstairs d with r downstairs d. The fact that that equals 0 is going to turn off that second term. And so then we only have to keep the first term. But notice that in the first term, we have a k upstairs a contracted with a t downstairs a. So that's going to give us a factor of -1, which is going to cancel out the negative sign in front of our integral. And so we end up with the simple integral shown here. So now then, because our integral is kind of simple, now's a good time to go ahead and unpack those antisymmetry brackets on the c and d indices. bearing in mind that by convention, anti-symmetrization means we take 1/2 of the thing minus the thing with the indices swapped around. And so applying that anti-symmetrization, we end up with the integral shown here. So we're starting to really boil things down to a simple integral, but we can go even simpler. You see, because we're working on the infinity bubble, we have asymptotic flatness. So way out there at infinity, our metric is simply the Minkowski metric. And so a covariant derivative is just a regular old partial derivative. So therefore, we can go ahead and write our integral like so. Here, all we've done is we've replaced the semicolons of our covariant derivatives with partial derivatives instead. And also, we went ahead and replaced this h upstairs c downstairs c with simply the letter h. And that's a pretty common notational convention. Bear in mind, h upstairs c downstairs c is just the trace of h, that is to say, the trace of the variation of our metric. So h is going to be a scalar field associated with the overall extent to which the metric is varying as we do our variational analysis. Alright then, now if you look at our integral, you see that it involves entities which live in spacetime, and it has these indices c and d, which run over the 4 dimensions of spacetime. But we can go ahead and clean this up, because way out there at infinity, our radial vector can be written explicitly like so, where we have 0 for its time component, because it's purely a spatial vector, and then we have the unit outward radial vector, call that r hat sub I, which is a purely spatial unit vector that points directly out of our infinity sphere. So then if we go ahead and apply this fact to our integrand, we see that we can change that d index, which runs over all the spacetime indices, into a purely spatial I index, which is going to turn off the possibility of d being the time index. So now that first partial derivative, partial I, is only going to involve spatial derivatives. There's no longer going to be a partial derivative in time associated with that term, because there's no time component of r. So now we're really getting somewhere. Things are starting to simplify. But let's go ahead and simplify things further by thinking about the definition of the scalar h. Well, as we saw earlier, this scalar h quantity can be written as the upstairs metric contracted with the downstairs variation of the metric. And because way out at infinity we have asymptotic flatness, we can replace the upstairs metric with the upstairs Minkowski metric for flat spacetime. And remember, the upstairs Minkowski metric, all that is -1, 1, 1, 1 along the diagonal, with zeros on all of the off diagonals. So, evaluating this contraction, we end up simply with -h00 plus h11 plus h22 plus h33. So let's go ahead and replace h with that expression. And by the way, if you don't mind, let's go ahead and use h sub kk to indicate the sum over all of those spatial components of h. So now we're starting to get a really specific expression for what exactly our integrand is. But we still have this weird expression, partial c, h upstairs I, downstairs c. So let's go ahead and evaluate that and see what that is. Well, first of all, the c index can be expanded as a sum over when that index is time, call that 0, plus when that index is spatial. And we'll use this term with the sum over the j's to refer to the sum over all of the spatial possibilities for the c index. And then, if you look at that first term, where we have a partial derivative in time, bear in mind that we're dealing with a stationary spacetime. And so the time derivative is going to be 0. So that is simply going to vanish away. And then, if you look at this remaining term with the spatial indices I and j, let's go ahead and lower that j index on the partial derivative. Now, in general, that's an illegal move. You can't just go lowering a single index like that. But we're way out here on the infinity bubble. We're in the asymptotic flatness, and so the spatial part of our metric is simply the Kronecker delta. That is, 1 when the indices are the same, and 0 otherwise. And that lets us be a little fast and loose with our indices. And so out here in the asymptotic flatness, you can think of this lowering of j as sort of a harmless abuse of notation, so that's okay. And the reason we're doing this is to massage this term into a form that'll appear later in an equation that we're going to invoke for the ADM mass. So we'll get to that in just a moment. But for now, we can go ahead and gather up all the things we have so far. You see here on the left, we have 3 terms with an I-index upstairs, and those are all contracted with our unit radial covector, r hat, downstairs I. And you know what, just for fun, let's go ahead and lower the I-index on the left and raise it up on the right. And that's a totally legit move because we still have a contraction of upstairs and downstairs, so it's all good. And so then we end up with the form of the integral that we're looking for. So this last move with the raising and the lowering of the I-index, it doesn't do anything at all, but I kind of like it because now we're integrating over the infinity bubble, the quantity with the downstairs I-index contracted with the unit radial vector. It doesn't matter either way, but I kind of like how this looks. Okay, so now we've gone ahead and massaged equation 31, integrated over the infinity bubble, into the form shown here. But the question becomes, how do we prove that this equals negative delta m? Well, you might think a good place to start is to take the definition of m as given by the Komar mass formula, and then vary it, and do some pattern matching and put in a minus sign and show that this is actually what you get when you vary m. Now the problem with that approach is if you just vary the Komar mass formula, and you try to do this pattern matching, you end up with a bunch of leftover terms that you want to vanish, and that do vanish, but not without a fight. And so making those extra terms go away requires going really into the details of general relativity and the Einstein field equations. So, in the interest of time, I want to take a more efficient approach. And this approach is to split up our integral like so, simply by factoring out that first term. And then what we're going to do is we're going to show that this first term is equal to the variation of the Komar mass, and then we're going to show that the second term here is equal to -2 times the variation of something called the ADM mass. The ADM mass is a slightly different way of defining mass in general relativity than the Komar mass. And we're going to talk about it more in just a moment, so we'll get into the details. But for now, the important thing to know is that if you're dealing with a stationary, asymptotically flat spacetime, then, in that situation, the Komar mass and the ADM mass are the same. And hiding behind that insight are all the technical details of general relativity that we would otherwise have to get into if we just wanted to start by varying the Komar mass and then doing pattern matching and showing that that equals our integral. So that's why we're taking this approach where we're using mixed definitions of the mass, which are different in form but ultimately equal, in order to do pattern matching in a more efficient way. By the way, this took so long to figure out, you guys have no idea. Because my first approach was vary the Komar mass and then get some leftovers and make them go away. And then I was like, I can't fit this into a video, this is way too long. But then it's like, hey, wait a minute, some of these terms look like the ADM mass. But anyway, in hindsight, this is the way to go. Well, alright then, so our goal is to first identify the variation of the Komar mass as the first part of the integral. Then we'll have -2 times the variation of the ADM mass. Then we use the fact that those two masses are the same in this context, so you end up with delta m minus 2 delta m, which is equal to negative delta m, which is the result that we're trying to prove. So then first of all, let's focus in on the Komar mass. We begin with the definition of the Komar mass, which we saw earlier. You can also see Poisson 4.86, bearing in mind their convention has a factor of 2 different than ours, but that's all good. And so then to vary the mass, we simply vary this equation. Now when we take the variation of this integral, we can do that simply by taking the variation of the covariant derivative k upstairs a semicolon d. So then how do we evaluate the variation of k upstairs a semicolon d? Well, first of all, let's go ahead and write this expression as the upstairs metric, g dE, contracted with k upstairs a downstairs semicolon e. So in other words, we're just moving down that covariant derivative from the upstairs to the downstairs, because then we can apply the definition of a covariant derivative, given by Poisson 1.5, which says that to take the covariant derivative of a 4-vector, we take the partial derivative plus a term involving the Christoffel symbols contracted with the vector. So then having written out k upstairs a semicolon d in that form, to vary it, all we have to do is vary that expression. To vary that expression, we can use the product rule as well as the fact that we're holding our killing vectors constant, so equation 21, delta k is 0, which also implies that the variation of the partial derivative of k is 0, because that's going to be the partial derivative of the variation of k, so that's the partial derivative of 0, so that's 0. And so then when you work through that math of the product rule and canceling those things out, you end up with the equation shown here. So then we can substitute that expression for delta k a semicolon d into our integral for the variation of the mass, and then we find that the variation of the Komar mass can be written like so. Now our next move is going to be to argue that the first term of our integrand becomes negligibly small way out there at infinity. To see why that's the case, consider that because we're dealing in an asymptotically flat spacetime, our metric way out there at infinity is going to approach the Minkowski metric plus some deviation from that metric, which is going to drop off as order of 1 over r at most. So when you think about that, you realize that the variation of the metric is going to scale with at most 1 over r, because if the extent to which the metric differs from the Minkowski metric is order 1 over r, then the extent to which the metric varies from one solution to the other is going to be limited at most to this 1 over r scaling. And then when you think about the fact that the Christoffel symbols have to do with the partial derivatives of the metric, and you think about how, because of asymptotic flatness, the metric is going to be constant, plus something that drops off with at most order 1 over r, then the derivative of the metric is going to drop off as 1 over r squared. So then using these two facts, if you look at the first term in our integral, the contraction of the variation of our inverse metric with the covariant derivative of our time-like killing vector, and you expand out that covariant derivative in terms of the definition of a covariant derivative, being a partial derivative plus this term involving the Christoffel symbols, you realize that that is going to drop off as 1 over r cubed. The reason being, first of all, we can neglect the partial derivative term on the infinity bubble. That's going to be vanishingly small out there. And then that second term is going to drop off as a 1 over r times a 1 over r squared, and so the whole thing drops off as 1 over r cubed. But then you have to be careful, because as the radius of the infinity bubble increases, the area grows on the order of r squared. But that's okay, because as the area grows with r squared, and that first term drops off with 1 over r cubed, the whole combination of that first term integrated over the infinity bubble drops off as 1 over r. And so that is indeed going to vanish in the limit as r approaches infinity. Now the same thing is not true for the second term. The second term is only going to drop off as 1 over r squared. And so therefore, when you have r squared canceling out 1 over r squared, the second term is going to converge to a constant as r approaches infinity, which is good. That's what we would expect. Because delta m is a finite number, all of the terms in our integral should either vanish or converge to a constant, but nothing should run away towards infinity. Well, alright then, so having neglected that vanishing first term, we find that our integral can be written like so. And now all we have to do is evaluate this integral. To do that, the first thing we want to do is go ahead and write out that term involving the variation of the Christoffel symbols in terms of the definition of the Christoffel symbols involving the derivatives of the metric. So to get the equation written here, I've simply taken the definition of the Christoffel symbols, as given in Poisson equation 1.11, and taken a variation of both sides. And now let's also go ahead and write out our area element, d sigma AD, as an antisymmetric product of our unit timelike vector t and our unit radial vector r times an area element dA, like we saw before. Well, alright then, so making these two substitutions, we can rewrite our integral like so. Let's go ahead and scoot this delta m equation up a little bit to make some space for the next few lines of reasoning. So for the next part of our analysis, we're going to recognize that the inverse metric contracted with a covector yields a vector, right? I mean, that's sort of what the inverse metric does. And recognizing that, we can go ahead and rewrite our integral like so, having deleted those inverse metric terms, and at the same time, converting those t and r covectors into vectors. And while we're at it, let's go ahead and replace our time translational killing vector, k, with the unit time vector, t. because we're on the infinity bubble. And when you're way out there at the infinity bubble, if you want to experience the passage of time, you simply have to move in the time direction because of asymptotic flatness. Next up, let's go ahead and focus on these terms that I've underlined here in orange. We can write this out as a partial derivative of the variation of the metric times some components of the unit time vector and the unit radial vector. Well, now, because of asymptotic flatness and the fact that we're on the infinity bubble, the unit time vectors are constants. So we can go ahead and pull those time vectors inside of the partial derivative. And at the same time, let's go ahead and raise and lower the index on the partial derivative and the unit radial vector, respectively. And while we're at it, we can also go ahead and relabel the index e to d. That's just a dummy index relabeling. Now, if you focus on the term inside of the partial derivative, we have hfc contracted with tc/tf. And because the f and c indices are repeated, we're going to sum over all of those indices. But now when you think about the unit time vector, it doesn't have any spatial components. It only has a time component for the time index, so we'll use 0 for the time index. And because it's a unit vector, t0 is going to equal 1. So at the end of the day, when we add up all these terms of h times t, everything disappears except for the one possibility where both c and f are the time index 0, at which case we simply have h00. 0. That is the time component of the variation of the metric. Now next up, let's go ahead and focus on the magenta underlined terms. If we write them out like so, and then on that first expression, go ahead and do a dummy index relabeling, switching c and f, which is okay because both of those are summed over in that term, so we can swap those around, it's all good. Well, but then you see if we do that, then the first expression becomes exactly equal and opposite to the second expression. And so actually we find that these two terms cancel out and add up to 0. So those magenta terms go away. Woohoo! Oh, and also bear in mind, we are on the infinity bubble, and out there we've defined this unit radial vector, which is a purely spatial vector, and so its time component is 0. That is, the 4 vector can be written as 0, and then a purely spatial unit radial vector. And so then we can go ahead and write this expression, partial derivative of h contracted with r, as the same expression, but where we swap the space-time index d, which has 4 possible components, for a purely spatial index I, which runs only over the spatial indices. By the way, the astute viewer may have noticed that our indices are downstairs here, and so actually, even though I said radial vector, technically what's shown here would be a radial covector. But it's all good because we're way out there in the asymptotic flatness, and we're using the mostly plus metric. And because the spatial components of the mostly plus metric are all just 1, 1, 1 along the diagonal, there's actually no meaningful difference out there between the radial vector and the radial covector. So we're allowed to be a little casual with our spatial indices way out there at infinity. So then, if we bring all of these observations together, we can show that the variation of the Komar mass is -1 over 8 pi times the integral over the infinity bubble of the partial derivative of the variation of the metric contracted with the unit radial vector. Oh, and notice here we've gone ahead and lowered and raised the indices again, just so that we can massage this integral into the exact form that we were looking for. Alright then, so having shown that this first integral is indeed equal to the variation of the Komar mass, all that remains now is to show that the second integral equals -2 times the variation in the ADM mass. The ADM mass is a definition of mass in general relativity that is based on how much the metric deviates from a flat metric at spatial infinity. In particular, we can write it in the form shown here. This equation comes from Alcubierre, Introduction to 3+1 Numerical Relativity, equation A.4. And by the way, that is the great Miguel Alcubierre. Fantastic book. And you can find this PDF online for free. You can also find a notationally different but fundamentally equivalent version of this equation in Poisson 4.81. So if you think about what is the ADM mass, what's a good way to think about it? One way I like to imagine it, and this is only just an analogy, but imagine if you put a bowling ball on a trampoline, and then you look at how much the springs around the trampoline are stretching, and if you add up the stretch of the springs over the whole perimeter of the trampoline, that kind of gives you some sense of how much mass is on the trampoline weighing it down, right? So you can imagine thinking about how much mass is on a trampoline based on an integral around the perimeter of the trampoline of the distortion of the springs. Well, if you take that notion and upgrade it dimensionally and think about the Einstein field equations, you can imagine that the amount of mass contained within a space-like hypersurface can be described in terms of an integral over distortions in the metric way out at infinity. That is, on the springs of the trampoline that is the universe. Oh, and by the way, the ADM mass requires that we're dealing in an asymptotically flat spacetime, which we are, so that's all good. So in the equation shown here, our indices I and j are spatial indices, and so we can write the flat Euclidean metric, that is the spatial components of the flat Minkowski metric, simply as the identity matrix, or equivalently the Kronecker delta, which has a value of 1 if the indices are the same, and otherwise it has a value of 0. Well, alright then, so to take the variation of the ADM mass, you see that it just amounts to the variation of those metric terms, because the flat metric, that is those Kronecker deltas, are constant. Well then from there, all we have to do is some dummy index relabeling, swapping I for j, and rewriting the sum over jj as a sum over kk. These are totally legit moves, we're just relabeling dummy indices, because on both terms the j and the k indices are repeated, so it doesn't matter what we call them. But having relabeled our indices like so, you can look at the second part of the integral that we had earlier, and you can see that that equals -2 times the variation in the ADM mass. There's a minus sign that comes from swapping these terms around, and the 2 comes from the difference between 1 over 8 pi versus 1 over 16 pi. Well, there it is. We've shown that our integral equals the variation of the Komar mass minus twice the variation of the ADM mass, and because we're working in a stationary asymptotically flat spacetime, those two mass definitions are equivalent, so therefore we have delta m minus 2 delta m, which equals negative delta m. And so therefore we've proven that the integral of equation 31 over the infinity bubble does indeed equal the negative variation of the mass. So I know that took a lot of work, but we got there. We proved it. Alright, so having evaluated the integral of equation 31 over the infinity bubble, our next move is to evaluate it over the two-sphere of the event horizon. And this is actually a comparatively easier thing to do. So that's great. Our first move is to use equation 8 to replace the time translational killing vector k with L minus omega h k tilde a, where L is the null vector tangent to the generators of the horizon, omega h is the angular velocity of the event horizon, and k tilde is the rotational killing vector. Well, simply by making the equation 8 substitution, we can go ahead and write our integral like so. Now the reason we've written our integral in this form is that both of these k tilde terms, k tilde a and k tilde d, are going to vanish because our rotational killing vector is tangent to the two-sphere of the event horizon. And so therefore, contracting it with the area element is going to yield 0, thereby turning off those k tilde terms. And the formal argument for why that's the case is that the rotational killing vectors that are tangent to the two-sphere are therefore going to be orthogonal to the surface elements d sigma ad, which are normal to the two-sphere. Specifically, the contractions k tilde a la and k tilde a na are both equal to 0. And so if you wanted to, as an exercise, expand everything out in our integrand and contract it with the surface element, the fact that k tilde contracted with L as well as k tilde contracted with N are 0 are going to turn off those k tilde terms. So then once those k tilde terms disappear, all that remains are those terms involving L. And so now it's a good time to recall that we can write our surface element d sigma ad in terms of this antisymmetric product of L and N times an area element dA. Because bear in mind, L and N are both orthogonal to the two-sphere, and this antisymmetric product is equivalent to the wedge product. So this is going to be a sort of oriented plane element that encodes the orientation in spacetime of our two-sphere surface elements. So then if we write out the surface element in that form, we end up with the integral shown here. And by the way, when you see the surface element written out like this, you can really see exactly how the k tilde terms would vanish when contracted with these terms in the surface element. But anyway, the next move is to recognize the antisymmetry in this integral, which is very similar to what we did before when integrating over the infinity bubble. We can use the antisymmetry under the exchange of a and d in order to simply double up 1/2 of the integral, as shown here. And then, if you look at this integral, you see a very pleasant surprise on that first term, because you see how in the first term we have an upstairs LA vector, but that's going to contract with the downstairs LA covector in our area element, and because L is a null vector, the contraction LA equals 0. So that's going to turn off the first term. And then, better yet, we can apply very similar reasoning on the second term because it involves an L upstairs D contracted with an N downstairs D. And we know by the definition and normalization of N relative to L, that contraction is going to equal -1. So then we can rewrite the integral like so, keeping only that second term, and deleting the LD and the ND, replacing that with a -1. So then you have 3 minus signs, and when all the dust settles, that ends up being 1 minus sign. And so we end up with this integral. And you know what? Now would be a great time to go ahead and unpack the antisymmetrization brackets on the C and the A indices. Bearing in mind that antisymmetrization, all that means is to take 1/2 of the thing minus the thing with the indices swapped around. Now yet again, we find ourselves in a situation where the first term of the integral goes away. This time, the reason is because if you look at this term, h upstairs c semicolon a downstairs c contracted with LA, you recognize that the hc upstairs downstairs is simply what we've been calling the scalar h, that is the trace of the variation of the metric. And so this term h upstairs semicolon a, L downstairs a, which by the way is equivalent to h downstairs semicolon a contracted with L upstairs a, is going to equal 0. Because if you think about the physical meaning of a term like this, we're taking the derivative of a scalar, namely h, along a killing vector, namely L, which is a killing vector on the horizon, because L is tangent to the generators of the horizon. And so as you flow along L, our metric is not going to change. So therefore the variation of the trace of the metric is not going to change as you flow along L. So by the symmetry of the situation, we can see that this first term has to go away. That leaves us then with an integral over only the second term. And now what we're going to do is we're going to bring down the A index on the H term, and we're going to pop up the A index on the L term, and then we're going to rename C to A and A to B. And so you see we end up with the integral shown here, which is fundamentally the same integral as what we had before, but all we did is we popped some indices around from upstairs to downstairs and vice versa, as well as renaming our indices. And the reason we massaged our integral like so is because now, if you look at equation 27, we recognize in that equation this expression, h downstairs AB upstairs semicolon A contracted with L upstairs B, which is really cool, because then what we can do is use equation 27 to rewrite our integral like so, no longer in terms of h and L, but instead in terms of the variation of our surface gravity, as well as the variation of the angular velocity of the event horizon. So that's really cool. Now, how do we evaluate an integral like this? Well, first of all, we've already proven that the surface gravity kappa is going to be constant throughout the event horizon. And so therefore, the variation of surface gravity from one solution to another is going to be constant everywhere throughout the two-sphere of the event horizon. So that means that the delta kappa part of our integral is simply integrating over a constant, and so we end up with negative delta kappa over 4 pi times the area of the two-sphere of the event horizon. So that's pretty straightforward. Now to evaluate the second part of the integral, all you have to do is pop out the constant, delta omega h, and then use Komar's formula for angular momentum to recognize the remaining integral as negative 8 pi times jh. That is negative 8 pi times the angular momentum of the black hole. If you want to see why that is, check out Poisson 4.87, and bear in mind the factor of 1/2 convention difference between Poisson and the convention that we're using in this paper. So all that's to say, at the end of the day, when we integrate equation 31 over the two-sphere of the event horizon, we find that it equals the negative variation of the surface gravity over 4 pi times the area of the event horizon minus twice the variation in the angular velocity of the event horizon times the angular momentum of the black hole. Next up, the paper goes on to look at the variation of the energy-momentum tensor term from equation 28. Let's go ahead and call that m sub t, and so from equation 28, we can define m sub t like so. Now the paper then goes on to claim that the variation of this term, m sub t, yields equation 32. And so what are we going to do? Are we just going to take that on faith and move on? Nope. We got to prove it. That's how it goes. That's how it is. That's how you learn these things. All right, so the first thing I want to do is recall from earlier the definition of the unit vector tangent to the flow lines of our fluid that's circling the black hole. So as we saw before, the unit vector v can be written in terms of a vector u that's normalized by its Lorentzian norm, where that vector u is tangent to the flow lines because it's comprised of a combination of our time-like killing vector k and our rotational killing vector k tilde, scaled by the fluid's angular velocity, omega. And now this lets us pull a maneuver here where we can replace our killing vector k in the integral with the expression u minus omega k tilde. See, because all we're doing here is we're saying that if u, the 4-vector tangent to the flow lines, is given by k plus omega k tilde, well, then it follows that k is equal to u minus omega k tilde. So now, having made that substitution, we can go ahead and split up this integral into two parts, as shown here, where all we've done is we've split out these two terms, and we went ahead and switched around the order of the omega k tilde and the u terms, which of course is a legit move because subtraction works like that. Alright then, so with mt in that form, we can go ahead and take its variation, simply by taking the variation of the integrands. So in this line, all we've done is we've taken the variation of the previous line. Now the next move is to apply the product rule to both of these two integrals, like so. This will end up giving us 4 integrals. You see, in the first case, we've isolated omega k tilde, and we've applied the product rule like so. And then in the second case, we're isolating this factor of u, and so then we're applying the product rule as shown here. Now the reason we chose in the first case to isolate omega k tilde, and in the second case u, is that you can see that there's a similarity between these two integrals as we've written here. And so therefore, the way we've split things out here can then be cleaned up a little bit, like so. If you look at that magenta integral, we're just going to go ahead and bring that down. Then if you look at the orange expression, we're going to scoot that on over to the left, but otherwise no changes. Then if you look at the second and the fourth term, those two blue expressions, we're going to absorb those together and bring it down like so. So really, all we're doing there is rearranging a couple of things and grouping some terms together. Now, the very astute viewer might have noticed that in the first term on the left, this integral involving omega and k tilde, we actually went ahead and brought the k tilde inside the delta. Now that's a legit move, because by equation 21, we're holding our killing vectors constant, and so delta k tilde is 0, so therefore it doesn't matter whether k tilde is inside or outside of the variation shown here. And you can prove that by applying the product rule, and then seeing how one of the terms vanishes. But in any case, the reason I wrote it like this is because if you look at it, this term in the magenta box is the same as the first term of equation 32. So we're making some progress. We're getting there. So that's really cool. We're on the right track. And so then, if you don't mind, let's go ahead and rewrite this equation, but instead of writing out that first integral we'll just write it as a magenta ... So we've already got that part of equation 32, no need to keep writing it. For simplicity, it is simply a ... Now check out what we've done for this third term. We've gone ahead and replaced u minus omega k tilde with k. And that's very similar to the move that we did previously, where we used the definition of u, the 4-vector tangent to the flow lines of the fluid. And now something really cool happens, because by equation 21, we know that the variation of our killing vector equals 0. And so then actually this whole integral goes away, because delta of Ka equals 0. Well, that's great. So now, for our next move, we're going to use equation 20, the definition of our energy-momentum tensor T, as a function of the fluid's energy and its momentum, and the unit 4 vectors tangent to its flow. And now because in our integral we have a b upstairs and an a downstairs, we're going to have to go ahead and raise that b index upstairs. When we do that, we find the expression shown here, where instead of downstairs VA/VB, we have a downstairs-upstairs VA/VB, and then, when we raise the index on the metric, we end up with simply the Kronecker delta, which is equal to 1 when A equals B, and is otherwise equal to 0. So then, going ahead and making that substitution for T, we end up with the equation shown here. Now an integral like this is just begging to be split up into two integrals, so let's go ahead and do that. We'll take that term involving the Kronecker delta, and we'll move that to the left integral, and then what remains is the integral on the right. So now let's go ahead and focus in on that integral on the left, and yet again, we're going to use the fact that u equals k plus omega k tilde, and we're going to write this integral like so. Couple of notes here. First of all, the Kronecker delta converted our volume element, d sigma b, into a d sigma a. The reason being, in our original integral, we had indices a and b, but the Kronecker delta turns off all of the terms for which a and b are not equal, and so therefore what remains is simply a contraction involving only the a index. And then also on that first integral there, notice that I pulled the delta outside of that integral in order to make it match the second term of equation 32. And that's a legit move because by equation 21, delta k is 0, so therefore k can be brought into or outside of the variation, either way is fine. And also our hypersurface S is constant as we do this variation, so we can go ahead and pull the delta outside of the whole integral if we want to. So anyway, we notice in that first integral the second term of equation 32, which is awesome. We're making even more progress, we're almost there. Okay, so from now on, that term in the orange box, we're going to just call that a orange ... So now let's go ahead and gather all our terms here. We have a purple ellipsis plus the orange ellipsis, plus an integral involving omega and k tilde, plus this other integral, which I've massaged into a slightly different form here by substituting the v's for u's, and then on the upstairs ub, replacing that with kb plus omega k tilde b. So there's a couple of steps there. The net result is we end up with an expression divided by the square of the Lorentzian norm of u, as well as a downstairs ua, and an expression involving our upstairs killing vectors. But now the question becomes, why write it out like that? I mean, that looks so complicated, right? But check this out. Consider these terms underlined in blue. Well, is that not the third integral of equation 32? It is! Ho-ho! Now the only difference there is that our u downstairs c, u upstairs c is replaced with the totally upstairs uc, ud, gcd. But by index raising and lowering, that's the same thing, so that's all good, that's equal. And so therefore, we have found now all three pieces of equation 32. And so now these blue terms are going to simply be a blue ... And so let's go ahead and write out our equation, and we find that we have all three terms of equation 32. But, oh no, we also have some leftovers. Now leftovers are okay if you're dealing with pizza, but they're not okay if you're dealing with equation 32, because it's a whole different situation. So we better hope these leftovers equal 0. Well, as it turns out, fortunately for us, the leftovers do vanish. Woohoo! The reason why has to do with these terms containing the rotational killing vector k tilde, And the fact that we chose our hypersurface S to be tangent to k tilde, such that the contraction of our rotational killing vector with the surface element is 0, because if we flow along k tilde, we're going to stay inside the hypersurface, whereas d sigma a is the normal vector that pokes perfectly outside of the hypersurface. So you take the contraction there, you end up with a 0 because they're totally orthogonal. And then, because as we're doing our variation, we're holding our hypersurface constant, it follows that the variation of the contraction of k tilde with our oriented volume element is equal to 0. Now you can kind of see all that just by looking at it and thinking about how it is, but there are some subtle steps in there, and so I think for maximum clarity, it's worth taking a moment to just see exactly how the leftovers vanish. Well, first of all, we already know by equation 21 that we're holding our killing vectors fixed throughout the variation. Also, because we defined our hypersurface S to be tangent to k tilde, then like we just talked about, k tilde a d sigma a equals 0. And then also, because we're holding our hypersurface S constant throughout the variation, that implies that the variation of d sigma a is going to be proportional to d sigma a, which is to say that our directed volume elements are not going to change direction. No, each one is going to stay pointing the same direction in spacetime, and so the only allowed variations on d sigma a is going to be a scale factor that comes from changes in the metric, but it's not going to change direction. So then from these facts, it follows that the variation of the contraction of k tilde and d sigma equals 0, because if you write this out using the product rule, you can see that on the first term we have a variation of k tilde, which is 0 by equation 21, plus a term involving the variation of d sigma a. And so, for reasons we just talked about, we know that term is going to be proportional to k tilde a d sigma a. But then, by the fact that our hypersurface S is tangent to the rotational killing vector k tilde, we know that k tilde a d sigma a equals 0. And so therefore, that whole expression goes away. Now then, having established the facts shown here, it's very easy to see that our leftovers vanish, because all we have to do is expand all of these terms using the product rule, and then apply the fact that all these things equal 0. So first of all, let's go ahead and pluck out that variation from the first integral in our leftovers, expand it with the product rule like so. In the first case, you see the contraction of k tilde and our volume element, and we know that's going to be 0 because S is tangent to k tilde. And in the second case, we have the variation of k tilde a d sigma a, which we've just demonstrated equals 0. And so both of those pieces go away, and that's all 0. And then if we go ahead and repeat the same process for the second integral in our leftovers, yet again, we expand it out with the product rule. Yet again, we identify those two terms that equal 0 and for the same reasons. And yet again, we find that that integral vanishes into thin air, never to be seen again. So those are the details, but the big picture there is this mess of leftovers that we have goes away because we're holding our killing vectors fixed by equation 21, and we've chosen a hypersurface S which is tangent to k tilde. So it doesn't come as much of a surprise that these terms involving k tilde disappear. Alright then, so we have now successfully proven equation 32. You'll never believe what comes next. Equation 33. Alright, so let's talk about equation 33. Okay, so in just a moment, we're going to derive equation 33 from equation 32. But before we do that, I just want to say a few words about what exactly equation 33 is, so that we know what it is that we're going to be deriving in just a moment. Well, first, let's go ahead and recall what we were talking about earlier regarding the material properties of the circle of matter orbiting the black hole. In particular, if you look at equations 17 through 20, you can see how we defined the temperature as the partial derivative of the fluid's energy density with respect to its entropy density. We also defined the chemical potential mu as the partial derivative of the energy density with respect to the number density. And using Euler's relation, we defined the pressure in terms of the product of the chemical potential and number density plus the temperature times entropy density minus the energy density. So that's all standard thermodynamics. And then we went ahead and defined our downstairs energy momentum tensor as the product of the energy density plus the pressure times the downstairs VA/VB plus the pressure times the downstairs metric where v is the unit 4 vector tangent to the flow lines of the matter as it circles around the black hole. Now next, let's go ahead and recall the equation we just derived, equation 32, where we saw that the variation of the energy-momentum tensor term, delta m sub t, from equation 28, is the equation shown here that we just derived. Well, now if you look at equation 32, it's kind of a mess. It's kind of like, what is this? Can we clean this up a little bit? Can we make sense of what we're looking at here? What does it mean physically, right? So then the paper goes on to invoke equation 19, and it uses that to make a statement about the variation in the pressure, delta P, as well as a statement about UA and the variation of UC, UD, GCD to the negative 1/2, UA, equaling 1/2 VC, VD, HCD. Now in a moment, we're going to get into all of that and why that's the case and why that matters. But for now, I just want to look at how the paper mentions that, and then goes right on into saying that therefore, delta m sub t, that is equation 28, can be written in the form shown here, of equation 33. So equation 33, all that is equation 32, but written in terms of the material properties of the fluid flowing around the black hole. Now in this equation, we have a number of new things that we're defining here. You have delta dj, which is the change in the angular momentum of the fluid crossing the surface elements of our hypersurface. Delta dn is the change in the number of particles crossing our hypersurface element. And delta ds is the change in the entropy crossing the oriented volume element of our hypersurface. Now then also we have mu bar, which is the redshifted chemical potential. And we also have theta bar, which is the redshifted temperature. Now I know there's a whole lot here, and I'm sure you've got a lot of questions about what is all this, and how do we know equation 33 is true, and what does it all mean, and why are we writing it like this, right? And those are all good questions, and so that's why now we're going to go into the details of deriving equation 33 from equation 32, so you can see where everything comes from and what it means. But I just wanted to show you what equation 33 is before we go into how to derive it, so that you know what we're aiming for in the following derivation. All right then, let's go ahead and prove equation 33 from equation 32. First of all, we'll take equation 32 as a given. Let's also go ahead and import these things we were just talking about, delta dj, delta dn, delta ds. And given all of that, we now have the quest of proving equation 33. So this part of the video is all about going from the stuff on the top part of the screen and rearranging it into equation 33 on the bottom of the screen. Well, first things first, right away, we can see that the first term in equation 32 becomes the second term in equation 33. The reason being, if you look at that first term, we have an integral over the space-like hypersurface of omega times a thing that looks a whole lot like negative delta dj. And so, by doing a little pattern matching and substituting in delta dj, we find that we can transform the first term in equation 32 into the second term in equation 33. Let's go ahead and make those terms purple, so we remember that they're equal. So now then, our challenge is to show that all of those non-purple remnants are equal to each other. To show that the rest of equation 32 equals the rest of equation 33 is actually pretty straightforward, but it's just a lot of little moves. And as we're doing these little moves, we're going to be copying and pasting the same integrals over and over again. So over the next few minutes, there's going to be a lot of text on the screen. But don't worry, it's actually not as bad as it looks. So rather than focusing on these integrals themselves, just focus on what is the technique that we use to get from one step to the next. All right then, let's go ahead and recall equation 19, which tells us that the energy density epsilon plus the pressure P is equal to the chemical potential mu times the particle number density n plus the temperature theta times the entropy density s. And let's also go ahead and write out the fluid's for velocity, u, in terms of the unit vector tangent to the flow lines of the fluid, v, times the absolute value of the Lorentzian norm of u. So that's essentially the equation that we see right after equation 20, but written the other way around. So rather than writing v as a normalized u, we're writing u in terms of a scaled v, but it's the same idea. So now with those two equations in mind, you look at the last integral in equation 32 and make those substitutions, swapping epsilon plus p for mu n plus theta s, and also substituting out u downstairs a. By the way, in the last integral of equation 32, recognize that u upstairs c, u upstairs d contracted with the metric GCD. You can think of the metric popping down one of those indices, and so we can simply recognize that whole term in the parentheses as negative u downstairs c, u upstairs c. And because that quantity is raised to the power of -1 in equation 32, it'll have an exponent of -1/2 when we do our substitution, which brings in another factor of negative uc to the 1/2. Now the next move is going to look like a mess, but it's really actually super straightforward, because all we're going to do is take that last integral, and you see that it has this term un plus theta s. Well, we can split that out into two integrals, one with the mu n and the other with the theta s, and then for each of those two integrals, we're going to use the product rule to split out mu and theta, respectively. So in the integrals shown here, you can see those mu integrals up top, and the theta integrals down below. So all that is we're breaking up the sum, and then we're applying the product rule to both pieces. So you see what I mean earlier when I was saying that we're going to have a lot of text, but the moves themselves are really straightforward. Well, this is a good example of that. Now fortunately, we can go ahead and clean up these integrals a little bit by recognizing that the contraction u upstairs a, v downstairs a, is simply the negative of the Lorentzian norm of u. And you can prove that by writing u in terms of v, and then using the fact that v is a unit vector. So making those substitutions, we end up with the integrals shown here. Okay, so now at this point, we can combine the second and fourth integrals together by recognizing that n times delta mu plus s times delta theta equals delta p, which is stated in the paper right before equation 33. So using that equation, we can write everything out like so. Now at this point, we have another easy but messy move, and that is to break up the third and fourth integrals using the product rule, so that in both cases, we can split out a v downstairs a. And that gives us the mess shown here. Alright, now to simplify this, we're going to use the fact that because v is a unit time-like vector, its Lorentzian norm squared is -1, and therefore u upstairs a contracted with delta v downstairs a is going to be 1/2 times the Lorentzian norm of u times v upstairs c, v upstairs d, h downstairs cd, where h, of course, is the variation of the metric tensor. And that is essentially what's written in the paper before equation 33, but it should be noted that in the paper, their expression, in which they write out delta v explicitly in terms of the definition of v, is actually missing a factor of the Lorentzian norm of u on the right-hand side of the equation. You can verify that by looking at the left-hand side of the equation and noticing that it involves a factor of u times a variation in the unit vector v. So therefore, the right-hand side has to contain a factor pertaining to the Lorentzian norm of u. So anyway, we can make that substitution for u upstairs a, delta v downstairs a, and simplify the third and fifth integrals, which allows us to write out everything like so. So then at this point, we're going to merge the third and the fifth integrals together using equation 19, which tells us that mu times n plus theta times s equals epsilon plus p. And while we're at it, we're also going to use again the substitution that u upstairs a, v downstairs a is the negative of the Lorentzian norm of u. So we make those substitutions and we end up with the mess shown here. Fortunately, this mess cleans up quite a bit when we recognize in the last two integrals the definition of delta dn as well as the definition of delta ds. And likewise, the definition of the redshifted chemical potential mu bar and the redshifted temperature theta bar. So, when we make those substitutions, we can clean up our mess like so. Okay, now we're almost there. If you look at this top line of integrals, what we want to do is go ahead and apply the product rule to that first integral to split out a factor of p. So instead of having the variation of the entire first integral, we end up instead with the integral over a term involving the variation of p, and then another integral involving the variation of our oriented volume element, which, given the constraints of our variation, that the hypersurface S is held fixed, and that the variation of our killing vector k is 0, then you can see that the variation of k contracted with d sigma is going to equal the inverse metric g upstairs cd, contracted with the variation of the metric h downstairs cd, times k contracted with d sigma divided by 2. So that's how we get that second integral. And now something really nice happens, which is that the first and the third integrals cancel each other out, because they're equal and opposite. So those go away. At the same time, our second and our fourth integrals have so much in common that we can go ahead and merge them together into one integral. And notice that there's no meaningful difference here between the a index and the b index on our k and d sigma terms, because in both cases they're summed over, so it doesn't matter what we call them. Well, anyway, at this point we pretty much have equation 33, because by equation 20, you can recognize that our first integral contains t upstairs cd, so that is equal to the first integral of equation 33, and then the last two integrals here are equal to the last two integrals of equation 33. But wait a minute. Hold on now. Actually, you see there's minus signs when they should be plus signs. So what's the deal with that? Well, the first time I did this derivation, and I got these minus signs, I thought to myself, oh no, I've messed up. And then the second time I did this derivation, and I got these minus signs again, I thought to myself, oh geez, I've messed up again, in the same way. Well, that's not good. But then after going through the math a few dozen times and always getting the same minus signs over and over again, I started to think, you know what? I really think those ought to be minus signs. Because if you take the paper literally and just follow the logic mathematically, you really do end up with these minus signs. But the problem is, these minus signs are absurd, because they would propagate into equation 34, and the net result would be that throwing matter, or entropy, into a black hole would decrease its mass. And that's absurd, that's not real. So equation 33 with the positive terms, that is physically correct. But mathematically, in accordance with the internal logic of this paper, those should be minus signs. And that seems like a contradiction, but that implies that somewhere else in the paper, there must be another sign error which exactly cancels out the sign error in equation 33. And actually there is, because if you go back and look at the definition of n and s in terms of integrals over the number density and entropy density respectively, you find that those definitions actually yield a negative n and negative s for positive number density and positive entropy density respectively. So therefore, independent of this concern about the sign error of equation 33, we find that we should reverse the signs of the definitions of n and s anyway, and that sign reversal would then propagate forward into the definitions of delta dn and delta ds, and when that happens, then when we pattern match in deriving equation 33 from equation 32, that minus sign would come in and give us plus signs on the last two integrals of equation 33. And if you want to see all the details of what's going on here, I put together a little note that just explains everything in gory detail. But the long story short is that all of the physical conclusions of the paper are still totally valid. It's just that the paper contains a subtle inconsistency with regards to the minus signs, and strictly speaking, equations 33 and equations 34 are only true after we reverse the signs in the definitions of n and s, such that those definitions then become physically realistic with regards to giving positive values for positive densities. So anyway, that is how you derive equation 33. Alright, so now we have equation 33. That is the variation of the energy-momentum tensor term from equation 28. And that is the final ingredient that we need, the final piece of the puzzle, in order to derive the glorious equation 34, the differential mass formula. So now all we have to do is bring together all of the things that we have so far and calculate the variation of the total mass, delta m. Alright, my friends, Now it's time to bring it all together to get equation 34, which is the differential mass formula that we've been working so hard to derive. We're almost there. So to bring it all together, the first thing we want to do is recall equation 28, where we expressed the integral mass formula in the form shown here, where we have an integral over the hypersurface S outside the black hole, which represents the mass of the matter outside the event horizon, plus 2 omega h jh plus kappa over 4 pi a, and that is also known as Smar's formula for the mass of the black hole. Now previously, just now in part 3, we went ahead and picked apart the integral term into two pieces. So the part of the integral that depends on t we called m sub t, and the part of the integral that depends on the scalar curvature r we called m sub r. And if you think about equation 28 in terms of m sub t and m sub r, you can see that m equals m sub t plus m sub r plus 2 omega h jh plus kappa over 4 pi a. Now then, if you remember what the main goal of part 3 of the paper is to figure out if we jiggle everything that m depends on, what kind of adjustment do we get in m? That is, we want to have a formula for the variation of m in terms of the variations of all the things that m depends on. And so from what we've written here, if you just go ahead and take the variation of everything on both sides of the equation, you end up with the variation of m is going to be the variation of m sub t plus the variation of m sub r plus the variation of the term in the Smar's formula part of the equation, which we can get by applying the product rule to both the omega h jh term as well as the term involving kappa and a. So we end up with the expression shown here. But now, from all the hard work we've been doing in part 3, we already know what the variation of m sub t is. That's going to be an integral over our space-like hypersurface of tcd, hcd, ka, d sigma a, plus these integrals involving the angular velocity and angular momentum and redshifted chemical potential and number of particles and redshifted temperature and entropy of the matter outside the black hole. And this is the equation 33 that we recently derived. And then we also know, before we did equation 33, we talked about the variation of m sub r in equations 29 through 31, and so we also already have an expression for the variation of m sub r. It's going to be an integral over a hypersurface of these curvature terms, minus a delta m that comes from a Komar mass formula, and also minus a variation in kappa over 4 pi a, minus 2 delta omega h jh. So then, remembering that our goal is to have an expression for delta m, all we have to do is go ahead and plug in delta of m sub t and delta of m sub r into the equation for delta m. And that gives us the mess shown here. Now notice that this mess, despite being messy, is actually comprised of 3 submesses, which are less messy. That didn't make a whole lot of sense, but the point is, first, if you look at this formula, the top line there is just the variation in m sub t, the middle line is the variation in m sub r, and then the bottom line is the variation of the Smar's formula part of delta m. So you see, to get this equation, we've done nothing other than substitute in the results that we've recently proven. And so now we do have an equation for delta m. The problem is it's a huge mess, and we don't want that. So let's start to go ahead and simplify this. Well, the first thing you might notice is that on the right-hand side of the equation, we have a negative delta m. So we can go ahead and add delta m to both sides of this equation, thereby deleting that term on the right side and giving us a 2 delta m on the left side. And then we can go ahead and divide by 2, so that on the left we have delta m, and on the right we simply divide everything through by a factor of 2. And that gives us the equation shown here. Now you'll also notice during this process, we had a couple of terms cancel out. So you see there's a negative delta kappa over 4 pi times a, and a plus delta kappa over 4 pi times a, so those cancel out. We also have a negative 2 delta omega h jh, canceling out with a positive 2 delta omega h jh. So our equation is starting to simplify. That's great. But our equation still contains 2 somewhat nasty integrals over the space-like hypersurface outside the black hole. And wouldn't it be great if those went away? Is there some way those can somehow cancel each other out? That would be awesome. Well, you look at what's contained in these integrals, and in both cases, they have in common the contraction of our time-like-killing vector k with the differential element d sigma. So that's cool. And they also both have an HCD, which is the variation in our metric, although one is downstairs and one is upstairs. But those are still pretty similar. But then they seem to have this irreconcilable difference, because one of them contains the energy-momentum tensor T, and the other one contains this expression involving the Ricci curvature tensor and the scalar curvature times the metric. And how can two such different concepts possibly be reconciled? In order for these two things to be equal, there would need to be some kind of relationship between matter and energy and the curvature of spacetime. But wait a minute, there is. It's called the Einstein field equations. And if you look at the Einstein field equations, you see RCD minus 1/2 GCDR equals 8 pi TCD. Whoa, this is exactly what we need. Because what this lets us do is replace the expression in the second integral involving those r's with simply 8 pi TCD. That 8 pi is going to pop outside the integral, converting the negative 1 over 16 pi into a negative 1/2, which is a nice companion to the positive 1/2 of the first integral. And then inside the second integral, we're going to have a downstairs TCD contracted with an upstairs HCD. But that's the same thing as an upstairs TCD contracted with a downstairs HCD. And so when we subtract these two things, we're going to find 0. So by applying the Einstein field equations to that second integral, we find that the integrals cancel. Woohoo! Isn't it great when things like this cancel? It's like they vanish, they go away. We don't have to deal with them ever again. They can't hurt us anymore. And so then if we simply erase those integrals, we end up with equation 34, which is the differential mass formula. We've done it. It's been a lot of work, but we got there.
The differential formula.
Oh my goodness, it's so beautiful.
The glorious equation 34.
All right, so let's go ahead and wrap up part 3 by taking a moment to examine the differential mass formula of equation 34. Well, this equation tells us that the variation in mass can be written like so. In this equation, we have a bunch of integrals pertaining to the matter outside of the event horizon. But, more interestingly for what follows, we also have a part of the equation that pertains only to the black hole. And so if we want to focus in on that part of equation 34, we can say that the variation of the mass of the black hole is going to be equal to the surface gravity kappa divided by 8 pi times the variation in the surface area of the event horizon plus the angular velocity of the event horizon times the variation in the event horizon's angular momentum. And when you look at an equation like that, it's very tempting to compare it to the first law of thermodynamics. That says that the change in the internal energy of a system is going to be temperature times the variation in entropy, plus angular velocity times the variation in angular momentum, plus other terms depending on the system, P delta V, a term involving chemical potential and number of particles. But if we just draw an analogy between the two terms shown here, we can see that the surface gravity of the event horizon is going to be analogous to temperature, and the area of the event horizon is going to be analogous to entropy. And that's a very interesting thing, because when you think about what kappa and what the area are, these are things that we derived using the tools of general relativity. So it's kind of weird that we would find this analogy with thermodynamics. We'll talk about that more in part 4. In the meantime, part 3 concludes with the following paragraph, which is that if an infinitesimal ring is added to a black hole slowly, without allowing any matter or radiation to cross the event horizon, the area and the angular momentum of the black hole are constant, and the matter terms in equation 34 give the net energy required to add the ring. Let me pause there before reading the next sentence. What that means is that if you look at these matter terms that I've highlighted here in orange, these terms encode the part of the differential mass formula that depend on the matter that's outside the event horizon. And so therefore, if you imagine adding a bit of matter, like an infinitesimal ring of matter, around the black hole slowly, and you don't let anything through the horizon, so you're just adding it orbiting around the black hole, then in that case, these orange terms encode how much energy is added to the system in order to do that. Now then the paper goes on to say, since the horizon's angular velocity h and its surface gravity kappa do change to first order in the mass of the ring, the change in the mass of the black hole, which is given by Smar's formula, mh equals 2 omega h jh plus kappa a over 4 pi, must be taken into account in the integral mass formula of equation 13. So what that's telling us is that if we did actually add an infinitesimal ring around our black hole, there is actually going to be a first-order change in omega h and in kappa, and so therefore there's going to be a change in the mass of the black hole associated with those changes in omega h and kappa, and that's going to factor into our integral mass formula of equation 13. Alright then, let's get into part 4, the 4 laws. In accordance with the paper, we'll go ahead and start off by talking about the second law. Part 4 begins, in this section, we shall pursue the analogy between black holes and thermodynamics, and shall formulate 4 laws which correspond to, and in some ways transcend, the 4 laws of thermodynamics. We start with the most obvious analogy, the second law, which is that the area A of the event horizon of each black hole does not decrease with time. That is, delta A is always greater than or equal to 0. A never goes down. The proof of the second law actually predates this 1973 paper, because if you see reference 1, that is a 1972 paper by Stephen Hawking, in which he proves that the area of the event horizon of a black hole can never decrease. And that's known as Hawking's area theorem, so that was already known by the time this paper was written. But the paper we've been talking about in this video, by proving the integral mass formula and the differential mass formula, provides a rigorous proof for the first law and the 0th law. So then when you combine that with Hawking's area theorem, you realize, oh, Hawking's area theorem is like the second law in this thermodynamics analogy that we're constructing. And also, if 2 black holes coalesce, the area of the final event horizon is greater than the sum of the areas of the initial horizons. That is, area 3 of the merged black holes is going to be greater than the sum of the areas 1 and 2 of the original black holes. This fact about the coalescence of black holes and the final area being greater than the sum of the original areas also comes from Hawking's area theorem in reference 1. This establishes the analogy between the area of the event horizon and entropy. The second law of black hole mechanics is slightly stronger than the corresponding thermodynamic law. In thermodynamics, one can transfer entropy from one system to another, and it is required only that the total entropy does not decrease. However, one cannot transfer area from one black hole to another since black holes cannot bifurcate. See references 1, 2, and 3 for an explanation about that. Thus, the second law of black hole mechanics requires that the area of each individual black hole should not decrease. Alright, so that's the second law. The proof of the second law can be found in reference 1, but it fits right in with everything we've been talking about today as far as the analogy between temperature and surface gravity and area and entropy. So now we're going to talk about the first law, and the first law comes directly out of all the math that we've been doing today. So if you've been following along with the reasoning in this paper, then you've seen for yourself where the first law comes from. All right, let's go ahead and say a few words pertaining to the first law. Well, as we know now, any 2 neighboring stationary axisymmetric solutions containing a perfect fluid with circular flow and a central black hole are related by the beautiful, magnificent, majestic differential mass formula of equation 34, which we have worked so hard to derive. By examining this equation and thinking about it real carefully, it can be seen that kappa over 8 pi is analogous to temperature in the same way that the horizon area A is analogous to entropy. And that comes from looking at equation 34 and thinking about the first law of thermodynamics with the whole T delta S situation and saying, okay, so kappa over 8 pi is kind of like T, and then delta A is kind of like delta S. It should, however, be emphasized that kappa over 8 pi and A are distinct from the temperature and entropy of the black hole. So what we're saying here with the first law of black hole mechanics is we're drawing an analogy, a structural parallel between the surface gravity and event horizon area with temperature and entropy respectively. But that is not to say that the surface gravity is literally temperature or that the area is literally entropy. No, it's a metaphor, it's an analogy. In fact, the effective temperature of a black hole is absolute zero. They're super cold. But wait, what? Why is that? Why is a black hole so cold? Well, one way of seeing this is to note that a black hole cannot be in equilibrium with blackbody radiation at any non-zero temperature because no radiation could be emitted from the hole, whereas some radiation would always cross the event horizon into the black hole. Think about it like this. If you're sitting around a campfire, the campfire is warm because it's giving off light and that heat is hitting you, and you're like, wow, that's hot, that's heat, I can feel the warmth. And so think about the energy transfer coming from the fire to you, hitting you, making you warm. So that's why a campfire is a thing that has some temperature. But a black hole is not like a campfire. Maybe the accretion disk around it might be pretty hot, but think about the black hole itself. It's not putting out energy, it's not putting out heat, nothing at all. Well, okay, there's a little asterisk here about Hawking radiation. We'll talk about that another day. It's pretty much irrelevant anyway, it's a super small effect. But the point is that to the extent that a black hole puts out no energy to anyone sitting around it trying to warm themselves up, well then that black hole is going to be at absolute zero temperature. It's just not adding any energy to its environment. Whereas if you're sitting next to a black hole and your body is putting out some radiation, infrared, because we're warm and we glow in infrared, well, that radiation is going to go right into the black hole. And so that's what they mean by if you have some object outside the black hole with non-zero temperature giving off some blackbody radiation, well, that radiation is going to go right into the black hole. The black hole is not going to give any radiation back, and so you can't have a thermal equilibrium between a black hole and anything of non-zero temperature. The temperature of a black hole is therefore zero. Now, if the wavelength of the radiation were very long, corresponding to a thing outside the black hole that had a very low temperature, very low blackbody temperature, then the rate of absorption of radiation by the black hole would be very slow. And so it might almost feel like kind of an equilibrium, but true equilibrium would be possible only if there were no radiation present at all. That is to say, you would only have a true equilibrium if the temperature of the thing outside the black hole were precisely zero. And you know what? Another way of seeing that the effective temperature of a black hole is zero is to note that the red-shifted effective temperature theta bar of any matter orbiting the black hole must tend to zero as the horizon is approached, because the time dilation factor, negative UA to the 1/2, tends to zero on the horizon. And the way to think about that is if you're outside a black hole and you're looking at some matter going into the black hole, and that matter is jiggling around with some thermal energy, well, because of time dilation, as that matter approaches the horizon, it's going to slow down, and its molecules are going to not be so jiggly as it goes on in, and right on the horizon, the thermal jiggling of that matter is going to approach zero, that is, absolute zero temperature. So what does this mean? Well, the fact that the effective temperature of a black hole is zero means that one can, in principle, add entropy to a black hole without changing it in any way. Because think about T delta S relating to the energy or the mass of a black hole. Well, if T is zero, then you can put in a whole bunch of delta S without doing anything. And we'll talk about that more in just a moment with a little diagram and some stuff. But in this sense, a black hole can be said to transcend the second law of thermodynamics. Because at first glance, it appears to be an object that you can just throw entropy into without it having any kind of effect. So a black hole is like a trash can for entropy. Put a bunch of entropy in a bucket, toss it into a black hole, there's no big deal, the entropy goes away. Whoa, we've just found a way to transcend the second law of thermodynamics, which is that entropy has to always increase. Well, not if we throw it into a black hole. Now this is where I do have to make a comment about Hawking radiation, and without going off onto that tangent, I'll just say that when you account for Hawking radiation, you get a more nuanced and sophisticated picture of what exactly the event horizon is and how entropy relates to the area of the event horizon, and there's a lot more to say about that, but that's a topic for another day. But for now, let's go ahead and continue the train of thought laid out in this paper. So they go on to say that in practice, of course, any addition of entropy to a black hole would cause some increase in the area of the event horizon. One might therefore suppose that by adding some multiple of the area to the total entropy of all matter outside the event horizon, one could obtain a quantity which never decreased. That is to say, and this kind of relates to what I just mentioned, that even though it seems like a black hole can eat entropy and make it disappear, but because that addition of entropy in general increases the area of the event horizon, you might think, okay, so area of the event horizon is a kind of sort of entropy-like thing, and if you add up the event horizon area with the entropy outside the black hole, then that quantity, that more nuanced, sophisticated notion of entropy, perhaps then would never decrease. However, the paper goes on to suggest that this is not possible since by careful management, one can arrange that the area increase accompanying a given addition of entropy is arbitrarily small. And so the paper goes on to imagine this thought experiment wherein you can add entropy to a black hole while having the change in area be arbitrarily small, that is, approaching zero, by putting entropy into two containers and lowering them on ropes down the axis of symmetry towards the north and south poles. Now, this is quite an interesting thought experiment. In practice, how do you get ropes with buckets of entropy and lower them into the poles? I don't know, it's a tough experiment to do. But imagine, for the sake of imagining, that this is what's going on. Well, by lowering our buckets of entropy over the poles, we are going to impart no change in the angular momentum of the black hole. Imagine, if you will, that the buckets are rotating around with the same angular velocity of the black hole. So we're not torquing the black hole, we're just lowering two buckets down and keeping the angular momentum constant. So that's cool, that's going to simplify our analysis. But even still, as the containers approach the black hole, they would distort the horizon. And also the shear or rate of distortion of the horizon would be proportional to the rate at which the containers were being lowered. In the interest of time, I'm not going to derive why that is right here today, but you can see references 2 and 11 for more information on that. And in fact, the rate of increase of area of the horizon would be proportional to the square of the shear. See references 2 and 11, and so to the square of the rate at which the containers were being lowered. So we'll take that as a given, that as we're lowering entropy into the poles of our black hole, the rate of area increase is going to be proportional to the square of the rate at which the buckets of entropy are being lowered. Thus, by lowering the containers very slowly, one could ensure that the area increase was very small. That is to say, if the container lowering rate is small, then the area increase rate is going to be a small times a small, which is a very small. And so in the limits that we're very slowly lowering some entropy into our black hole, we're going to have a negligible increase in the area of the event horizon. So we can make delta A approach zero. When the containers reach the horizon, they would be moving parallel to the null vector L, and so would not cause any area increase as they cross the horizon. That's in the limit of we're lowering it very slowly. So we're putting entropy into the black hole without increasing the area of the event horizon. In a similar way, the effective chemical potential mu bar tends to zero on the horizon because of the time dilation factor, which means that in principle one can also add particles to a black hole without changing it. In that sense, a black hole transcends the law of conservation of baryons. All right, to really understand what we're saying here, let's go ahead and write out our differential mass formula and look at what terms go away when we think about this thought experiment. Well, we can express the change in mass of the black hole, like so, and then you can think about the points being made in this paragraph as saying that the variation in mass can approach zero, even if the variation in entropy and/or if the variation in number of particles are non-zero. Because you look at this equation and we're thinking about lowering stuff slowly, so that delta A approaches zero and that kappa delta A term goes away. Then because we're lowering things over the poles, you can neglect the delta JH term because we're not changing the angular momentum. So those first two terms, ignore those go away. Likewise, that first integral, that pink integral over the delta dj, that can be neglected as well because of the axial symmetry of this thought experiment. And so what you end up with are the integrals of mu bar delta dn and the integral over theta bar delta ds. Now in these integrals, you have the redshifted chemical potential and the redshifted temperature, respectively, both of which tend to 0 on the horizon. And so because those tend to 0, you can have some non-zero change in the number of particles in the mass outside the event horizon, as well as in the entropy in the mass outside the event horizon, because that's going into this black hole, while at the same time this whole equation is going to be negligibly small. So all that's to say, it seems like we can use a black hole to delete entropy and to delete particles from the universe. Now we're going to have to take this conclusion with a grain of salt, because 1 year after this paper was published, in 1974, Stephen Hawking showed that black holes do radiate. Quantum mechanically, they emit radiation at a temperature of kappa over 2 pi. And he also showed that the area of the event horizon really is entropy, with the entropy being the area divided by 4. So when you factor in Hawking radiation, you get a more nuanced picture of black holes, and you see that the analogy that we've been constructing in this video is more than just an analogy, but it actually tells us something very deep and profound about black holes. But bear in mind, we've derived this thermodynamics analogy by considering general relativity. So isn't that really neat? Like, you can think about the nature of space and time and curvature in a rotating black hole, and you can figure out how the mass depends on things, and you can draw these analogies, and then these analogies that come from general relativity foreshadow this profound discovery about Hawking radiation. But anyway, that's a story for another day. And that brings us to the 0th law. Continuing the analogy between surface gravity and temperature, one has the surface gravity, kappa, of a stationary black hole is constant over the event horizon. Now you see how the 0th law is similar to the 0th law of thermodynamics, which essentially says that temperature in equilibrium is going to spread out and become constant over some system. So if you imagine, say, like a chunk of metal with some temperature gradient, so there's like a hot spot in it, well, give it some time and the temperature is going to diffuse, and you'll end up with a constant temperature profile in equilibrium. And so likewise, if you imagine a black hole and it has some surface gravity kappa, well, that surface gravity kappa is going to be constant over the event horizon. This was already proved in section 2, see equations 10 through 12, so we're not going to reprove it here. We already put in the work back then. And also, other proofs under slightly different assumptions are given in references 6 and 2. So that's all there really is to say about the 0th law for now. Alright, and last but not least, we have the 3rd law, which is that it is impossible by any procedure, no matter how idealized, to reduce the surface gravity kappa to 0 by a finite sequence of operations. Now this law has a rather different status from the others, in that it does not, so far at least, have a rigorous mathematical proof. However, there are strong reasons for believing in it. For example, if one tries to reduce the value of the surface gravity of a Kerr black hole by throwing in particles to increase the angular momentum, because remember earlier we saw that if you increase the angular momentum, the surface gravity goes down, one finds that the decrease in surface gravity kappa per particle thrown in gets smaller and smaller as the mass and angular momentum tend to the critical ratio j over m squared equals 1. Remember, that's the upper limit for how much angular momentum a Kerr black hole can have relative to its mass. And at that limit, the surface gravity kappa is 0. But the point is that you can't get to that limit because as you keep throwing in particles, you get diminishing returns, and so you can never quite get to the limit. Mathematically, you can imagine some ideal process where you can get pretty close to that limit. But while idealized accretion processes do exist for which the ratio j over m squared approaches the critical ratio of 1 with the addition of a finite amount of rest mass, see references 13 and 14, they require an infinite divisibility of the matter and an infinite time. So that's not really realistic. There's a mathematical argument you can make, but in physical reality, you can't actually do that. Another reason for believing the 3rd law is that if one could reduce the surface gravity kappa to 0 by a finite sequence of operations, then presumably one could carry the process further, thereby creating a naked singularity, a crazy pathological point in spacetime where it's all singular and weird. If this were to happen, there would be a breakdown of the assumption of asymptotic predictability, which is the basis of many results in black hole theory, including the law that the area of the event horizon cannot decrease. So their point here pertains to something known as the cosmic censorship hypothesis, which is that even though in general relativity you can have black holes where at the center there is this strangely singular point, it's always going to be contained within an event horizon that is censored by the event horizon. So if you want to read more about this, look up cosmic censorship hypothesis. Also, you can look up naked singularity. But the long story short is that it's generally believed, and there are sound reasons for believing this, that in space, you're not going to have a singularity that's just out there in the open, naked. It's going to be surrounded, it's going to be clothed by an event horizon. And so that's all they mean by talking about naked singularity. Now, the reason this pertains to the third law is that if you could reduce the surface gravity to zero, then it's like, okay, you're sort of like taking off the event horizon. You're taking a black hole and you're revealing the singularity within it. And that's something that's not allowed under the cosmic censorship hypothesis. And now I do want to reiterate that the third law stands apart from the others in that it doesn't yet have a rigorous proof. Technically speaking, it is a conjecture, but it's motivated by examples, because if you try to spin up a Kerr black hole to the limit where J equals m squared and kappa equals 0, you find that each particle you throw in gets you closer, but the increments shrink, and so you can never quite get there. So we do have good reason to believe that the third law is true, and it also fits in very neatly with the other three laws that have been proven. And also, there have been some limited proofs of the third law under certain assumptions. So the third law is at least mostly true, and it seems very likely that it's totally true. Well, anyway, that's a few words about black holes. Thanks for watching. I hope you learned something new, and I hope you had a good time. And thank you so much to all of you who have been supporting my channel on Patreon. Your support is truly what makes it possible for me to make these videos. So thank you all so much.